Okay, good morning, everyone. Welcome to day 2 of the 34th Tactical Fire Remote Sensing Advisory Committee meeting. We had a good day yesterday. Lots of presentations on some very relevant topics to remote sensing support to fire management, and we have another full schedule today. So let's go ahead to the next slide. I just kind of want to do a little bit of a recap. From a technology standpoint, we stand on the threshold of tremendous advances in sensor technology, both airborne and spaceborne, computing power, which includes artificial intelligence and machine learning, and ever-growing data streams. So how do we harness this technology when facing the headwinds noted below? And as I mentioned yesterday, there is some institutional inertia that we have to deal with, together with declining budgets, which are a negative influence, counterbalancing the art of the possible, which is what we're here to investigate and hopefully infuse into to fire support. Some of those undermining currents include lack of funding, comfort with existing technology and ways of doing business, challenging contracting and acquisitions processes and rules, a lack of understanding of the art of the possible, distrust built up from years of being burned by sales pitches on silver bullet solutions. Next slide, please. And as Bob Baird noted yesterday, the Region 5 Fire Director for the Forest Service, failure is not an option. There's many issues that influence our ability to harness remote sensing capabilities for decision support. There's technical issues, institutional issues, funding issues, bridging the gap between research and operations, which is something that we try to do in this forum, and making connections between end users and those with capabilities. And that's really what this is. We're a community of practice, and this is a place where we share needs and gaps and the art of the possible. Next slide, please. One of the things that I wanted to keep bringing up during this meeting was artificial intelligence, machine learning, and ways to harness that to use remote sensing more efficiently for fire support. There's a number of different use cases: finding new fire starts from multiple sensors, recognizing smoke, drawing points, lines, and polygons on active fires rather than having someone do that, a man in the loop do that. Fire behavior modeling and prediction. We'd really like to move forward and advance our ability to do fire prediction and behavior modeling. And I'm sure that there's a number of other activities that we can use artificial intelligence and machine learning for. And the key point is that we have an ever-growing fire hose of data coming at us, and we need to be able to pull out the necessary pieces without putting a lot of people in front of computer screens. Next slide, please. And that's really what as I've said before, the TFRSAC is a community of practice with a number of different participants. We have federal agencies, state agencies, professional organizations, academic institutions, and the vendor community who are an important player in this forum. And the idea here is that we have to work with the end user community to understand their needs and gaps, and then push them through some mechanism to get those solutions operationalized. And there's a number of different ways of doing that, and you can see the list there on the right-hand side. And I think the next slide has the connective tissue. Can you go to the next slide there? But we're looking for ways to improve that connection, that connective tissue between the communities of practice and those various mechanisms of getting solutions operationalized. Clearinghouses is one potential way to do this. Having an innovation activity, National Science Foundation, ESIP, there's a number of groups out there that can serve as that connective tissue to bring those two sides together. Next slide, please. There are a number of on-deck presentations. There's a slim chance that we may be able to bring one or two of these on today. We have a pretty tight schedule, but I did want to recognize these folks, and we'd really like to get their presentations included in the bundle at the end of the meeting, so that those are available to people to review. I also wanted to mention that NASA is hosting a short wildfire workshop on May 19th. It's going to cover NASA GIS products freely available through the disasters mapping portal and how to use them. And you can read the rest of that there. And Jeremy Kirkendall is the key contact for an invitation. I've also posted that in the IO chat, which is now open. And yeah, so next slide, please. This came out of the Keck Institute of Space Sciences, the Wildfires That Matter workshop that happened a couple months ago. This was I'm not going to read through this because this is a real eye chart, but there's a lot of really good information in this matrix in terms of problem definitions, solutions, and actions that need or should be taken to help move the ball down the field for remote sensing support to fires to improve that capability. Next slide, please. Vince, can I turn it over to you to go through the logistics? This is a review of what we presented yesterday, but would you like to take the reins there, Vince?
Sure. Just wanted to remind everybody, obviously you're already online, so you know all of this video collaboration platform information that is posted right here. But anyways, make sure that you are able to get into the NARI website for the link, and also the agenda is at this same link as well that you see in that first bullet item. There's just general information down below that on how to tune up your video quality with YouTube, with the YouTube menu, etc. I'll go on to the next slide real quickly. And we want to reiterate that the question and answer platform is basically shown in that access to conferences.io at the very bottom of the last bullet of the 3 bullets there. So you can access that at the website too. And this allows you to put in your questions. And don't be worried that the questions will disappear, because we're collecting those questions as they are posted in Conferences.io, and we're building a large matrix of them for Everett and I to utilize during the open discussion period at the end of the day to pose those questions to the presenters who will be online as well, and allowing them to answer those questions verbally to you. And we'll also be posting those questions after the conference is done, and hopefully the answers to those questions from the participants. So keep informed and ask your questions or your comments, whatever need be, at the conferences.io platform. Next slide. Connectivity issues, you probably all will face some of those during the day. So just some general instructions on how to solve those connectivity. We had any major problems yesterday with that, but
Vince, we lost you for about 20 seconds.
Okay, I was just going to say, with the connectivity issues, you can see some of the problem solving that you may have with video feed or poor connection or poor voice connection, like I just experienced. So you can see the instructions listed up there. Reconnect if you need to a different power source, etc. Next slide.
This is the need help slide.
Yeah. If you need any help, please email your questions or comments to the email address that you see at the bottom, the last bullet, rcalnari@mail.nasa.gov, and they can help you through the process. There'll be the NARI host will be there to help support any questions or issues you may be having. Next slide. Kind of coming up slow on my system.
This is the miscellaneous slide, Vince.
Okay. So again, as a reminder from yesterday, same with any of the new participants today, Everett and I will be providing all the contacts for the attendees, the email addresses, and post-meeting. And the meetings will also be recorded and will be shared with the community at the URL you see up there, which is the same URL you're using for accessing the information on the workshop and the registration and the like, and where the agenda is. So all of those recordings will be available probably about a week or so after the event. So if you want to go back and look at some of the video presentations, you're free to do that. And again, we will provide all of the presentations at the Cloud Vault as well, U.S. Forest Service Cloud Vault, for people to download for their use, or to reference the speaker and contact the speaker directly through that email address attendance list we'll provide as well. And I think that's it. Maybe next slide. I don't know if there is a next slide. Oh, we wanted to remind people of what the TFRSAC is all about. Everett spoke to a community of practice. I'll just kind of go over that real briefly. The TFRSAC was founded in 2003, Everett Hinckley and myself, as a joint collaboration between NASA and the Forest Service to look at new and evolving technologies to improve observations of tactical wildfire support missions considerations. And we're basically a community of practice which focuses on sharing best practices and creating new knowledge. So we're not a conference. We're not an official working group within the agency. We're a community of practice where we gather a number of members of the fire community, fire management community specifically, with those of us in government, in industry, and in academia and the like, research centers. Collaboratively work on topics that relate to understanding improved information content and data collection efforts in support of tactical fire operations. We meet twice yearly in the spring and fall. These have been virtual the last few meetings. Last two meetings have been virtual, but we hope to again meet potentially in person in the fall in Boise, Idaho, where we usually hold our fall meeting, and then next spring, hopefully at NASA Ames. And we will be sure to include also a virtual presence for all those meetings as well, for those of you who don't feel comfortable traveling or can't travel. So our objectives, just as a reminder to everybody, is basically what I just said, to demonstrate evolved and evolving technologies for increasing information content and timeliness of Earth observation data collected for wildfires. So it's a member of the collaboration of the community members, as I said, from industry or NASA centers and research institutes, universities, basically looking at the gaps that need to be filled within the wildfire management community, and hopefully picking out those low-hanging fruit technology developments and observation capabilities that we can utilize to improve their and fill their gap needs within that fire management community. So with that, I think we can move on. Anything else you want to mention, Everett?
No, this is the last slide in this intro deck here, and yeah, we've got lots of great topics both yesterday and today. I believe the YouTube recordings will be available for those that want to listen to those after the fact. For the folks that are out there watching on YouTube, please use the IO link, which is on the web page there, to post questions, and I encourage folks to use that to comment to other folks as well if you have comments that you'd like to post. So please use that. And for the speakers, please watch your time carefully. We're on a very tight schedule today, and so keep an eye on the chat window there as well. So our first speaker today is John Melton, and let me bring up his bio. Dr. John Melton is a senior engineer in the Aeronautics Directorate at the NASA Ames Research Center. With over 30 years of aerospace experience, he has performed independent and collaborative research and analysis in support of the largest and smallest government commercial aircraft, space and spacecraft programs. So with that, John, would you like to do a mic and a video check? Please turn your video on.
Video should be on. Can you see me there?
Yes, we can. Thanks, John. Take it away.
Hey, thank you so much, Everett. Thank you, Vince. Good morning. As Everett said, my name is John Melton, and I'm a senior engineer at NASA Ames in our systems analysis office. And I want to say a big thanks to Vince and Everett for asking me to present some of my perspectives on wildfire science, and especially the links to the research and expertise of the aeronautics portion of NASA. or as we like to say, the first A in NASA, the first A being National Aeronautics and Space Administration. Now, this is not a presentation about NASA's future aeronautics plans in wildfire. Those plans are still under development, and hopefully we'll hear a little bit more about them tomorrow from the head of aeronautics, Mr. Robert Pierce. I hope that many of you will be able to join us for those discussions and the breakout sessions that follow. We sincerely look forward to capturing your inputs and hearing both your comments and your suggestions. Next slide, please. So over the last several months, my small group has reached out to wildfire experts, both internal and external to Ames. And that's included technical experts at NIFC, the Forest Service, CAL FIRE, the Colorado Center of Excellence for Aerial Firefighting, Department of Energy, and the Y-Fire group down at the University of California, San Diego, along with several experts local to Ames. Now, as you might expect, we've heard about the many interesting and challenging issues surrounding wildfires, and that includes everything from the tracking of individual firefighters on the ground, the many ways remote imagery is used throughout the fire season, all the complications surrounding fire modeling and model validation, the differing instrumentation levels aboard the various firefighting and supporting aircraft, the communication chain that kicks off once a wildfire is detected, the process of controlling the aircraft within the TFR that's usually created around a fire event. And we've even gone so far as to read large portions of the Dingle Act and the entire Aerial Firefighting Use and Effectiveness report, the AFUE report. Now, we know we still have a lot more to learn, and again, nothing better than yesterday's TFRSAC for expanding our horizons, that's for sure. But we've taken what we've read and what we've heard, and we've begun to look at how those issues could map to the aeronautics research that's currently being performed by NASA. Now, we realize that we've kind of just scratched the surface on the numerous wildfire activities that are underway across multiple federal and state agencies, universities, as well as the growing number of commercial data science and data service providers. Next slide, please. So this slide lists some of the alignments that we see with several of NASA's current aeronautics research thrusts. Aerial wildfire suppression and observation directly involves many of those same aviation challenges that either are or have been the subject of substantial NASA aeronautics research investments. Now, a short list of those includes air traffic control and enhanced situational awareness, aircraft control and the development of precision trajectories, the efficient deployment of aviation fleets, all types of different aircrew human factors, along with human-machine teaming and the integration of unmanned vehicles of all sizes with various different levels of autonomy on board. And that's just in addition to NASA's traditional roles of advancing aircraft design and engineering for both fixed and rotary wing vehicles. Now, many of you may know NASA Ames is leading two very relevant flight projects, demonstrations for this season, including both the Swift high altitude long endurance vehicle that will be used to capture some high altitude imagery over some fires. And yesterday, probably many of you heard about Joey Mercer's stereo project that provides kind of a UTM in a box capability for managing unmanned vehicles and enhancing situational awareness in the fire zones. Now, we're also using some aeronautics research funding in the development of what we call the data and reasoning fabric, and that's basically a framework that's currently under development to support numerous aviation and civic data services. Next slide, please. So I thought I'd take a look at where all of those previous research areas align with the research that is performed by NASA's Aeronautics Research Mission Directorate, ARMD for short, because NASA never has enough acronyms. So I've extracted these images directly from the Aeronautics Strategic Plan. Now, NASA's aeronautics research is driven by 6 primary strategic thrusts, and each of those thrusts have outcomes that are defined out beyond 2035. Now, the work towards those 6 thrusts are carried out in 4 primary programs spread across the research centers. And depending on the time frame you choose, I think that 5 to 6 of those strategic thrusts have direct relevance to wildfires. Next slide, please. So what specific aeronautics competencies does NASA have? Well, every NASA center obviously is a little bit different, but there is a lot of commonality, and the research programs often involve expertise that's spread nationwide and across multiple centers. So in this chart, I've highlighted, or this chart illustrates 8 of our core competencies here at NASA Ames, and I've highlighted 5 of those core competencies that are directly engaged in either aeronautics research or our Earth Science program, all of which have, of course, applicability to wildfire aviation and wildfire science. So if we start in the upper left and we work our way clockwise, Ames is the lead center for air traffic management research. Next, we also host the agency's primary supercomputing facility. We also have a large division of experts focused on all aspects of robotics and autonomy. Vince spoke yesterday about our Earth Sciences program and all the remote imagery work that's done there. And of course, we're very, very proud of our long history of wind tunnel and computational aerodynamic and engineering support that Ames provides to all of the nation's commercial and government aircraft and spacecraft programs. Next slide, please. Now, the research that we do at Ames is performed in some very unique facilities. That includes a very wide range of wind tunnels that provide the ability to test full-scale, kind of medium-sized aircraft and rotorcraft at very relevant airspeeds. We also have agency-unique simulation labs for both air traffic controllers and aircrew, including an extremely sophisticated 747 cockpit simulator and the vertical motion simulator, which is a mobile cab that can simulate large motions in both the horizontal and vertical directions, and it kind of provides unparalleled force feedback simulation realism. Now, these piloted flight simulation facilities were engaged about a decade ago in the handling studies for the Very Large Air Tanker program, and they've been used to simulate every possible type of vehicle, from airships, helicopters, electric air taxis, F-35s, space shuttles, and moon landers. Now, finally, our advanced supercomputing facility allows us to run the most sophisticated and detailed climate and atmospheric models, along with the full array of detailed numerical engineering analysis simulations that are required for aerospace vehicles of all types. And of course, each facility has a smiling, experienced supporting staff that's usually a mix of career civil servants and contractors. Next slide, please. So this slide is my attempt to put some structure to wildfire aviation research areas and to initially align them with NASA's aeronautics experience. Again, just my opinion, and we'll hear more from NASA headquarters and Mr. Pierce tomorrow during his presentation. I personally see wildfire aviation research collaboration opportunities falling into basically 3 large buckets. Now, that first bucket focuses on enhancing the aerial operations and their effectiveness. That second bucket would focus on early detection and rapid response. And the third bucket would focus on the safety of aircrew and the development of future air traffic control strategies in fire-impacted airspaces. Now, obviously, there's a lot of overlap between each of the activities in these buckets, so different groupings are possible, and there will be a lot of common data that needs to be shared between each bucket. Now, I've highlighted this sharing of data with the green line, but that green line would absolutely have spokes that extend out to other partner groups and data at other agencies. These tasks would, of course, just be kind of an aviation-focused extension to NASA's existing wildfire support activities. And I'll go through each of these three big buckets in more depth on the next three slides. So next slide, please. So the first of my buckets focuses on improving aerial operational effectiveness through analysis, optimizations, and autonomy. One potential product could be the development of kind of specialized environments for the replay and the analysis of wildfire aerial operations. I can imagine replaying scenario data that, for example, was maybe collected by Stereo and the SWIFT exercises that will happen this year, as well as looking at historic flight path data that NASA can pull from its Sherlock and other FAA flight history and trajectory databases that it has access to. These replay and analysis environments could combine data from external terrain, wind, weather, fuels, fire models, etc., and be a first step in helping to create those big collated data sets that are necessary for machine learning and the development of fleet deployment and route optimization strategies. Now, finally, these type of environments could be used to study the tactical and strategic impacts of the integration of autonomous vehicles. And that would likely start first with the small multi-rotors that are planned for use as comm relays, pre and post-fire surveys. But it could eventually include larger UAS up to including potentially future autonomous air tankers. Next slide, please. My second bucket here focuses on accelerating and streamlining the early detection and response chain and providing some of the data-centric services that are useful to other high-end decision support tools. The data and communication services provided by the Data and Reason Fabric could be leveraged here to connect with external data services and provide an easy mechanism for sharing some of that space-based imagery, the imagery that comes from new high-flying UAVs like the SWIFT, low flyers like in Stereo, data from Civil Air Patrol and other early detectors. There's also a great potential here for NASA's high-end computing capability to provide rapid real-time modeling of expected fire behaviors. And finally, we see opportunities for the development of very sophisticated decision support tools that make kind of risk and uncertainty-based suggestions and provides them in real time to incident commanders as kind of a shadow mode recommender system. Next slide, please. So my third bucket of activities is designed to improve the safety and effectiveness of the air crews and air traffic control, both now and in the future as more autonomous aircraft play an increasing role. Again, NASA Ames has some very relevant history in this area in the development of the VLATs, human in the loop simulations that include both pilots and controllers are an Ames specialty. And those simulations will become increasingly important as we try and understand the multiple interactions that occur as we pair manned aircraft with unmanned autonomous wildfire support aircraft, and that could include also ground vehicles as well. We could also study ways to lessen the impacts that larger fires that are occurring more often at the urban interfaces and look at ways to mitigate their impacts on the commercial operations at nearby airports. These high-fidelity simulators will also be vital in the creation of the new decision support tools that take advantage of all these new capabilities that arise from the human-machine teaming. We need these high-fidelity simulators in order to kind of play out scenarios and understand all those interactions. And we want to do that while we're also ensuring the safety of everyone, both in the air and on the ground. Next slide, please. So I want to end my talk today by sincerely again thanking Vince and Everett for giving me this opportunity to share my thoughts with the TFRSAC community. I also want to say thanks to the many different organizations that were willing to basically accept a cold call, either from me or from a member of my team, as we try and get smarter and develop the background information that we then share with our senior management. Wanted to also say a big thanks to Sean Triplett of NIFC and his team for their willingness to speak with us, and also to Ben Miller and his team at the Colorado Center of Excellence for Aerial Firefighting. We've enjoyed all of these discussions. And to the many others that we hope to speak with in the future, we look forward to those opportunities. Please do join us tomorrow to hear the perspectives and the plans from NASA headquarters. And we also strongly invite you to participate in the networking and the discussion activities that will occur afterwards. So thanks very much. Everett, I did want to say one thing about what Mr. Baird said yesterday about that very famous quote from NASA that, failure is not an option from Apollo 13. I'm going to add another one to there that we also use, and that is, in God we trust, all others bring data. And to kind of follow up with your machine learning bent, I'll say bring data, but make sure it's been cleaned and collated as well and is ready for use. But yeah, multiple relevant NASA sayings, and we look forward to supporting these expanding wildfire efforts, no doubt. So thanks again.
And thank you, John. I've enjoyed the continuing engagement with you and your team. And this is exactly the type of iterative learning and sharing of ideas that we like to see coming out of this meeting.
Great.
And thank you also for your closing mention there of machine learning and artificial intelligence. And yeah, I've seen lots of cautionary notes about jumping into that pool. That I just actually found a really good article about that yesterday about some of the cautionary notes about machine learning and artificial intelligence. So that's well taken. So thanks, John, and we'll go ahead and move on to the next speaker.
Great, thank you.
We have Cherry and Matthew from Dryad, and he's going to present on a sensor-based approach to forest fire detection. And I'll bring up your bio here. Cherian is a full-stack software developer and architect with more than 18 years of experience in industry, academia, nonprofits, and startups. And he has a strong interest and focus on high-impact work and he's the cloud platform lead at Dryad Networks.
Thanks a lot, Everett. Hi, everybody. As already mentioned, I'm the cloud platform lead at Dryad Networks, which is an early stage startup developing an ultra early warning system for the detection of wildfires based on a network of sensors which detect gases emitted at the very early stage or the smoldering stage of a wildfire. Next slide, please. So our immediate goal is, of course, to protect the forest from the spread of wildfires. We aim to potentially cover entire forests, or at least the most vulnerable part of regions of forest, and most importantly, provide an early and real-time monitoring alert system. Since this is a ground sensor-based approach, the solution will provide accurate location information, allowing us to send out alerts with detailed information related to the location of the fire. So on this slide on the right, you can see an example of a fire alert in the form of an email, which gives precise information while the sensor which triggered the fire alert. And being an early detection system, we also aim to provide a solution which is robust and reliable in preventing the spread of wildfires. The main benefit, of course, is the early alerting, which means that we can react immediately and get resources on the ground faster, limiting the potential damage caused by the fire. And in the long term, we want to expand the solution to cover other use cases where a remote sensor, a ground sensor-based approach would be a good fit. So this could be natural disasters. We've already talked about wildfires, but also floods and hurricanes. Protecting natural assets is another aim by monitoring pollution, carbon emissions, and other environmental factors. And the solution can potentially be deployed in water bodies like oceans, rivers, lakes, and also in domains like agriculture to, let's say, monitor the health of soil or the moisture levels. We expect to generate a considerable amount of data, which we can make available to scientists and policymakers for further analysis. Next slide, please. So our end-to-end solution, which we are calling Dryad SilverNet, is a network of sensors which are made up of two types of IoT devices. The sensor nodes, which detect gases emitted during the smoldering phase of a fire, so really early stage, and the gateways which pass on the data from the sensor to the cloud and the other way around also, vice versa. The network is built over the LoRa specification, LoRa standing for long range, and more importantly, the LoRaWAN protocol, LoRaWAN standing for a long range wide area network, which together provide long range, low power consumption, and secure data transmission. This approach is ideal for sensor deployments in remote areas like forests with little or no access to power supply or even cellular mobile networks. The sensor nodes are solar powered and are being designed to use as less power as possible. And this is further enhanced by our patent on energy harvesting for sensor devices. And along with the fire detection, the sensor nodes also currently detect temperature, pressure, and humidity, which we can also make available if required. For the gateways, we are extending the LoRa specification to add mesh networking capabilities, which will allow us to scale up for large area deployments. And the last piece of the puzzle is the cloud platform, which does a number of things. It manages the registration of the devices, so the sensor nodes and the gateways. It monitors the health of the sensor network. And most importantly, it's responsible for sending out fire alerts to relevant personnel. Currently, this is email, as you've already seen, but we're working on expanding the notification system to include other messaging protocols, as well as integration with fire management systems. We will also provide an analytics component, allowing third-party users to have access to and to analyze the data that's produced by the network. Next slide, please. That's like a overview of the sensor network. At the edge, you see the sensors, which will detect which will detect the fire at the early stage and send out the fire alert to the mesh gateways. The mesh gateways actually don't have any connection to the internet, so they can be deployed in the deep forest, and their sole purpose is to pass on the message to eventually reach what we call a border gateway, which will be located at the edge of the forests, connected to the internet, either via satellite or via mobile networks, whichever is available. And the message finally reaches the network server, which is a component in the cloud, specifically part of the LoRa specification. And our cloud analytics platform connects to this network server to perform the management of the devices, to also monitor the network, as well as sending out the alerts. Next slide, please. I think it's important here to locate our solution in the ecosystem of the various solutions that already exist. I think we can all agree that the more time taken to detect and stop wildfires, the higher the chance for the fire to cause damage at an exponential rate. So clearly, early detection is the key. And we at Dryad, with our solution, we are focused on this early stage detection of wildfires. The time taken for the sensors, these gas sensors, to detect a fire is actually dependent on a number of environmental factors. But let's say a ballpark estimate for the sensors placed at, say, 100-meter distance from each other should detect and trigger an alarm within 30 minutes to 1 hour or even faster if the conditions are right. On the flip side, it may not be always feasible or even cost effective to cover large forests with sensors, in which case the focus will be on the most vulnerable areas of the forest, so near roads, hiking paths, campfires, etc. I would like to emphasize here that we are really committed to preventing the spread of wildfires, and that's the main reason why all of us have come together to work on this project. And even though we believe that Dryad Silvernet is an important element in the overall solution, it will still be one part of a much larger ecosystem of solutions. So we are really looking forward to a collaborative approach to solving this very difficult problem. Next slide, please. So quick look at the team. We are 7 co-founders with many years of experience in our respective domains, from hardware design development of the sensor nodes and gateways to embedded software running on the devices, to the work on the cloud platform, which I myself am responsible for. This also includes expertise in corporate strategy, business development, and financial planning, and all of this specific to the mobile network domain. And also scientific research experience, interestingly, in forest ecology, in particular forest fire detection, which will be very useful for us when we actually deploy the networks in the forest. Next slide, please. So moving on from the prototyping phase, the next areas of focus for us will be mainly collaboration. We are really looking forward to be part of a community of experts to help us deliver a solution. And it's really exciting to be in this meeting. I've already learned a lot and seen a lot, many sides of the problem which I didn't know about before. There are, of course, gaps in our knowledge, especially when it comes to integrating with fire management systems. So we would be really obliged if and appreciated if we can collaborate with people who are more who are experts on this. And of course, we're happy to share our data and collaborate with the wider community. I've already seen some areas of work which would be really interesting for us, like fire behavior modeling, fire prediction, even post-fire analysis. And of course, the last mile delivery, which already has been talked about quite a bit in the meeting, getting a solution into the hands of firefighters on the ground. I think the focus for us mainly is to be able to, since we're designing and developing the solution now, is to have access to stakeholders who can inform us about the most efficient and optimized ways in which we can deliver our solution, and provide a user experience which makes it easy for the end users to use the product. Also, proof of concept, we will be soon setting up POC live deployments in forests to verify that our solution works end-to-end. So if anybody's interested in partnering with us on this and collaborating with us on this, we are more than happy to have the discussions. Next slide, please. Just a quick look at the roadmap. From a product development perspective, last year was spent mostly working on an MVP for acquiring funding, investor funding, which we have done successfully. Currently, we are very close to releasing a beta product, which is essentially a fully functional end-to-end product from the sensors to the gateways to the cloud platform. And shortly following that, we will be deploying live test deployments in the forest, proof of concepts, which will run till the end of the year with different partners. And by the end of the year, we expect the solution to be verified using these proof of concepts. First customers we hope to have from the beginning of next year. And hopefully by the end of next year, deploying large-scale networks in Europe and America. And finally, in 2023, the expansion to the largest forests in the world, in Asia and Latin America. From a funding perspective, we have completed a seed funding round last year. Just recently, we were funded by the European Union through a European Union project. And we are hoping to complete a Series A funding round by the beginning of next year. Next slide, please. And that's it. Thanks to everyone for organizing the event. It's been really interesting to be here, and especially to Everett for the invite and giving me a chance to speak today. I'm looking forward to the questions later, and also any feedback, suggestions, advice that you may have for us. I don't think I mentioned it before, but we're actually based in Germany, in Berlin to be precise. I would ask you also if you would like to visit our website, it's simply dryad.net for more information. And there's also actually a few videos which are videos of demos that we've done in the forest, which are quite interesting. Please don't hesitate to get in touch with us if you need if you need any information. Thanks and have a great day.
Thank you very much, Jerry, and that was great. And I've really enjoyed our engagement over the past couple months here. So thank you for presenting today. And with that, we'll go ahead to our next speaker, Parimal Korpardikar, also known as PK, which I prefer. He has served as the director of NASA Aeronautics Research Institute, or NARI. In that capacity, he is responsible for exploring new trends, collaborations, and partnerships needs related to aviation enterprise. So with that, I will turn it over to PK, and go ahead, PK, if you want to turn on your camera and give a sound check.
PK, we're unable to hear you. It looks like you're still muted, PK.
Yeah, I'm ready whenever you are.
Yeah, go ahead, and if you'll turn your camera on, if that's possible. There you go. We see you and we can hear you.
Okay, perfect. Are we ready to go, or you still need time?
Nope, you're ready. I've introduced you and given your bio, so you're ready to go.
Okay, perfect. Thank you again. We are immensely grateful. First of all, I want to say for the service Everett and Vince have offered for last 18 years. And NASA Aeronautics Research Institute is working with them. But really, the NASA Aeronautics Research Mission Directorate is very happy to collaborate with the TFRSAC and grateful to have the third day added to TFRSAC to work with you on identifying additional, basically, research items that NASA Aeronautics, in collaboration with NASA Science Mission Directorate, could offer to support the firefighting. So Lori Grindle and I are co-leading this effort that you will see tomorrow related to gathering of the needs as how best NASA Aeronautics can support the wildfire fighting activities. So that's the intent of this quick chat here with you all, to give you a preview of what is going to happen tomorrow. And I would like to introduce my partner here, Lori Grindle. Lori, can you come on the video for just a second, so you all know who she is. And we will be talking to you a lot more detail tomorrow. So there she is, I think.
Yep.
Okay. All right, next slide, Anna, please. Okay, so what we are after tomorrow is understanding comprehensive needs of wildfire management. And when we say comprehensive needs, what we really are after is planning season, during the season, predicting, detecting, tracking, mitigation, suppression, and post-fire remedial efforts. And like to kind of sort out in 3 different buckets. Near term, how can NASA help collectively in the near term, midterm, and a long term? So some reflections from you all about what your priorities and what your needs are when NASA can contribute to value. We are here to be a supporting organization in collaboration with many other entities that already exist, but our charter is to conduct research to support you, and we are not interested in sort of taking the operations over or taking over anything that is already going on really well. So idea is to augment what needs to be done, given that the fire seasons are growing longer and bigger. We want to help and participate in reducing the impact of wildfires and mitigate them for the overall betterment of the climate and Earth. So we will use your input that we get from aeronautics, science, space perspectives, and formulate our research, development, testing, implementation opportunities to improve the state of the art in wildfire management. And I'll just give you one example. What we have seen is current wildfire fighting occurs during good visibility conditions, low wind conditions relatively. How can we expand the envelope of that to maybe 24/7? Have more aircraft fighting, possibly have better aircraft surveilling that and pinning down where exactly the fire is and such. So there are many areas where we feel very passionate from our perspectives that we would like to see how best we can help you. Next slide, please. So there are three ways you can actually contribute tomorrow. One is basically request for information and response to that. And many of you have already done that through your entities. We have over 50 requests for information responses, which is just awesome at this stage. And we got gathered much good information, and based that gave us ideas about what kind of breakout groups we need to have. We have over 300 registrants, as you probably saw already, and those will be then put in 4 different breakout categories, but there are 2 breakout sessions that you will see tomorrow. And these include preseason, surveillance, during season, and suppression and mitigation, as well as the post-season, post-fire season. So those are the basically rough categories in which the breakout sessions will be executed. In addition to the breakout sessions, because we have so much interest and passion around this by many folks, and some of them are able to participate fully, some of them want to bring in more ideas, we have also opened a feedback response form where you can start to contribute your ideas a priori now or tomorrow or later as to what else can be done. If you didn't get an opportunity particularly to talk about what your ideas are tomorrow in full extent, you can also provide your response on this form. Some people like to write, some people like to explain things verbally. So this is one of those ways you can actually contribute as well, in addition to being present tomorrow. And if all that fails and you have really interesting ideas that don't conform to any of the categories we said per se, but really creative, you are welcome to send us a free text email as well at that NASA Aeronautics Research Institute email address. So we'll capture those. So we're looking forward to your strong participation tomorrow, and like to continue the momentum of that TFRSAC has built for the last 18 years, and we are very grateful for the opportunity to piggyback the other side of TFRSAC, our workshop here, and we are looking forward to continuing to nurture that relationship. We want to collaborate with, of course, all entities, Forest Service and Agility Prime DoD. Air Force is co-sponsoring this activity tomorrow as well. Next slide. And this may be your last slide. Yeah, so that was it. Are there any questions for Lori or I?
PK, we'll hold the questions, and you may want to check the IO chat window there to look for anything that's directed at you. We're really looking forward to the meeting tomorrow, and I too am excited about the collaboration that we've developed here over the past couple months, and I'm really glad to see this. As you noted, you used the word augment, which is a word that I like because it suggests that you're trying to figure out ways to fill existing needs and gaps, and do that in a very careful way. So I really appreciate that. So just keep an eye on the IO chat window, and with that, we'll go ahead on to Dave Jones, and who's going to be briefing on GeoCollaborate. I'll introduce Dave. He's the founder and CEO of Storm Center Communications, Inc. He's an AMS Fellow and a 2020 ESIP Partner of the Year. Dave Jones is the CEO of Storm Center Communications and has presented at TFRSAC over the years about his SBIR Phase 3 technology called GeoCollaborate. And Dave, could we get a sound and a video check with you?
Sure, test. Everett, can you see me okay?
Now I can, yes, and your sound is perfect, so go ahead.
Oh, great. Okay, thanks, Everett. I appreciate that, and thanks for the invitation you and Vince for me to give another update on GeoCollaborate. We continue to see progress working with other federal agencies as well, and I'll mention that in just a few minutes. But I did want to show that this first slide here was what I briefed last TFRSAC, was when we provided support for the California Civil Air Patrol and the California National Guard to provide a collaborative common operating picture for them to address some task orders that were issued for imaging for a damage assessment in the August complex wildfire. We're funded under the JPSS river ice and flooding and fire and smoke initiatives. So we operated under the fire and smoke initiative to see if we could provide the HER smoke model, the high resolution rapid refresh smoke model, in combination with FAA flight restricted areas, TFRs, temporary flight restriction areas, and also those yellow boxes, which were the task orders issued by the California National Guard of actual imaging locations where they needed. So that was very successful, and we're looking forward to seeing how we might be able to support the JPSS program and perhaps work a little bit more with the California Civil Air Patrol with validating and verifying some of this HER smoke model data, which is very exciting. Next slide, please. So over the last 6 to 12 months, we've really been working with a lot of agencies, and we've noticed some key things, and that is that key components in the trusted value chain, data chain, are needing to be addressed. We've also noticed that there's a need to address stakeholder identified gaps in that value chain and optimal workflows and services that are necessary to produce both AR by many agencies, chief data officers, things like that. They're primarily focused on how can they make their data available and get it in similar formats and all that sort of stuff. But overall, what we've noticed that there is a need to use key technologies to provide vital information to stakeholders, to do it rapidly and to do it in a way that you can engage anybody, anytime, anywhere. Next slide, please. And so this is really very interesting. By some estimates, we've even done some interviews ourselves with some operational users, but 80% of response time is spent procuring and looking for data, so that 20% of that time can be spent learning from it, analyzing it, and putting it to work. Now, we supported some folks up in Alaska, and after we did a hot wash, did some interviews, and we found that 40 to 45% of hydrologists are spending they're spending 40 to 45% of their time in their shift just trying to identify data they can use to put to work. And if we can just unlock some of that time in getting people faster access to data, then we can really accelerate the decision-making capabilities for those who may or may not have technical expertise, but need to look at geospatial and other data and make rapid decisions. So where we work very closely is at the interface of science data and that decision maker who doesn't have science expertise. And so GeoCollaborate is really designed to connect anybody, anywhere, on any platform in a synchronous way. So everybody's looking at this collaborative common operating picture. Next slide, please. So I've briefed this last TFRSAC, but I got some really good comments back on it because it was something that helped to identify or describe how GeoCollaborate works. Many of you may be in this boat as well when you give briefings. Typically, you have a lot of browser tabs open from different websites showing specific things that are really useful, and you page through those browser tabs when you want to give a briefing. And then you use screen sharing, like we're doing today with Microsoft Teams, Google Meet, or Zoom, or whatever. And essentially what GeoCollaborate does, you can hit the next slide, is it pulls the trusted information from those sites from those portals, from those hubs, from those geospatial, sort of one-stop shop areas, and pulls it into a map so everyone can see the same map at the same time. But the key with GeoCollaborate is it's not screen sharing. It's actually sharing the data to everyone's platform in real time. So it makes it much more effective and impactful when you're looking at data that you may or may not even know exists, and you can interact with it by clicking on it and interrogating it and things like that. So what we really have focused on over the last 10 years, believe it or not, through this SBIR program and other funding from NASA's Applied Sciences Division, is that non-experts are going to be using the data, and non-experts are going to be looking for data. So why would we make non-experts have to search and find that data? It really should be presented by subject matter experts and interpreted and shared with people in real time. So we're talking about delivering disparate sources of information in real time onto anyone's web map on any of their devices. Next slide, please. So essentially, from a user interface standpoint, and we will have a demo during the break. I'll ask people to connect and we'll have a little bit of fun where you have a leader that logs in with credentials, and then anybody else who connects to a URL can connect as well and follow in real time. Now, it could be credential-based, doesn't have to be credential-based. This demo won't be credential-based. And then down the bottom, there's a collaborative dashboard that's designed to keep up in any ops center, anybody's police station, fire station, even citizens. If it's a citizen public-facing capability, could then interact with the data sets that the subject matter expert is staging for them to look at. So it's a very simple interface for a way to present scientific information to decision makers and or the public. We've heard a lot of people saying we need to keep communities updated on what's happening, but yet it really doesn't exist with a collaborative kind of approach. Next slide, please. So from a 10,000 foot standpoint, we're talking about disparate system interoperability. It's been talked about for decades. There have been presentations, and people even today say we need to have a data sharing capability so everybody knows what everybody else is looking at. Well, we have it. It's GeoCollaborate. It was developed under the federal government's SBIR program, and we're now in a phase 3 status, meaning that any federal agency can immediately acquire this technology and support services, training, things like that on a sole source basis, because we've gotten to phase 3 status. This diagram shows how trusted data sets can be accessed and shared across agencies, across organizations, displayed in operations centers, political leaders, mayors, governors, association presidents could access data and information and see it in real time. Also, private sector data sharing is certainly a capability within GeoCollaborate, so we can put more data analytics and machine learning to work. Next slide, please. So this is what I'm talking about, and everybody has probably seen this kind of graphic. You have all sorts of trusted data sources out there. Where are they? How do you find them? You get them into your decision-making and situational awareness environment. Could be street data, building, vegetation, AI, machine learning, any type of integrated data sets, whether it's drone data or things like that that you want to bring in. It just has to be provided as a data service, as an OGC compliant format. And then we can start testing it and playing with it in GeoCollaborate to see how it shares across platforms and in real-time situations. So we can then provide feedback to that data provider and say, hey, this is going to work, but everybody's going to really need a high bandwidth connection. And we have to be very sensitive to the mobile devices, the phones, and all that sort of stuff. So let's see what we can do about making the data a little bit more friendlier to share. Next slide. We're really creating an agile, collaborative, common operating picture. And so the slide did change, just some of the terms on the right changed. Sean talked yesterday about the National Incident Feature Services. They can be brought in real time. NIFC data sources, perhaps sustained IR imagery from hail, although that's in its research modes. We could certainly integrate GeoCollaborate into research environments to test how that data should be processed and formatted to make it most valuable for decision makers on the ground. DOE, FireGuard output, any of that stuff we could work with and pull into this collaboration community. So it really means if you're working in an ops center and you want to share data to a fire chief, you can get them to connect without any complications. If the police chief needs to know what's going on, they can connect in. If counties or municipalities need to connect in, they can connect in. Next slide, please. And so we've also introduced, and we've worked over the last 3 to 4 years with a group called the All Hazards Consortium to introduce, this has really been a pull from decision makers, operational readiness levels. It's an evolving trusted data sort of ranking. So non-experts can look at these ORL numbers and immediately trust the data. They don't have to spend 10 minutes trying to find out the lineage of the data, where it's coming from, who's processing it, who's touching it before they see it. And so this really comes from the executive director of the All Hazards Consortium, and also several utilities, investor-owned utilities around the country, who really want to take advantage of more science data to make drive their decision making, but they don't know where the data comes from, so they need some sort of trust level. Next, please. And so we're supported, as I mentioned, by the NOAA JPSS Fire and Smoke Initiative, and also by the River Ice and Flooding Initiative. And so next slide, please. I just wanted to show how this data sort of comes together. So we're able to pull in HRR smoke model, which is now operational, by the way. It's just been made operational at the beginning of this year, which is terrific. Fire temperature RGBs, the active fire products being produced by SIMS at the University of Wisconsin. We can pull that data in very quickly. And so I think all of these products that are coming in are able to be shared out in real time across platforms. Next slide, please. And also, here's an example of one of the fires last year that approached Mount Wilson Observatory. Next slide, please, with active fires detected, and also the live fire perimeter data. This is a video. You can go ahead and play that just for a second. This is from the Alert Wildfire camera from Southern California Edison. So we were able to look at that and make that available through GeoCollaborate so people could see that camera as well. We are doing this all as a test in our Fire and Smoke initiative. Next slide, please. Okay, and this is just an example of GeoCollaborate showing some post-fire threats, showing burn scars, and also zooming in on those burn scars to access the USGS debris flow probability product, which has been so far pretty impressive, where you can inquire on that data. Anybody who's in a collaboration session or using the dashboard can touch those individual polygons and see what the probability is for debris flows should they get rain. Next slide. And this is an example on the left of the HER smoke model combined with the EPA air quality sensors, so we can take multiple agency data and put it together. Now, keep in mind, we're not producing any of this data. It's all coming from the trusted source and is being shared across the platforms. That's where we focus, sharing across platforms in real time to give people that situational awareness as a group, so you can have collaborative decision making. On the right-hand side is some flood threats that happened just last week in Arkansas. And this is derived flood areas from the VIIRS sensor on NOAA 20 and SNPP from NOAA. Next, please. And so here is an example of Civil Air Patrol over Paradise, where they gathered all this imagery. They gave us a couple gigabytes of GeoTIFFs, and we sent them off to University of Wisconsin. In a few hours, they processed them, made them web map tiles, and we were sharing them within GeoCollaborate. So, so this damage assessment imagery can be out very quickly. It really takes working with the data curator, the data provider, and making sure that we're producing them in forms and formats that are easily shareable. That's the key term, easily shareable. Next slide, please. And so that's my last slide. I just am happy to announce that just 2 weeks ago, a paper was published, which is a call to action for global access to and harmonization of quality information of individual earth science data sets. This is an international collaboration effort. I was thrilled to be a part of it. And it just talks about the need to have data sets and data formats of high quality that are available to drive decision making. So I'll stop there, and I know we're going to go into a break, and I can talk a little bit more about how the demo will work. So Everett, thanks very much.
Yeah, thanks, Dave. That was great. And as always, you know, I'm glad to see the continuing evolution of this capability and the new data sets that you just mentioned, one that's just come online there. That was the smoke layer.
Yes, the HER smoke model is now operational at NOAA. So it's running in their operational environmental modeling center. So now we have vertically integrated smoke and near surface smoke forecasts that are updated every hour. I'm going to share some of that data during the break.
Okay, and bringing up NOAA there, we've had a lot of collaboration with them recently. They're very interested in some of our fire products to help them with their weather prediction around fires. So yeah, so we're actually running a little bit ahead of schedule, which is fine. So I think we'll start our break here in just a minute or two, and I think we're going to bank this time for the next block of speakers, just in case we run a little bit long, and hopefully we won't. There is one other presentation that I would like to squeeze in, if we can. So if we can stay on schedule, we'll go ahead and come. I guess we'll come back from the break around 12:45 Eastern, or 45 minutes after the hour, whichever time zone you're in. And so get up, stretch your legs, get some food, do whatever you need to do, human breaks, and come back at 45 minutes after the hour.
Hey,
and Dave is going to be doing a demo. So if you want to experience GeoCollaborate over the break, please stay online here, and Dave will give the instructions what needs to be done. Vince?
That's just what I was going to bring up for you to mention. Thank you.
Thanks. So Dave, if you want to put your your video, and I believe there's a link that folks need to tag into. So
yeah, that's right. And I'm going to share my screen as well, if I can do that
sure.
during the break. So let me pull up GeoCollaborate, and I can give everybody the address. So you should be able to see GeoCollaborate up currently.
It's coming up right now. There it is.
Okay. And so the address that I'd like everybody to go to is this FS. So fs.geocollaborate.com. As a matter of fact, maybe I guess we can't really put it in the chat because it's YouTube.
Dave, if you actually drop it in the chat for me, I can add it to the YouTube chat as well as Conferences.io so people can pull it from there.
Oh, terrific. Okay, well, I'll do that.
Why don't you let me do that, Dave, and you can concentrate on what you're doing there.
Okay, thanks. And the address is really going to be the /follow. So it's fs.geocollaborate.com/follow. Going to be this one right here.
Okay, I'm posting it now.
Thank you, Everett.
Yep.
Awesome. And so, I'm going to keep this pretty informal because it's just, to really demonstrate a couple of things that GeoCollaborate can do. I'm going to give people some time to connect to that address. Again, it's fs.geocollaborate.com/follow. And what should come up is this map. So the map that you see right now is a web map, and you can move around it, zoom in, zoom out. And it's just like any web map you're probably familiar with every day that you work with. The thing about GeoCollaborate is once you turn GeoCollaborate on in the upper left-hand corner, there's an on-off switch. Once you turn GeoCollaborate on, then your map will zoom out to match my map. And so, so I am leading this session, and I'm going to turn, I just loaded a couple of data sets here, so let me just turn them off. And then what's on your web map matches mine. So I just turned off some data sets, and they will likely turn off on your map as well. But what I want to show you is if you have GeoCollaborate on, I now have control of your web map. So now what this means is, again, we're not using screen sharing if you are connected through the other web connection. And what you should see approach, and you can change your base map as well by deploying the left-hand arrow, and a little menu will pop out. And then you can click base map. And I like satellite because if you zoom down to the street level, then buildings show up and all that sort of stuff. But as we zoom into certain areas, then you will start to see that data appear. So for example, in this particular fire burn scar perimeter, this fire perimeter, this is the August complex fire. You in your web browser can actually interrogate this data. You can click on it. You can interrogate the colors from the USGS product. You can see that it's the August fire complex. And so what's happening here is actually I'm instructing all of your web browsers where to go and get this trusted data, and to do it in such a way that we're connected in a real-time collaborative environment. So I can zoom back out. And for those of you who are happy clickers, I know a lot of folks who like technology are probably trying to click around and move the map around, and it's probably coming back to my view because I am the leader. Now, when I go and turn on this HER data, this near surface or vertically integrated smoke, you'll see it appear on your web map as well. But you can turn GeoCollaborate off, and then you're free to move about the country. You can zoom in, you can zoom out, you can look at data sets and things like that. We could put in test data sets, we could put in imagery and all that sort of stuff. This is vertically integrated smoke from the operational NOAA model, the HER model. And you can see where some sources are, but remember it's vertically integrated. So it's through the course, through the entire atmosphere. So it may not be too thick. You see it's thick in certain areas, like down here in Arizona. I'll zoom in just a little bit. There's a little bit thicker smoke here from a fire that's burning. Now, if I zoom back out, I want to do one other thing. I want to get, I'm going to turn off this data layer, the vertically integrated smoke data layer. And I just want to go and turn on a data set of the EPA AirNow air quality sensor data. And occasionally this, when AirNow is doing data testing, sometimes it turns on, sometimes it doesn't. And since it's not turning on for me, because I never set up a bunch of data sets for these demos because I want everybody to see how GeoCollaborate works in real time. I'm turning on now a NOAA GOES satellite image, which is a full disk image. I'll back out just a little bit. And this satellite image is less than 15 minutes old. and you can see the weather systems around the country. We can add in goes west, and we can also add in the Japanese satellite Himawari data set. But I'm going to do one other thing, and I'm going to issue a big geospatial message, but it doesn't have to be this big. It can obviously be on the street corner or a particular building or whatever, but I'm going to issue a freehand geospatial message. Excuse me. And I'm going to type in a message saying, hello, TFRSAC. We need air support in this huge area in Colorado. Of course, it wouldn't be that huge. It would be very precise and detailed. But those of you that are collaborating in real time should see a green polygon now over Colorado. And you can click on that polygon. Once you click on it, you see the message. Hello, TFRSAC, we need air support right here. This could be, we're going to gather our team together here. We're going to be staged over here. We're going to fly drones here. We're going to be sharing the live coordinates of drones that are flying. And then that could be coming in as a service to GeoCollaborate, so it's sharing out across multiple platforms this information. So I did want to mention, I mentioned in my talk, a couple other agencies are using GeoCollaborate. NOAA is using it in their National Water Center, and they're using it to have live exercises now with states around the country on inundation modeling and flood modeling to deliver NOAA data geospatially into the operation centers for these states. The NOAA Hurricane Research Division is using GeoCollaborate. They're going to be putting it on the Hurricane Hunter aircraft so they can share data between the aircraft and also between the scientists in the aircraft and scientists on the ground, so they can get better eyes on areas of the hurricane that might be rapidly intensifying. So I'm going to take a pause there just to see if there's anyone that's you know, on the Teams meeting here who has any questions, or if anybody has any questions that I might be able to answer.
Let me jump in there, Dave. I've been watching the I/O, and there's a number of questions that are directed your way.
Sure.
Let's see. Have you considered pushing out more of the IAP content? I'm not sure what that is. Besides fire perimeter, out in the rest services for situational awareness.
Can you repeat that, Everett? Sorry, I missed you there for a second.
Have you considered pushing out more of the IAP? That would be incident. I'm not sure. Besides fire perimeter, out in the rest services for situational awareness.
Yes. So here, that's a great question. So here's the way GeoCollaborate works. It can consume any service. So any data services that are being set up, perhaps by the Geospatial Intelligence Center, or you know, the Forest Service, or states, or private sector organizations, all we need to do is get the link for that REST service, and GeoCollaborate will share it in real time. So Storm Center is not reserving any data. We're taking those trusted sources and sharing those out in real time.
Thanks for that. Okay, here's another one. Why isn't the Enterprise Geospatial Platform, which is under the Forest Service and the other land management agencies, why isn't the Enterprise Geospatial Platform using GeoCollaborate?
So because we're phase 3 SBIR, they can. Any federal agency can start to engage with GeoCollaborate, like NOAA has. We have 3 contracts with NOAA. DHS, we have a contract with DHS now, and the U.S. Census Bureau issued us a contract and are looking for long-term applications with GeoCollaborate to help make the census more accurate, connecting with people in the field. So any agency can do it. We just haven't been engaged quite yet. So I'm hoping, that's what I'm hoping, these, you know, TFRSAC presentations are for, to get that awareness out so we can begin this important work of getting this data shared out in real time.
Yeah, and the first time I saw this, I realized, how useful this would be for HADR type missions, human assistance and disaster response, where time is of the essence.
Yes.
So let's see, here's another question. What service architecture is behind GeoCollaborate? For example, is it cloud-based with elasticity baked in?
Yes, great question. This is all running in AWS currently. We can run in any cloud, and it can run in any classified network behind the firewalls if you want to have a more controlled sharing environment. And it is scalable, so we typically can collaborate with 2 or 3 people or 10,000 people.
Let's see. Just want to note that AirNow data did show up in my browser when Dave clicked it on. Okay.
Yeah. So that's great. I love that feedback because the way GeoCollaborate works, it's based on bandwidth, right? So since I'm actually sharing and issuing commands from my system that I'm also have my camera on and using all my bandwidth, my command may not have made it to the AirNow system, but it made it to the cloud, and that's why other people got it. So you can get that often when the leader shares a data set. Many other followers could get the data before the leader even sees it.
Okay, next question, how fine can the resolution for the GeoCollaborate be? And that's probably dependent on the source data.
That's right. That's right. Whatever the source data is, so we can zoom down to, and I'll just do this live while we're looking at the satellite data. I'll turn off the GOES image, and I'll zoom down here into into Southern California, and you can see the map will start to resolve. And you'll see it's just like a Google Earth type of capability. So we could actually issue geospatial messages for individual plots of land, identifying individual areas for targeting for airdrops or things like that. So it can get as high res as the source data is available.
Okay, let's see. Follow up for Dave. Is there documentation on how services are consumed? Serving entities would want to know that load is directed to them.
Yes, that's exactly how GeoCollaborate works. So the serving entities, and that really plays into the trust factor of the data that we're delivering through GeoCollaborate. Essentially, we're instructing all of the collaborators where to go to get the data. And so those who are serving it need to have the capability of serving it. I mean, typically collaboration sessions are between 10 and 50 people, so it's usually no problem. But GeoCollaborate is scalable and could be deployed in a national emergency to have millions connect to it. So those servers would have to be able to, provide that robustness. So if they were in the cloud, they could scale as well. And that's the benefits of having data served from the cloud when you have a collaborative environment like this.
Is there a plan to display aircraft and ground vehicle tracking data?
Yes. Thanks for that question. Don't know who asked it, but we're currently involved with NOAA right now, and they are, we haven't received the task order yet. It's coming for us to do real-time processing of the NOAA aircraft and turn it into a service. The specs are it has to update within every second. So we'll be able to track from a hurricane perspective the planes flying into the storm, along with satellite imagery, radar data, and all that stuff. And their hope is that they could also share that data with the Air Force because they also fly through hurricanes in their C-130s, and they don't coordinate too much currently.
Okay, let's see. The next one is there any way the geospatial message system alerts the end clients without them having to click on the polygon to see what the message is?
Yeah, so so the reason why GeoCollaborate has such an easy user interface, and it took us 6 years to make it this easy. We only put functionality into GeoCollaborate when a customer asks for it. So if a customer asked for that, we would put it into GeoCollaborate.
And this is sort of a kudo here, and this is so much more, all in caps, than Google Earth, the architecture alone to make it happen. So that's a kind kudo there, and I think very appropriate.
Well, I appreciate that, and just a quick response to that. We developed GeoCollaborate under SBIR, as I mentioned. The first thing that we did in our you have to show a prototype in phase 1 of SBIR, is we actually did cross-product collaboration. So we had created a Google Earth real-time collaborative environment, but federal agencies came back and said the way that worked and them installing software on their platform, it wasn't going to work. And so that's why we did it web-based. But we actually designed GeoCollaborate to be integrated into any mapping platform. So ultimately, we can make any mapping platform collaborative by integrating GeoCollaborate into it.
Right. Yeah, that's the beauty of it. Let's see. Is there any ability to serve data from outside of the U.S. or restrictions to use of GeoCollaborate for regions outside the U.S.?
No, there are no restrictions for using GeoCollaborate outside of the U.S. As a matter of fact, we did receive a sole source contract from another country that has, is allies, has treaties with the U.S. So they actually honored our sole source status with the U.S. federal government and issued us a contract. As far as data sharing, any service that's set up, international or domestic, can be shared. You just want to make sure that the data can be shared in a robust environment if you're planning on collaborating with a bunch of people.
Right. Architecture in the cloud, is it built on the ArcGIS Enterprise?
No, it's built on Esri's JavaScript capability. Their JavaScript, we're migrating right now to JavaScript 4.x, but it just consumes the OGC compliant services. We can integrate it into, like I mentioned, any mapping platform. If Esri wanted to do it, we could integrate it into ArcGIS Online and make ArcGIS Online collaborative to hundreds of thousands of customers. I've had some of those discussions a long time ago, but didn't quite pan out. But it can integrate into any environment.
Let's see. This is regard to a prior question. I think the immediately prior question, using versus serving outside the U.S. likely different. It's all about where the infrastructure sits.
And, one of the things that we've thought about is how, you only need a URL and the ability to turn GeoCollaborate on with a switch. Of course, everything could be password protected, it could be encrypted and, things like that. But if you want to easily collaborate with people and improve situational awareness, flooding, save lives, help with humanitarian response, respond to wildfires, GeoCollaborate was designed specifically to enable easy connection and easy collaboration so people can join into this session. You don't have to download an app, you don't have to register for this or that or whatever. So and that's where we've seen a lot of very positive feedback.
And I'm actually going to skip a question here and come back to it because this one is sort of relative to what you just said there. Are there plans for allowing data export and then in parentheses like fire perimeters?
So here's the great thing about the entire data sharing environment. If we are consuming data, that means that there already is a REST service available, or a KML or a CSV file, or all sorts of web map tiles and things like that. So if someone wants to get that data directly, because the followers cannot see where the data is coming from, the followers cannot download and save the data. This is very good because it protects any other agencies or organizations from FOIA requests. You're just using the data for situational awareness and decision making. But we can always make that connection to the data service. If it's an open and available data service, then we can provide that to you and let you know where that data service is coming from. But things like fire perimeters, I mean, Sean talked about it in his first talk. They're setting up an open geospatial portal, which has a bunch of data that you can take and put into your own mapping applications. GeoCollaborate is about immediate situational awareness, sharing data, briefings, and delivering data to people who may not know where it's coming from or could find it valuable, and they may not be technical experts. They just want to use the data for decision making.
Yeah, and I wanted to add on to that. There are some data sets that are sensitive in terms of actually providing that data to. So having it sort of hidden behind a black curtain there, but still being able to see the data, I think is very valuable in itself. And yeah, there's liability that goes along with some of this data. So
sure, yeah, DHS loves that capability.
So I'll back up one. Is the U.S. military using or considering GeoCollaborate?
That's a great question. We have had some attempts to respond to some RFIs that the DoD has had. We never hear anything back, so we're unsure. We don't have any contracts with any DoD organizations, but we consistently hear that their challenge is not being able to share data.
Have you had any engagement with NGA at all?
Yes, we were invited to present to a group at NGA who is now actively searching within NGA to their different programs for needs assessment.
Just a second, Dave. I had to close my door.
Sure.
So here's a nice comment. Seems like a Zoom meeting for GIS, only way more significant than Zoom. So that was just a comment.
Thank you. Yeah.
And here's one on performance and capability on mobile devices. What is the capability and performance on phones and tablets and things like that?
It works. We designed it to work in low bandwidth environments. So if you're connected with a mobile device and you lose your bandwidth, once the data will remain on your device, the data that you've received, and once you connect back into the network, and it doesn't have to be the same network, can be any network. All the data that the leader has shared will load back into your device. So it works. We have ideas where we want to improve performance. Just how sort of like user interface type of stuff to make it much more friendly for mobile devices. But the data does deliver to the device. You can interact with the data. And now we just want, to get more people to use it so we can have real interactivity and say, okay, what do you need?
Okay, there was one more question, I think. Is there documentation on how services are consumed? Serving entities would want to know. Oh, I think I already covered that one.
Yep, REST service, or you have an API, or you're serving web map tiles, things like that. And we could just do testing. It's going to work or it's not, and then we can analyze it and find out why it's not.
So clearly, from the number of questions you got, Dave, there was a lot of interest in this capability, and I'm glad to see that. I'm going to suggest that you and I take a 5-minute break here, unless
Sure.
you want to hang on here. If there's, I won't be able to watch the I/O for a second here because I got to check my email.
No worries at all. I mean, I can hang out here for 5 minutes. If anybody has any questions, they can, chime in.
Anyone on the Teams session have questions for Dave?
Hey, Dave, this is John Melton from NASA Ames. I just want to say completely awesome what you've shown here. Thank you so much for sharing it.
Oh, thank you, John. I appreciate that. And this is NASA SBIR. So we're really hoping that we can work more with NASA to put more of that data to work.
Always nice to see a good use of the taxpayer dollars. Absolutely.
Thank you very much. I'm just going to play a little bit and get a couple of other data sets and display them. The National Weather Service issues watches, warnings, and advisories. And I'm turning on a layer right now that shows all the latest. This is updated every minute from the National Weather Service's IDP system, their information dissemination portal. And you can interact, those of you that are following in real time on the web map can interact and click on those advisories to see what they are. So it's, somebody mentioned it's kind of like Zoom for GIS. It really is. I've heard people say it's like Google Docs for GIS. We really have seen a lot of benefits in testing data services and data sets that people want to collect and offer, and we can do that in this real-time collaborative environment. So what we're really excited about is how this accelerates the transition of research to operations. So we are really closing that gap to the valley of death, as it's called, because we can take prototype products and put them in front of operational decision makers very quickly. Those operational decision makers aren't going to pull punches. They'll tell you if they like it. If they don't, they'll ask some questions, and you can go back and rework those products and then deliver to them again at a future time, so they can give you some evaluation. And one of the things that we're building into GeoCollaborate now, it's not ready yet, but it's a way to give feedback for individual data layers. So if somebody has a data layer we're testing, they can answer questions and provide feedback, and then we can give that back to the data provider so they can improve the quality or whatever their metadata is showing, or things like that. So we're really excited about that capability.
Hey, Dave, as a former Midwesterner, I got a feature request. Any chance for that cicada emergence layer?
Yeah, I could take a picture out of my backyard.
Oh,
yeah.
Oh, that's
yeah.
wonderful.
I'm located just north of Annapolis in Maryland.
Oh, okay, yeah.
And so,
so are you hearing them yet?
South of me, just north, just a little bit away from the Naval Academy, they're coming up by the thousands.
Awesome.
Probably the millions. Yeah, they have red eyes, but it's pretty awesome.
I want to remind everybody that we'll be off a break in about 2 minutes at 9:45 a.m. West Coast time, 12:45 p.m. East Coast time.
Thank you,
And Vince, you're going to handle the next block here?
Yeah, I'll be emceeing the next block. Thanks.
Okay.
I'm going to call it quits here, Everett. I'll be still connected, but I'm just going to turn my camera and mic off. I really appreciate the feedback and all that stuff from everybody that was participating. And all you have to do is just close your browser, and that ends the collaboration session. This particular instance is one that we use for NOAA to test fire and smoke products. So it'll move around a lot and display data and all that stuff. And fairly shortly, it'll probably be password protected. But I really appreciate everybody's feedback.
So are you working with Tom Rankovens and Davida Street and folks like that at NOAA, or?
So Tom is at NESDIS. We're working specifically with the JPSS program, the Joint Polar Satellite System, in their fire and smoke and river ice and flooding initiatives, and we've expanded it a little bit into the tropical and hurricane initiatives. So I know Tom very well, but we don't work directly with him. But if you would, mention some of the stuff that you're seeing here and all that stuff, could motivate him to maybe want to work with us more.
Okay, great. Thanks, Dave.
Thank you.
I guess we'll get queued up for John here. Yeah,
Great.
thanks again, Dave. That was
And
great.
I'll stop sharing my screen. Apologies, I still am here. Okay, there we go. Thank you.
John Green, are you there?
I'm here, and now maybe you can hear me.
Okay, well, we'll give it about a minute or so, and then I'll do a,
There you are.
I'll read your
Hi.
bio, and then we'll be ready to start shortly.
You feel free to make up stuff when you read my bio.
Don't give me that option.
Feel free to improvise.
So just a reminder to the block 5 speakers. It looks like everyone has a 15-minute block except for slot number 5, which has 20 minutes. So please keep an eye on your time. Try to keep it within limits. We're trying to run a tight ship here today, and with apologies to folks.
All right, thanks. I think we're ready to start up again in session 5 or block number 5. And we're going to start out with a presentation by John Green. John is a biomass co-owner and founder. He's worked in the airborne imaging business for over 20 years as a product engineer and business development lead, mostly for Argonne ST, which was formerly Daedalus Enterprises, which obviously, if people remember the airborne program, Daedalus Enterprises built a number of systems worldwide, airborne systems, the Daedalus scanner systems, and built a number of data systems for NASA as well. He has been involved in the development and operation of a number of those instruments in use throughout the world, including the MODIS Airborne Simulator operated by NASA, and the MIVIS hyperspectral sensor operated by CNR in Italy, the Large Area Fast Spectrometer operated by the U.S. Marine Corps, and the Airborne Multispectral Scanner operated by the U.S. DoD. Since starting Ziomass, John has been the principal investigator in several innovative research programs, including the NASA SBIR development, Small Business Innovative Research grant proposal. Airborne, within that program, the Airborne Wide Area Imager for wildfire mapping and detection. Also involved in the Navy SBIR program, real-time spectral band optimization for hyperspectral cameras. And John is going to present us the current efforts on the 3-band detector, IR detector for CubeSats and UAS, also known as T-Bird. So John, take it away. And as Everett said, 15 minutes.
15 minutes starting now or starting when you started?
Starting now.
All right. Well, first off, I want to thank Vince and Everett and Anna at NARI. This is, boy, I was going to count how many TFRSACs I've done, and I didn't get a chance. I've done quite a few of them. But the group that you guys have put together is just really phenomenal. I learn a lot, and I get to meet a lot of interesting people, and I think you all have really produced some tremendous results in putting people together. So again, thanks, Vince, and thanks, Everett. Next slide, please. Brief outline, tell them what you're going to tell them, right? I started working at Daedalus Enterprises. Vince mentioned Daedalus in around 1988. And I mentioned that partly to let you all know who I am, but partly just to kind of flow into the fire mapping and fire detection part of what I did at Daedalus. At Daedalus, we built airborne remote sensing sensors, airborne remote sensing instruments. And delivered them and operated them all over the world for a wide variety of applications. And so I've done a lot of things, not just fire, but since we're talking about fire, and for the last 10 years or so, I've done mostly work developing fire sensors. But anyway, it starts out in 1988. When I started at Daedalus, coincidentally, in 1988, we had the Yellowstone National Park fires that burned almost 800,000 acres. That led to a couple of development efforts, including a Firefly system at JPL that ended up being used by the U.S. Forest Service. Daedalus built the sensor head for that system. The next thing we did was called a wildfire spectrometer that then became the MODIS airborne simulator, and then the MODIS master simulator. And a lot of these things are still flying. I think master flew just recently. One of the dataless sensors, one of the first TFRSACs I went to, Vince was flying a modified dataless airborne thematic mapper in an Icona and mapping fires while we were doing the TFRSAC. So anyway, that's just a little of the history. Some of the dataless sensors I worked on flew in the ER2, and I mentioned that because we are hoping to get the T-Bird into maybe the ER2, maybe something similar, but a high altitude aircraft. And just so you know, for those of you who may not know, the ER2 flies at around 70,000 feet. That's above 95% of the Earth's atmosphere, very close to outer space. And of course, where we're going here is T-Bird is designed to go into a CubeSat. So I'm gonna tell you a little bit about some of the development systems that we've done, including the wide area imager, the thermal mapping airborne simulator, and then T-Bird. The T-Bird concept, what we're doing right now, we're near the end of the phase 2. Phase 2 is going to produce a TRL. There's a typo. That should say TRL-7 airborne prototype. In the phase 2 option, what we call phase 2E or extension, will harden that airborne sensor and further develop it and prepare it to launch in a CubeSat. Depending on what kind of funding we find in the phase 2E, we may be able to afford to launch. We'll definitely build the CubeSat ready sensor, and hopefully we'll actually put one in space in the phase 2 extension. And then in the phase 3, hopefully, there's 24 of them in space. Now, just because I mentioned TRL-7, I have a note to myself to tell people what TRL-7 means. The definition is basically a system prototype demonstration in an operational environment, all key functionality available and demonstrated and tested, well integrated with operational hardware, software systems, demonstrating operational feasibility, most software bugs removed, limited documentation available. So TRL-7 is basically a demonstrator. In TRL-8, you're operational. In TRL-9, I think, is mission proven or something like that. And again, just to emphasize, in the phase 2, so the sensor I'm building right now, the operational environment is airborne, not space. So we're going to get into an airplane here probably within the next 6 months or so, and then as we move forward, we'll put this thing in space. Next slide, please. This is just the about Ziomass. I'm not going to read it to you. Pretty picture, a little bit of fire imagery, and the hyperspectral imager we made for the U.S. Navy. We're a very small group. There's 3 or 4 of us that are actually working in the company right now and hoping to do big things. We think we're doing pretty good. Next slide, please. A little more background. The highlights on this, I tend to compare, I use MODIS and Aster as comparisons. And there are other instruments out there, but people are aware of these and they make a pretty good comparison. When I started doing this, I said, well, okay, or NASA asked me, could you put one of these things in space? I said, what would that look like? Well, I think we'd put it in, why don't I just model this after MODIS and Aster? I don't know a lot about orbits, so I just used these orbits. MODIS has 36 bands where T-Bird has 3. MODIS has a 1 kilometer resolution in the thermal, where T-Bird will have 150 meter resolution. Aster, for reference, has a 90 meter resolution. And next slide, please. I'm going to start going a little faster because I tended to ramble there at the start. The wide area imager, this is the first step stair system that Ziomass built. by comparison, the wide area imager has a 300 microradian spatial resolution, and T-Bird has a 213 microradian, so T-Bird is higher resolution. The WAY had a 90-degree field of view, and T-Bird has 110. The big thing is the WAY weighed, sorry, the wide area imager weighed about 80 pounds, where the T-Bird will weigh approximately 12 pounds. Next slide, please. I included several examples of wide area imager imagery, partly just to show off the, we think it's pretty high quality imagery, and partly to help explain how the step stare optical system works. Next slide, please. So the image you're seeing here is comprised of about 40 individual frames. The T-Bird will collect 3 bands in each frame. We take a picture. There's about 8 frames across and maybe 5 along track in this. This is just one piece of a total flight line, which might run. Some of these flight lines are 20 or 30 miles long. So you take an image. There's a cross-track scanning. It's a scanner that rotates, stops, stabilizes, and you take another image, and that continues across the track. In this case, 8 frames across. The images are collected, tagged with metadata, including position and orientation, and are automatically processed by the onboard orthorectification processor using a high-resolution DEM. What we've shown here is the real-time product. There's no further mosaicing or blending. Let's go to the next slide. There's just a couple of more examples of the imagery we collected. These are 2-foot pixels. This is a job we did for the Metropolitan Sewer District in Jefferson County. And they're mostly interested in groundwater flows. So you can see examples here where you have warm water flowing into a spring from what's an industrial facility up at the upper right of that corner. You can just see a little peek of it up in the. So anyway, next slide, please. Again, just pretty pictures. It's interesting that thermal imagery is very useful for fire, but on the opposite end of the spectrum, it's also very useful for water. Next slide, please. TMAS, I mentioned TMAS, that was the second step stare system we built, and there's some of the specs there. I'm gonna go a little quicker, so next slide, please. I like to put up these atmospheric charts and overlay the spectral bands. So these are the spectral bands in TMAS. Next slide. And we finally, one more. That's the TMAS going into the airborne mount. Next slide. And finally, we get to T-Bird. Go ahead. That's just some contact information and administrative stuff. The T-Bird overview. Again, I don't want to read you all these slides. I'll emphasize that 4th paragraph. We're building a flight-ready TRL-7 prototype right now, and in the phase 2 extension, we'll build a spaceborne prototype. Next slide, please. So we mentioned the step stare a few times. The step stare system basically solves the problem of having to choose between high spatial resolution and a wide field of view. I'll also mention here forward motion compensation. I think forward motion compensation is important. When you open the shutter and the spacecraft or aircraft is moving, your image smears. So we've developed a forward motion compensation mechanism. And I'll also mention the step stare system can accommodate higher scan rates. That allows us to use basically the same system, the same basic design for a space-based system in various orbits, as well as an airborne system, again at various altitudes and speeds. Next slide, please. There's a CAD drawing of the current design and a pretty picture of some fire we collected over in Boise a few years ago. A few specs here. Again, one of the big things is the sensor head weighs approximately 12 pounds. Next slide, please. The T-Bird bands out, and what I want to mention here is there's a tremendous amount of flexibility in this design. across the range from 3 micrometers to 12 micrometers. The band edges are defined by bandpass filters that sit right in front of the camera, but the camera sits in a port that has a relatively wide spectral range. So we can put those bands just about anywhere we want within that range relatively simply. And next, please. Okay, that's a lot of information, and again, not going to read you everything, but it gives you a few highlights. I will point out the, again, we're designing for a certain orbit, but we're quite flexible. And so we're looking at other orbits. And that's important when we talk about revisit rates. Next slide, please. As we're looking at this, I'm starting to learn more and more about orbits. So what we've shown is the CubeSat version with 150 meter GSD, and you got operating altitudes and speeds there. There are other orbits. For example, we can drop this down to something like 400 kilometers instead of the 700 or so, and not quite double the resolution, but we come close to doubling the resolution. So again, this just shows we'll be putting an instrument in a CubeSat. We'll also have a second instrument that's flying in some aircraft, so we can do overflights and coordinated research. Next slide, please. Block diagram, again, there's lots of information there. I'm not going to read it all to you, and I'm down to 1.5 minutes. But this is a good illustration of the features that are built into the system. We're roughly divided into an acquisition and control unit and an image processing unit that includes detection, classification, orthorectification, and compression. Next, please. This is a picture of the user interface in the lab looking at a resolution target. Next, please. This is a test of a resolution target showing that we've achieved the resolution that we expected. Next, please. Pretty pictures of the phase 2 prototype that's coming together. These were taken a couple of weeks ago. This is it has been bolted together partly. We're almost ready to start testing the deliverable unit. The results you've seen have been from a laboratory brass board that we put together. Next, please. There's the sensor head in the CubeSat mechanical environment or envelope. So we have a 6U cube. We fill roughly half of it with the sensor head. The rest of the space will go for spacecraft, ancillary equipment like reaction wheels and power supplies, batteries. Next slide, please. Just another shot of the same thing. And next. Program structure, again, I'm not going to read it all to you. I'll jump down to, we're in the phase 2. We have a phase 2 option to extend, which offers up to $375K in matching funds. There's some dates there. I'll tell you, we are in the process of negotiating an extension, and these dates are going to get pushed out by 3 to 6 months. And next, please. I think we're coming up on the last one. Yep. I believe that's the last one. That's the quad chart. We produce quad charts on all these projects, and just a little bit of basic information about the system. There's my contact information. Please feel free to call or email. And that's the end. I will again thank Vince and Everett and Anna for setting this up. It's been a great TFRSAC so far.
Thanks, John. Very concise, but nice and short and quick presentation on the thermal detector for CubeSat and UAS. And I know that you'll be receiving a lot of queries from the community, probably through IO chat, but I would like to point out that some of the interest in lighter than air platforms may be coming your way for instrumentation demonstration missions on those LTA platforms as surrogates for longer endurance CubeSat type missions. So I think the interest from the community is going to be rapidly climbing on your recent instrumentation developments going forward in your SBIR process. So stay tuned for those contacts and some of the presentations later today on CubeSat approaches, and as well as the LTA interest in developing demonstration missions with new sensor capabilities on those types of platforms for supporting wildfire information. There are 2 queries for John Green in the IO. So I'll let those run till the end of the session, and we will pose those to you in the closeout. But I encourage people, if you have questions for John related to his presentation or the sensor, or need to contact him, please put your request in the IO, and we'll get those forwarded to John. Thank you.
Thanks again.
So our next speaker, if she's ready, is Dr. Mary Ellen Miller. Excuse me. Dr. Miller is a research engineer at Michigan Tech Research Institute, MTRI, and she has extensive experience in modeling fire effects and working with land management stakeholders create fire decision tools for land management. She was a investigator under the funded investigator under the NASA Applied Science Program Wildfire Element that we managed a few years ago. And Mary Ellen continues to stay involved in the fires community and is a great supporter of the wildfire observation capabilities. And with that, I'll let Mary Ann start her presentation. Mary Ellen, excuse me.
Thank you, Vince. I am very fortunate to be working with a very large and diverse team working to apply remote sensing to pre, post, and active fire management and science. And this presentation is fast. Also, last summer, I had the opportunity to work remotely with the National Emergency Response Teams, and it was a wonderful experience. I think more work should be done to integrate researchers and responders. And to further that goal this spring, I practiced walking really fast and managed to secure a red card. Next slide, please. So a pre-fire concern of land and water managers is protecting critical water supplies from the impacts of wildfire. Peak flow rates can increase up to 100 times, and sediment delivery to streams can increase by 1,000. So managers really want to quantify the benefits of fuel reduction treatments in order to both justify their costs as well as prioritize their spatial application in order to maximize the benefit to protect resources such as water supplies. Next, please. So a few years ago, I was privileged to work with the McCollum Watershed Avoided Cost Analysis Working Group. It was a group of local stakeholders, including the Forest Service and the Nature Conservancy, that came together to protect their watershed, the McCollum Basin, which is in the Sierra Mountains of Central California, and it's very beautiful. It's similar to Yosemite. And the team decided to use 3 different models. FlamMap was run by the Forest Service to predict fire severity. FSIM was used to predict fire probability, and I ran Web Watershed to predict erosion. So we predicted hill slope scale erosion for 4 different cases. Background rates, just current forested conditions. After a fire, assuming the current fuel loadings. And that map was used by the working group to plan fuels treatments. And we actually predicted the effects of the fuel treatments on the watershed. And then the last week, we reran we created a prediction of post-fire erosion following the treatments. Next slide. And here are samples of our results. The first image is predicted first-year post-fire hill slope erosion, assuming that no fuels treatments were in place. And the second map, you can see that the colors are lighter. This was after the fuels treatments, and we showed a reduction in potential erosion. So we actually combined the 4 different maps of erosion predictions, along with the spatial predictions of burn probability, to predict that regular fuels treatments about once every 25 years in the lower portion of the basin would reduce overall long-term erosion rates by about 19%. Next slide. So one of the big challenges, though, in planning fuel reduction treatments to protect your water supplies is actually forecasting burn severity before a fire occurs. Shortly after the McCollum project ended, the Butte fire burned the lower portion of the watershed, which gave us an opportunity to validate the flame map derived predictions. And it turned out the flame map wasn't any better than guessing. So we were sad, but we found that using a combination of flame map and terrain and topography, we were able to use random forests to create a better prediction. Next slide. So the Forest Service asked us to create a tool, an online tool to help land managers forecast burn severity. And we were using, we used the machine learning tool Random Forest, along with Flame Map, the fire behavior modeling, land fire data, FireSev data, which consists of a lot of topography and NDVI, and we also added soil metrics. And so the user selects an area, and the 10 to 12 nearest fires are selected for training data, and the user enters an email address, and within a few hours, Random Forest is run, and you're provided with a burn severity prediction. Our accuracies are a lot higher than Flame Map alone, but we would like to improve this tool using some of the new NASA products such as EcoStress or fuel structure products from JEDI or ISAT. Next slide, please. So switching gear, another new thermal sensor that has great potential for fire is EcoStress, which is on the International Space Station. And EcoStress relies on multiple instruments, models, and data sets to perform energy balance modeling in order to derive evapotranspiration and evaporative stress index. And our example here is from the Williams Flat Fire. And as you can see, right before the fire occurred, water stress was very great. Next slide. So we're very interested in using EcoStress data to see if it can help map fire danger and improve estimates of live and dead fuel moisture for both fire behavior and emissions modeling. And of course, I'm very interested to see if it could help the burn prediction tool. Next slide. So to test our theory, first we downloaded EcoStress evaporative stress index data and RAWS weather station data for 10 sites in Idaho and Washington, basically the area surrounding the Williams Flat Fire, to look for correlations between ESI and 1,000-hour fuel moistures. And we found the Spearman correlation coefficients ranged from 0.38 to 0.85 for our 10 sites. And the ESI data is correlated to the fuel moistures, but the relationship is stronger for individual stations. Next slide. So next we looked at live fuel moistures from the National Fuel Moisture Database, and we compared this data with ESI. And we're using the NASA Appears tool to get the data. And our initial results showed only a slight correlation. So additional work is needed to gather a greater range of data. And one of the issues we're facing is the fuel moisture databases and the RAWS weather stations are often located near roads. So we think we can improve this analysis if we use homogeneous patches of pixels. So next slide. So one of the driving factors is we are looking to improve fuel moisture for the consume model, which is used to predict wildfire emissions. And we do have, MTRI has the WIFIS model, which is an easy to use interface for consume. Next slide. So for now, we're going to switch to post-fire. We are always looking for ways to improve the speed and accuracy of our rapid response erosion database, which allows users to upload a real or a forecasted burn severity map for fuels planning. And in seconds, download all the spatial model inputs that you need to predict runoff and erosion from the process-based hydrology model WEP watershed. We typically use burn severity maps that have been derived from Landsat or Sentinel, but time is critical You need to get them out fast, as the first major storm can result in life-threatening floods and debris flows. And some exciting news about RED: it was transferred to our operational partners, the Forest Service, this spring. Next slide. So to make modeling even easier, we've developed QApp, which is an open source QGIS spatial interface for WAP watershed. And you can use QApp in conjunction with RED. The output from the RED model is the input to QApp. Next slide. And this last year, I worked with the National Park Service, their teams, to evaluate values at risk on recent wildfires, including the Mojave Dome, Pine Gulch, and Cameron Peak. And this example here is looking at a value at risk at Bridge in Rocky Mountain National Park after the Cameron Peak fire. Next slide. Another really exciting project with the Park Service was the Mill Creek reevaluation. In 2018, the Carr Fire burned the Whiskeytown recreational area, and it actually burned a lot of the housing in the area, causing a little bit of a crunch. And another blow was the burned area emergency response team at the time recommended vacating the Tenant House, which is a historic house at the base of Mill Creek. And they really needed housing. So 2 years later, the Park Service asked the Department of Interior Bear team to re-examine conditions. And a field crew went out and took samples of vegetation cover and vegetation type. And we used modeling, earth, and field observations to help the National Park Service understand vegetation and hydrological recovery. And we found that during the summer months, it is safe to rehabilitate the house, especially during the summertime. And I was really thinking remote sensing is currently underutilized for studying and understanding post-fire recovery. And every time I talk to bear teams, they're always very surprised to learn about peers. So next slide. So another exciting work we're doing is we have partnered with the University of Wisconsin Bridge team, and they are actually working with NOAA to create rapid estimates of burn severity using NDVI data from VIIRS. So there's a higher temporal resolution, but lower spatial. Next slide, please. So we use both RED and QApp to predict post-fire erosion and runoff for the Williams Flat Fire using both the burn severity maps derived from land fire and from the new bridge product. And the bridge product was created without any a priori knowledge of the Landsat map. And we discovered our post-fire predictions only varied by about 10%, meaning the higher temporal resolution bridge product does have potential to provide an early warning. Next slide. So we were very excited about our initial results from the Williams Fire, and we decided to test the 2018 Carr Fire. However, the soil burn severity map and DNDVI map did not align very well. So more work is needed to improve the bridge product, and I decided our burn severity predictor tool could work well here. We would like to test the machine learning algorithm to forecast burn severity from bridge and to predict raw DNBR values to create the burn severity maps. And this could be a way to have a faster prediction of burn severity as the bear team goes out and collects field observations to create the field verified soil burn severity map. And next slide. And so on this slide, I just have some of the links to our databases and tools. And thank you very much for your time.
Thanks, Mary Ellen. And again, the questions can be posed to the conference.io site, and we'll relay those to Mary Ellen at the conclusion of today during the wrap-up discussion or open discussion period, where we'll have all of the presenters hopefully available to speak to questions that have been posed throughout the day in that conference.io. And Everett and I will read off those questions and get the responses from everybody. So again, thank you, Mary Ellen. Cool product, and I know this is a continuation of work you did on your applied sciences, and I applaud it, as we always have in applied sciences, to the work that you've done in supporting both NASA and your U.S. Forest Service partners with operational capabilities. So thanks again. All right, moving to our next speaker. If you can get his slides ready, and then we'll do a quick voice check with Cormac. But our next presenter is Cormac Purcell. He is the program director at Trillium Technologies Australia. So he's calling in from afar and working on a diverse project involving brush fires, oceans, and machine learning. Trillium actually builds public-private partnerships that accelerate interdisciplinary research, and they are best known for the NASA Frontier Development Lab program. And Cormac is going to be talking about the Brushfire Data Quest, the promise of artificial intelligence for brushfire management and defense in Australia and New Zealand. So Cormac, I'll let you take it away. Test your audio.
Thanks very much. Can you hear me okay?
Just fine.
Yep. Sorry, that broke up. Just checking in. Can you hear me?
Yeah, no problem. Just
Okay,
fine.
perfect. Thanks very much. And thanks very much for giving me the opportunity to speak here. It really is a bit of a thrill. So as I said, my name is Cormac Purcell, and I work for Trillium, which is absolutely best known for something called NASA Frontier Development Lab, and I'll speak a little bit about that in a few slides. Next slide, please. So this slide probably needs no introduction to this audience, but by way of motivation, we're looking at the smoke plume from the largest fire recorded in modern history that happened in Australia. In the center of this map is Sydney, where I'm sitting now, and this happened around Christmas time, December 2019, and the smoke stayed with us for around three months. For all of my time, I've never seen something like this at all. And as records go back, the fire here was the single largest fire to burn continuously over any period in any part of the continent. We're told that this was a once in over 100-year event, but we now know that the forecasts predict this to be much more frequent, and almost making this a common fire season by the year 2050. Next slide, please. Australia has quite a unique landscape. We really have a triple whammy when it comes to fires. We have some extreme weather. We're the driest continent on Earth. The topography is quite remote, so it's quite difficult to actually fight those fires. But in particular, the fuel is quite unique. Much of the burnable land is covered with eucalypt forest, and eucalypts have a very unique type of bark that make them almost a weaponized tree. They have evolved to promote fires in the landscape, and you can see here on the middle picture, upper, what we're looking at is bark from a paper bark tree, and this is very oily, resinous bark that is very friable and drops into the landscape, renewing most of the fuel on a 5-year scale. One unique aspect of Australian fires is that we have something called spotting that is very common. This is where the convective currents loft firebrands into the air and seed fires up to 30 kilometers away from the main fire fronts. And these fires can join up and accelerate the spread of a large bushfire in ways that are very stochastic and unpredictable, making them extremely dangerous to firefighters on the ground. The map on the right-hand side is a measurement of the Forest Fire Danger Index, showing how the index has increased, how it's become more dangerous over the period of 1978 to 2017. And that's just a measurement. Our forecast models show that this is going to get significantly worse over the next few decades. Next slide, please. So the question is, we all saw this a year ago, and we wanted to ask a question: how can we support and help the operational firefighters in our job as scientists? Next slide, please. Okay, so at Trillium, we have developed and run something called Frontier Development Labs. Many of you at NASA may have heard of this in one context or another. It started at NASA Ames and has been going since 2015. So Frontier Development Labs is a public-private research partnership between the major space agencies and leaders in commercial artificial intelligence and private space. The ethos is for human good, and we release all of our research under open source licenses so that academics and our business partners can take it forward. Next slide, please. So some of the types of research that have come out of the program in the past have been providing illuminated maps of lunar permanently shadowed regions to support NASA Viper missions. Near real-time stream mapping and water occupancy from orbit using Planet Lab data in a data fusion with LiDAR, and looking at scaling measurements of stellar rotation using machine learning models that scale up to really large numbers of stars detected in the Kepler missions. And this is just an example of what is now over 50 different machine learning workflows. So we said perhaps we could do something similar in Australia. So next slide, please. In 2020, we built a new program inspired by Frontier Development Lab called the Bushfire Data Quest. And we were lucky enough to get some fantastic partners over here. We were supported by the Australian Space Agency, which acted as a node, and which led on to fantastic support by philanthropic organizations, big compute providers, academic institutions, and government institutions. So all scientific and data providers with a great deal of expertise. Next slide, please. All of this was based on scientifically defined challenges that were defined by our community. So we brought the scientific community together and came up with with 3 different challenge areas around fuel assessment, early detection of fires, and fire behavior. And these, when we drilled down further, became 4 different projects with 4 different teams. So we looked to map fuel moisture content in the landscape from orbit, and then do the same thing using similar data for fire risk maps and fire progression models. How we could detect fires better from orbit again at the earliest stages, and then look when fires were burning to see if we could detect signatures of extreme fire behaviors as an early warning. Next slide, please. So just like Frontier Development Labs, what we did was we brought focused teams of experts at PhD and postdoc level into one room, or one virtual room in this case, paired them with AI rock stars, and then provided them with dedicated compute resources, time, and an outer ring of experts to enable them to do the best work of their lives. And it's these 4 different pillars that really allow us to get results that are in just a short amount of time, that are really as good as you would get in a year or of focused research. So next slide, please. So the idea here then is just research challenge, the right research talent, and it's a competitive program. We have acceptance rates of around 11%, which is not dissimilar to Ivy League university levels. The right capital and capacity, and then a really important point is to bring the right data sets and prepare them ahead of time so that the teams can get a running start at the research itself. Next slide, please. Okay, so here are our four teams. Because this was a shorter program, only a 3-week research sprint with a single week full-time at the center, we think they did fantastic work. We'd like to acknowledge, as well as our teams who were located in Australia and New Zealand, we had fantastic support from the Northwest Nazarene University, who, in an asynchronous mode, gave us some data support. So this work took place in the middle of 2020 over the 3-week period. Next slide, please. Okay, so the outcomes. The first team looked at early detection of fires using the Himawari 8 geostationary weather satellite from the Japanese Space Agency. They applied a machine learning super resolution pipeline and image subtraction and stacking from an astronomy perspective to a historic fire around the Canberra region. They found that using the machine learning pipeline to boost the data allowed them to detect the fires earlier and at a higher signal-to-noise ratio than the standard hotspot product, which is very similar to what you're used to in the States. This machine learning workflow is now open source, and the next steps are to scale up and validate on some test fires. Next slide, please. Our other fuel team was looking at measuring live fuel moisture content, which is a great proxy for flammability. However, the current product that's used in Australia is based on the low resolution MODIS data, so a resolution of 500 meters. A new product built on Sentinel-1 plus Sentinel-2 could provide much better insight on the scale of human structures, so i.e. farms and towns. So the team built a suite of machine learning regression models, which were based on ground truth data taken near the Canberra region. So this is just measurements of moisture from fuel that's been gathered and baked in an oven. They were able to prove the concept and get out some realistic looking fuel moisture maps. However, what we found is we've exposed a major data gap in the Australian region. So that absolute calibration requires much more extensive ground measurements. And we're planning now to have a citizen science program that takes those measurements in order to build a much nicer data product. Next slide, please. Our other fuel team looked at taking a new approach to fire spread prediction models. All of our current operational fire spread prediction models are based on empirical fire models in the background, and then are fed with proxy measurements of fuel and weather. The team wanted to learn directly from the data, so they built 2 fully convolutional machine learning fire segmentation models that learn directly from fire history data sets. The models took in weather variables and Sentinel-2 declouded time series and accurately predicted the fire scar extent and played how the fire propagated forward in time. You can see from these little animations on the bottom that the fires learned about features in the landscape, like in the red dotted lines, we have barriers created by rivers, and the fire model learned from that those features in the landscape would prevent a fire from crossing. The next steps are to merge these models with physics models to get the best of both worlds. Potentially very fast modeling framework that can learn from up to the minute data and potentially be very portable, running on very small devices in the fireground itself. Next slide, please. Our final team, we're looking again at the Himawari 8 multi-band weather satellite, and they were searching for signatures of extreme fires in that data set. They used principal component analysis and color ratio analysis to search for signatures of pyrocumulonimbus events before the clouds were visible. So in the little animation on the 3-panel plot on the right-hand side, inside the square green box, what you can see is a very white cloud coming up out of the red-coded haze. And in the bottom three panels on the right-hand side, what you can see is you're starting to see signatures in the multiband data, even before that cloud starts to rise, of an extreme fire behavior. So we think that this could help build an early warning system if applied, but it's quite speculative work still. Okay, next slide, please. So all of this data was, all of this research was done during that short period, and we're hoping to build on it over the next year or so. Because we believe in open science, it's all being published in a report called The Promise of Artificial Intelligence for Bushfire Defense, which places it in context and also outlines the possibilities for the future. One of the very important outcomes, of course, has been the identification of different data gaps that we have in the local area. And this very much aligns with some of our Royal Commission reports that have been feeding into the challenge of managing bushfires over the next few years. And there's a huge effort underway in Australia to identify these gaps and put in systems and data sets that are much more suitable for operational use. Next slide, please. So based on this, we thought that the different projects that we have do fit on a kind of decision line that would help operational firefighters. But in order to validate our results, we recently went out and talked much more closely to firefighting teams operating around the country here. Next slide, please. So in February of 2021, we ran a concurrent design workshop to examine exactly what the user needs are in partnership with the University of New South Wales at, in fact, a satellite design facility called the Australian National Concurrent Design Facility. Next slide, please. So this report put technologists and scientists and in a room with operational firefighters, from people who worked on the fireground all the way up to the incident management team, and asked them what their user needs were and how technology could actually help them. We're in the middle of finalizing a report which lays out current practice on the fireground itself, how incidents are managed, and how current technology and data is used. Next slide, please. And then this is married with exactly how data is used and case studies of all of our national data agencies. For instance, on the right-hand side here, this is how the Digital Earth Australia Hotspots product is developed and used in practice. And we also identify what could happen in the future and how technology could potentially make the greatest impact over the next few years. Next slide, please. So out of this report and out of this consultation with firefighters, a few opportunities have arisen. We have found that the biggest problem that firefighters have on the ground is situational awareness. In Australia, most firefighting is done via a base from trucks. Trucks drive into the landscape, and then firefighters demount from the trucks. Over that time, after they leave their truck, they're almost operating blind. And so we believe that you can get much further with a set of devices which are connected and allow access and reporting back of data, and potentially automating a lot of what the firefighter does. This improves much improved safety and integrated warnings, because situational intelligence, when it's not done properly, costs lives, especially when fires are influenced by weather and very changeable weather, which happens in much parts of Australia. Next slide, please. We've seen an opportunity for much more data to flow up from the fireground. Much of the modeling that's used to support fires, fireground decisions is based on very high-level modeling and satellite data sets. We've really found that we need ground truth, and one example here would be this Kestrel weather meter, which all fire crews carry. Currently, it's just used to check local conditions, but the data itself is not really fed upwards. But it can be critical to inform how a model runs and really to peg a model to reality. We also need to know lots. Sorry, go ahead.
About a minute left. Thank you.
A minute left. That's absolutely fine. Yeah, thanks. Next slide, please. Resource management is a major issue as well. Only 20% of firefighters are deployed to the fireground at any one time, and it really is a wicked problem to try and manage volunteer firefighting availability, food and accommodation, and all of the other consumables that go into fighting a large campaign fire. Next slide, please. And then finally, real-time probabilistic fire suppression models. So current tools are used to predict the path of the fire on about a daily basis. But what if we could run many more ensemble models and make proper recommendations to say, okay, here is where you need to put a fire break. Here is where you need to put some water to put out a fire for the least resources and the most effectiveness. Next slide, please. And finally, all of this needs to be supported by frameworks in which researchers can operationalize their data tools. And one example is a toolkit, an open source toolkit that we just built for the UK Space Agency, running machine learning models and operationalizing them for flooding researchers and people in the field who are dealing with floods. And next slide, please. So we want to run a new FDL in the latter half of the year. So in December, we're looking for probabilistic fire. We'll be looking at probabilistic fire modeling and fire ops tools, and all of the opportunities that we identified in the recent report. And we'd love to hear from you what your opinions are and how firefighting in the US differs and how it could help. And then just go on to the final slide. So if you're interested in contributing to or seeing the concurrent design workshop report, which is coming out soon, please get in touch with me at cormac@trillium.tech. Thank you very much.
Great, thank you, Cormac. And again, these presentations will be available in the Cloud Vault, so you can copy that information on contacting Cormac from his presentation materials that'll be stored there and available after the meeting. With that, I'd like to introduce, and again, thank you, Cormac. I'd like to introduce the next speaker in our series, this block. It's Stan Kubota. Stan Kubota is currently retired. He retired as a Forest Service fixed wing operations specialist out of Region 5 in California here. He is also a current NWCG red card rating of an air tactical group supervisor and helicopter coordinator, an infrared sensor operator, Forest Systems trained, program manager with the Forest Service Firewatch Cobra helicopter program, program manager of the Dynacorp International Forest Service Sherpa aircraft maintenance program, and on and on and on. Worked air base, air tanker base manager, Lhasa National Forest, and originally was a U.S. Forest Service hotshot and smoke jumper. So he comes with a great deal of experience in the aircraft operations component of the U.S. Forest Service, especially in his most recent position as a fixed wing operations specialist. And Stan, you're supposed to relax when you retire and not take on new tasks, but we welcome you to give your presentation. I want you to do a quick sound check and let's see how you sound, and then we'll go from there.
Great, thank you.
Turn on your video, please. Thank you.
Yes, how do you hear me?
Loud and clear, you're good.
Perfect. Okay, and my video's good. Yes, thank you very much for having us and letting me present to this group. We're not as much scientific, but we do collect a lot of data. We do collect data, and this fire integrated program, fire integrated real-time information system that was developed under a concept from a lot of the chiefs in Southern California. What they really wanted was to know where the fire is, how big it is, and where it's going to go. And those were our three main challenges when we first began this program. So what we do is we have two King Air aircraft. This is the 2.0 version. And what we do is we end up launching on incidents that we hear. We are funded by California Office of Emergency Services. So we're not just fire any longer. We do law enforcement missions. We help in search and rescue with our sensors, and we're all risk. Any emergency that we have, even maritime things that come up, incidents, we will respond to. We leave it up to the air tactical group supervisors to make that decision. Every right seat person in the aircraft is a qualified air tactical group supervisor. Go ahead, next slide, please. This is just an example of one of our King Airs. This one happens to be stationed down in Los Alamitos, California. That's the top picture. This is known as Intel 24, which is a 24-hour operation out of Los Alamitos. It's currently on duty now, but only staffed 12 hours. Hopefully, if the program continues, we will be staffing 24 hours down in Los Alamitos, and another King Air, Intel 12, will be staffing 12 hours out of Sacramento, perhaps McClellan, beginning July 1st. On the lower part of the slide is an example of how we operate, and an example of how our airplane is equipped. We have a sensor operator that operates in the back of the aircraft. He operates the gimbal. It is a FLIR 380 HD. And we also have an Overwatch TK9 multispectral sensor underneath the aircraft. We transmit our data beyond line of sight, and that's what's on top is a satellite connected system where we transmit our data as we're flying. Next slide, please. So going back to our goals, we were tasked to get over an incident. Whenever we hear about an incident, however we hear about it, we use right now, Southern California has what they call, LA City has a fusion center, and that fusion center is monitoring all kinds of radios and chat rooms, wherever they can find data on incidents that are starting. And they advise the air attack through a WhatsApp chat that there's something going on in the state of California, and that aircraft will launch, depending on the air attack feels that, and the fusion center feels that there is potential. So currently, we're primarily looking at fires with basically a year-round fire season down in Southern California, but we have flown a couple of search and rescue missions, a couple of maritime missions, and some flood missions. We've had some landslides earlier on in the rainy season of California where we did infrared imagery and video imagery, and collected data and sent it to Interra. Interra is our depositor of information. That's where we deposit it, and it goes out to be modeled. Fires go out to be modeled to the Wi-Fi supercomputer at San Diego State University, and that's where these projections are made, which I'll talk about shortly. Also on those flood responses, the TK9, the Overwatch TK9 is used to collect digital elevation model data pre and post flood. So if we know there are some significant flood prone areas wherever those areas are, we will go out and take models, digital model data from those areas with that Overwatch TK9, and we will preserve those. And then when and if a flood occurs or there's landslides that occur, we can go back and see how they occurred, and that's just data that is available. through Intera. Intera posts our data through EGP, and I'm not absolutely certain on the data produced by San Diego supercomputer other than what the fire modeling is, and we'll speak to that here on the next slide. Next slide, please. So our goal was to deliver this modeling, this fire location and modeling information to remote locations via satellite. In this particular case, once it gets into a satellite system, it gets transmitted off to a server, and it gets posted out through LTE. This is how this one was probably received in LA County, Southern California Fire, where they get it as quick as they can. Our goal, and we'll get over an incident, is to produce a perimeter within 5 minutes of arrival. We also stream our digital video from the FLIR 380 HD as we come towards the fire and all the time until we get over the fire. That video is and will be available through a new fashion this coming fire season. We're working on that, but Jeff Logan at Orange County is the person to get that access for the imagery and data that comes out of WhatsApp. Since we are funded on and by Cal OES, the WhatsApp chats that deliver and send out our data are built upon the different Cal OES regions. So that's how they're divided. If you subscribe to a particular location, say if you were just interested in incidents that are occurring in the Bay Area, then you would subscribe to Region 2 through Jeff Logan, and that would be Region 2 Cal OES. Next slide, please. So this is an example of a fire that was located and a projection model that was put out by the Wi-Fi supercomputer. It uses data that's located in the vicinity, all the data that's accessible, including any weather data that's out there, predicted winds, fuels, if they have any data on the fuels there. And this particular image, you could see the spread potential. The spread potential on this particular incident is taking into account no suppression actions. And you could see the time that it is taking that fire to spread. It's in 30-minute, I believe, minutes on the spread model. In this particular instance, there is no aircraft over the incident. It was just a spot that may have been picked up on a alert wildfire camera and projected from that point. So this comes out pretty quickly before there's even a real solidly known latitude, longitude. There's a kind of a rough one on top, and it says Region 1, where it says the west, the latitude, longitude on top, and it has the particular region. The region is Region 1, which is Southern California, right in that Southern California corner. It's in relation to Cal OES's Region 1. If those that are not familiar, that's what that means. And you can see with that, there are some weather stations out there that are depicted. If there is a perimeter that was built by the aircraft, then it would be shown in black from that point of origin, that detected point of origin. So the original point of origin may not be completely accurate. Once the aircraft gets overhead, it will build the perimeter, and the relocated spread model, the redone, recreated spread model will go from there. Next slide, please. This is an example of a of a incident that occurred in Southern California utilizing a spread model, but it also used the perimeter that we had built prior to the final perimeter in it. And if you notice, one of the things that our projection models do not take into account is a pre-existing fire. There happened to be a fire that had occurred earlier in the year on the lower, where the kind of the straight edge is on the lower lobe of the southwest corner, of the southwest big blob, basically. That's why that straight line is there. The model, we had to adjust the model to demonstrate that that's not going to burn because there was a perimeter there, or an old fire, existing burn that would not carry fire at that time. So that is being done as the fires are being modeled. Information is being brought in to determine that that's why, or that's not gonna, the modeling is being adjusted for that, is what I'm trying to say. So once again, I just kind of maybe skipped over it kind of quickly, but our data gets pushed to Intera. Intera is a company that distributes our data to EGP, and it also sends it to the Fusion Center, and it also sends it to UCSD's Wi-Fi program with their supercomputer, and that's how the modeling gets done. Next slide, please. Okay, so this is this image is a one of our images that you get out of the 380 HD. It's just an infrared midwave, high definition midwave infrared. And as you see, if you notice, there are some dark spots along the line. Those are either burned into or holding suppression efforts. And these images that are coming out of our 380 HD are being broadcast out through our satellite system to be distributed out of a server back to and through an LTE system, of which you can, and I apologize for the side noise. I happen to be doing this outside of a fire station, just because of the meeting that we have to attend to next. And I may not be available for questions at the end because we have another presentation to do. But the other thing about this is that the firefighters on the ground are able to view this through that WhatsApp chat from Jeff Logan. We were sending out a link, but I think there's just going to be a password protected link that will be issued in the near future for incidents. Next slide, please.
And you've got a few seconds to wrap up. Thanks, Dan.
Okay, let's go ahead and play this video. This is just an image that was being transmitted live from a fire close to Carlsbad. I'm not sure if the video will have my voice on it, but this is kind of what we do. We respond to fires. We happen to get to this fire prior to any other responding aircraft.
Inbound. It's a fire amongst structures. Let's go ahead and go infrared. And with the infrared, you can see that there are numerous spot fires, and those spot fires are like palm trees that are on fire, and they are spot fires. So go ahead and zoom in, Matt. There you go. Spot fires throughout the neighborhood. This is very close to the ocean, right off the shore in Carlsbad. Go ahead and zoom back out. And let's go color. You can see the winds were pretty strong, and they're coming out of the south now, pushing that fire kind of parallel to the shore. And one more time, let's go take a look at the spots with your infrared. Get really close in on those. Yeah. So they're out there a long ways. There's pretty strong wind down there, probably 15 knots. There's a palm tree throwing.
Okay, we can move on to the next slide. And this is just the last video I have. It's just for folks that don't understand what high definition IR is. When the people that are engaged on the fire can see the imagery, what they can do is they can see breaks in the line, and that's what this video demonstrates.
That's it, man. Descend to maintain 11,000, 11,000. Right, take 11,000. Hey, call it 3 Hotel Tango.
Second. And of course, my health is the number one priority here. So what Dr. Lee needs, we'll make it happen one way or the other.
Okay. So with that, next slide, please. That's all I have for you today. Thank you very much for your time, and I hope I can join the question and answer session later, but I may not be due to another prior engagement. Thank you very much for your time. Thanks.
Thank you, Stan. And we'll see if there's any questions and add them to the from the Conference.io site. And if there are, we can let you know. And if you're able to answer them and available, fine. If not, they'll be posed and you can answer them at a later time. Thank you.
Thank you.
Okay, I'd like to jump to our next speaker. This was a long session. It was 6 presentations, so it's a little difficult to stay on time, but Ali Adabare is Vice President, Engineering and General Manager, American Aerospace ISR. He manages their UAS division that is an OEM manufacturer of the Air Ranger Group 3 Long Endurance UAS. And he also leads the integration of novel payloads and sensors for prevention of and response to environmental threats and natural disasters. Ali brings over 15 years of product design and development experience and served as co-PI on the NASA SIO demonstration program for UAS operations in the national airspace. And he'll be talking about the beyond visual line of sight UAS type certification process for that Air Ranger platform, along with David Yoel, who's CEO of American Aerospace. With that, I'll let Ali check his
Yeah, I'm here, and thanks. And actually, Dave's going to provide most of the presentation, and I'll be chiming in for a few slides.
Can you hear me?
Yeah, we got you both, so you're free to go.
Very good. Thank you all. Appreciate the opportunity to share information with you about our unmanned aircraft systems. Next slide, please. We'll just quickly review a bit of background, talk about this aircraft and its specifications, talk about our recent NASA SIO demonstration, payload capabilities, our type cert process and timeline for ability to operate this aircraft in the national airspace, projected timeline, and talk about where we have operations underway and pending, and summarize. Next. So currently we're located in 4 places: New Jersey, Pennsylvania, Virginia, and Oregon. We're establishing operation centers in Louisiana and Central California. We'll talk a little bit more about California in a moment. So we have 3 groups. The Airborne Systems Group provides flight services as well as sensor packages. Skyscape Industries is our drone services company. And Ali runs our ISR division, the builders of the Air Ranger unmanned aircraft. Next slide. Next. Ali?
So Hi, this is Lee here. The Air Ranger is a Group 3 UAS. It's designed for commercial missions. It's about 18, a little over 18 feet wide, full wingspan, and about almost 10 feet long. What's nice about it, it's got an endurance of over 18 hours, depending on the configuration. Very high service ceiling. It travels between typically about 50 and 100 knots. And has excessive payload capacity and power available. So we can carry up to 75 pounds from our base aircraft, including fuel and payloads and other peripherals. And we have well over 900 watts of available power to provide. So that way we can carry a bunch of multiple sensors at the same time, complex sensors that smaller vehicles can't carry. It's catapult launched using a pneumatic launcher, and this will show in a video on an upcoming slide here. And we have a variety of communications, including line of sight communications with the tracking antenna, beyond line of sight, and even going to SATCOM and LTE as we're working towards our type certification. We have over half a dozen aircraft currently built and in fleet, and we're building another roughly 4 aircraft per month. Next slide. The big accomplishment we had this spring was completing the NASA System Integration and Operationalization, or SIO program. We were in that program with Bell Helicopter and General Atomics, who were providing proof of concept for their commercial operations. For Bell was below 1,000 feet, for General Atomics above 10,000 feet. And we're in that in-between range where our operations are really typically between 2,000 to 3,000 feet. So we're in that 1,000 to 10,000 space where we're not a huge UAV, but we're also not a small one. And what we were able to prove out in that in the program, as again we'll show a video on the next slide, is the use of detect and avoid components, a pair of Echodyne radars, and a ADS-B in and out transponder from SageTech, and proving our commercial mission with those components on board and a configuration that could move towards type certification. So that it was a successful program in the sense that that we're kind of paving the way as we work to type cert our aircraft. Next slide.
I'll take this one, Ali. So this is the certificate of authorization. We have this green box on the top right. You can see Bakersfield there, just to the in the lower right quadrant of the image. The airspace has a 6,000-foot ceiling. It's about 4,350 square miles. We've been operating out of the Buttonwillow Airport, which is down in this area here in the desert. We currently have a 50-mile range. We've had 5 weeks of operations here in late 20 and early 21. We expect this fall to be in permanent routine operations in California in this location. This is where we conducted our NASA SIO demonstration mission. We've also been working with the Department of Transportation, Pipeline and Hazardous Materials Safety Agency, and the pipeline industry in developing automated threat detection and reporting systems using unmanned aircraft systems. In that center image there, you can see this was a rather complex layout here, but the launcher's in the foreground. You can see the tracking antenna and the trailer in the back. So this is what our ground footprint looks like, and even smaller for remote operations. And our goal is by the end of 22 that we'll be flying true BB loss without chase in the national airspace on a routine basis. Currently, we're using chase aircraft. Next, please. So this is the video. I'd suggest you turn the volume off so we can just talk through it, if you don't mind starting the video. It's just a minute or two.
Since were you folks able to get this to work? It's a YouTube link.
Okay. Well, we'll move on. The thing I'll point out here is that you can see the radars on the aircraft here. So we were flying a full AI-enabled multispectral remote sensing package. We're able to provide real-time reporting from this aircraft across an oil and gas company, but with a full surveillance solution on board and a full sensor package, we were able to demonstrate this capability under the NASA SIO program. Next, please. So just a little bit about our payloads. We have a multispectral mapping system we call Instamaps. We can report, we can produce maps in near real time and deliver them both in visible and long wave infrared. It's compatible with manned aircraft as well as unmanned. And can at 4,000 feet in a UAS, basically we can map 27 square miles an hour at roughly 8-inch resolution, post-flight real-time 16-inch resolution. Next, please. This is a basic block diagram of the architecture of the system. So we acquire the imagery, georeference in real time, database, apply our machine learning algorithms send those to a threat database, which is then forwarded to our cloud publishing platform. And we're typically publishing in a matter of 10 seconds. It's in your inbox in 10 seconds from acquisition, typically. And then after flight, we upload all the data to our cloud where we publish full higher resolution orthomosaics and produce other data products. Next. This is an example of an automated threat detect with fire. The pink lines here are gas pipelines, 20,000 gallons a minute. And this was on a patrol we conducted with a customer. And there was a big burn pile adjacent to the pipeline. We were able to report rapidly, enabling them to respond and ensure that the fire did not impact cause an eruption of the pipeline. Next, please. This is visible imagery, machine learning applied machinery threat detection, which for pipelines is a major threat. Just to demonstrate our threat detection capability, but also one of our visualization tools with the full image visible and infrared on the left, situational awareness map in the middle, and the zoom windows for threat monitoring and by the user to be able to zoom in and understand the context of a threat in more detail. Next. These are some of the thermal data products that we've been able to produce in the past. These are steam lines at a upstream oil and gas field, some other thermal targets in an upstream field here. You can see a heated pipeline, a steam line running under a road, for example. And over here is just a fire map we produced on a flight home from another mission last year. Next. Example of an orthomosaic. This one's about 4-inch GSD, plus or minus 1 foot geospatial accuracy. Published in a matter of the full orthomosaic of this 10 square mile area was published in about 6 hours. Next, please. We also have a whole series of TASE LRS gimbal camera systems. We've got about 24 of these now with mid-wave IR with optical zoom in them, in case anybody's interested. We have a large portfolio of these sensor packages. The main point I wanted to communicate today to you, though, is knowing the well-developed scientific basis of the sensor solutions that are used in wild and fire. We have a platform for sensors that might be of interest, and that's why we thought we'd share this information with you. Next, please. We've also flown 8 campaigns for telecom companies carrying small cell sites on our aircraft, and we've demonstrated the ability to, if you could go back, please, demonstrated the ability to provide 4G LTE communications in communication denied environments after disasters using small cell sites on unmanned aircraft. We've completely developed this capability both with ground fiber, ground control center to cell tower, and satellite feeds to the network core. And we've provided voice, text, imagery, and video capability to hundreds of people. Actually, after Hurricane Michael, we were down over Mexico Beach, Florida for a week orbiting, providing cell coverage since the cell service was out. Couldn't get approval for the UAS flight at that time, but knowing the importance of communications in wild and fire, this is another type of payload that can be provided with unmanned aircraft systems. Next, please.
You can go to the next slide. I know we're on short time here, but give you a quick update on where we are with type certification. So we've implemented, as Dave mentioned, our InstaMaps automated threat detection system and demonstrated it on pipelines, over fires, doing thermal imagery and mapping. And we've proven out the commercial operation. So now we're working down the path of taking that commercial mission, and which fits in very well with what you folks are doing, and getting to the point where we can operate anywhere in the country without having to have a COA and chase, which is the way we operate now. So we've basically proven it all out. Now it's a matter of going through and getting the FAA's approval. So if you go to the next slide. So just going to give you an idea of where we are. We're paving the way in this Group 3 UAS space, as extension of the NASA SIO program. We've put in our application. We're working on our G1 and our experimental certification right now, with the goal of having a full type certification sometime next year, hopefully earlier in the year. But we're well on our way, somewhere in the middle of this chart. You can go into the next slide. Dave, go ahead.
So, sure. In summary, we have a long endurance UAS, operates at medium altitudes, that's going to be available for operations in the national airspace in about a year. We have some sensor packages if those are of interest, but basically we have a platform for carrying sensors that we hope you'll find of interest. And with significant size, weight, and power availability to support those sensors. So thank you for your attention. Sounds like we're number 7 on the list for this session, so we'll keep it short. Happy to answer any questions you have.
And thank you all from Ali as well. And feel free to go to our search us on YouTube. You'll find some of the videos that we've recently done.
Great. Thank you, Ali and Dave. And it's good to see AAI. Dave, you've been a long-time participant in TFRSAC. We haven't seen you for a couple of sessions, so it's great to have you back and see that you're progressing along with UAS developments, especially in long-range UAS. And thanks again. And there'll probably be some questions for you that'll be in the Conference IO chat. And so we'll pose those at the end of the day during the closeout discussion, open discussion period. With that, sure, thank you guys. I'd like to work into the last speaker of this session. Colleague is Richard McCrate, he's a scientist, business owner, and commercial pilot with over 8,000 flight hours. He founded Near Earth Observation Systems, NEOS Limited, and co-founded Firewatch. His background includes firefighting and researching 75 wildfires in California for the U.S. Forest Service. He went on to pioneer ecological remote sensing from ultralight aircraft with major funding from NASA, worked with us at Ames and other centers in that regard many years ago, I guess we could say. Richard has a BS in physical geography, environmental science, University of California, Riverside, and an MS in forest physiology from Oregon State. And he's going to be speaking on the Firewatch efforts and Firewatch updates. So with that, I'll let Richard do a test of his sound and his volume, and we'll move on. You there, Richard? Can't hear anything yet. Might be on mute.
It looks like maybe Richard has fallen off. I can email him on the back end and see if I can locate him.
Okay. We'll hold for a second and see if he lost his connection or where he might be. After this, we'll go to a break. It'll be probably a little bit shorter. We're running a little late on time, but we'll go to break after this before we go to the final block session of the day, which has 5 presentations.
Yeah, today's second break was scheduled for 30 minutes instead of 20 minutes like yesterday, so we have a little bit of time to play with.
Good.
He was on earlier.
I'm going to recommend that we actually cut to break now. And if he ends up coming back on, we can shuffle some time in the back end or maybe try to pull people back early.
Okay.
Yeah, why don't we do that? Shall we go with a 20-minute? Why don't we come back at 2:45 after the hour? Does that work for folks?
What's our break schedule for? 12 p.m. Pacific time?
Yeah, it was technically 30 minutes, but we're going to be leaving break about 9 minutes early. So I think 45 would be great. We could get a little time, and if we can find Richard, we can have him be first up.
Okay, sounds good. All right, so 11:45 Pacific time. We'll be back from break. Work for everybody? Sound good,
Sure.
Everett? All right.
Yeah, can we post that in the slide window here?
What time was
that? That would be 2:45.
11:40. We will post it on YouTube, correct?
Okay, great. Thanks.
Thank you, Anna. All right, see you after the break, everybody.
Sounds good. Why don't you go ahead and turn on your video too there, Richard?
It should be on. Okay, turn. That's off. That's on.
I'm not seeing.
Perfect.
Okay.
You are now visible, Richard, and we are live.
Okay. Thanks, everybody, and welcome back from break. We're into our final block of the day, and we shuffled things around a little bit. We got Richard back online, and so we'll start off with Richard. Richard McCrade is a scientist, business owner, and commercial pilot with over 8,000 flight hours. He founded Near Earth Observation Systems Limited and co-founded Firewatch. His background includes firefighting and researching 75 wildfires in California for the U.S. Forest Service. So Richard, go ahead and take it away.
Okay, well, thank you very much, Everett, and greetings to Vincent and ladies and gentlemen. Thank you for this opportunity to share some information, and I've sure appreciated hearing more about other people's work today. I wanted to preface the Firewatch presentation by saying first, this is a joint presentation by my partner, Gus Cateron, and myself. I will be the sole speaker today. And before I get into the actual presentation, I want to provide a conceptual overview. So I would start by saying that in the 21st century, it's become increasingly apparent that we need a new paradigm to deal with escalating firestorms. I'm saying that from the standpoint of a firefighter and researcher. Waiting until we see smoke come up over the ridge is definitely too little too late. Next slide, please. This is what, case in point, this is what I saw flying the Witch Creek wildfire aftermath on October 27, 2007. For those of you that are familiar with San Diego, we're looking at Lake Hodges, I-15 in the background, and Rancho Bernardo to the right. This is, and what it also shows, and before we move the slide, is just the complete devastation. This was one of the major campaign fires driven by 50 to 100 mile an hour Santa Anas, and it was total devastation. Next slide. So this is a North color ortho image mosaic that was created that same day at that same time, looking at the conditions from the oblique. Now we're at vertical, mapping out the details of the fire scars that surrounded a good part of the northern Rancho Bernardo area. We're looking at Highland Valley directly to the north, and Lake Hodges is off to the left. From this color image, we can see that Rancho Bernardo had the most destruction, and in particular in the trails community. Next slide. Okay. So the fire came in from the northeast, and it ended up taking out just major chunks of real estate. We're looking at upwards of 77 homes destroyed in the trails community alone. And when I say destroyed, these are homes that are totally leveled. We're not talking about damage here or impacts, it's total devastation. Next slide, please. By zooming in, we can see in more detail the destruction for each house that was impacted. Now, what if we had a crystal ball, to be able to tell beforehand where areas were most at risk to wildfire? Well, in fact, we do. Next slide, please. Next slide. Okay, there we go. So what we can do is look back to 2005, 2 years before the Witch Creek fire. These are the same exact homes marked with X's that were destroyed in the 2007 wildfire. One of the first things we note is the dense vegetative fuels in and around the individual homes. The idea of a California requirement specifies defensible space as a mandate. We see virtually no defensible space in most of these homes, and that's been something I've witnessed over 10 years documenting wildfire destruction. Next slide. So hopefully that shows up. So this is taking the same area, taking the difference between 2005 to 2007, normalizing the color to get rid of shadows and other artifacts, and being able to look again at the relationship between extreme burn of areas in the red, orange that were where most of the vegetative fuels were totally removed, and their proximity to homes, again, marked by X, that were destroyed. We can see remnants of a fire front coming through here, spotting any number of fire dynamics. But the bottom line is that the vegetative fuel around these homes was the primary factor in carrying the wildfire through the community and destroying 77 plus homes. Next slide, please. And if we look at the same area in 2018, if it comes through here, there we go. The same exact scenario that we saw in 2005 of heavy vegetative fuels in and around homes that were destroyed and now since have been rebuilt, most of them. There are some areas that are vacant lots where the insurance didn't cover rebuilding, but we can see that there's almost a fool's errand with looking at risk management and how we deal with it in a community which maybe prized vegetation more for privacy than for safety. Next slide, please. So what can we take away from all this? My research shows that defensible space is one of the most important strategies available to protect homes from wildfires, yet one of the least utilized. So that's where Firewatch comes in. Next slide, please. Firewatch is an airborne information system support providing airborne imaging and analysis for wildfire risk mitigation. Next slide, please. The company was, or I should say the business enterprise, was founded by both myself and Gus Calderon. Gus is especially a talented man. He provides the commercial piloting of our Bonanza aircraft. He's also a 20-year pioneer of drone technology. He's working currently not only with Firewatch, but also with Teledyne's division of Drone Express, which is just in the process of building US-made drone or cargo drones, FAA certified cargo drones. If you've been paying attention to the news, they just got a deal with Cougar food chain stores across the United States. So we see is a fleet of these FAA certified cargo drones that can be retrofitted for remote sensing with a 4-pound payload or greater and over an hour endurance out of sight operation. And as Vince also mentioned, I've had 75 wildfires working as Helitac Hotshots Fire Behavior Officer, research scientist at the U.S. Forest Fire Lab in Riverside. And so I come to this with direct experience as well as trying to keep up anyway with the changing dynamics of our environment. Next slide, please. So this is a cliche by now, especially after our meeting last couple of days. Wildfires increasing in intensity and frequency, increased economic impacts and loss of life. Non-compliance with defensible space regulation is widespread. So this becomes kind of our focus on what wildfire risk represents to communities in this in the urban wildland interface. Again, this is a state law, but virtually nobody is heeding it. Next slide. So we think back to what we just saw with the Rancho Bernardo case study. This is a series of normalized green vegetation cover maps to again get rid of shadowing and background details. They show just the dominant green vegetation cover. We see again how these communities are surrounded with vegetative fuel that under sand wind conditions are extremely flammable. We see the aftermath of the fire reducing fuel load by burning up fuel matrices in combination with homes. I guess what would you expect? And then we see this reemergence of the same conditions that led to this catastrophe already cycling through in 2018. So how do we break that chain of sequence of cyclic disasters? Next slide. Well, we think studying again defensible space and understanding how much vegetative fuel is surrounding structures will be an important indicator of wildfire hazards, and that by strategic vegetation monitoring and management, we'll be able to reduce the potential destruction from catastrophic wildfires. So as a concept, FireWatch works to identify wildfire risks, inform homeowners and community leaders what those risks are, and monitor the vegetation, the vegetative fuel, to see how well these mitigation strategies work over time. And I would emphasize that this is a multi-year process. Nobody's going out and creating defensible space and changing years of 20th century thinking in a year or less. So we have 5-year studies going on with Rancho Santa Fe in San Diego. We're also working with the Tree San Diego, working with them to help optimize their tree growing programs. And this has funding from CAL FIRE as well. Next slide. Where you incorporate both integrated airborne and drone technology with GIS. Next slide. And so we create multispectral data sets from aircraft or drones. We process and analyze the imagery both from the area or community level to the parcel view. We generate image maps for characterizing color infrared, and spectral vegetation indices. We use GPS triggering for repeat station imaging, monitoring changes over time. Next slide. Next slide. Okay, great. Now, again, because we're dealing with homeowners associations, we found it to be very critical to put information in more accessible forums. So we're using Google Earth in this case to create super geotip overlays. We can put 16 gigabyte images into Google Earth and create tiles that then allow easy navigation and viewing of not only our data, but all the context data of Google Earth. We can also bring in other people's data like parcel map information, so that for every location we have a parcel ID, homeowner or owner of the property, and other considerations. So we find this especially valuable when we find hazardous conditions, no defensible space, because then we can go to the owner, know the address and who to contact. And that's being done now by the Rancho Santa Fe Fire Department. It's using this data for that purpose. Next slide. So we can also zoom in. This is 5-inch GSD imagery that covers 20 square miles. So we're able to go in, and in particular, we're using the color infrared to look at the above average mortality going on in eucalyptus and other introduced species, primarily due to climate change, the drought, extended drought. And we're seeing a lot of these trees. You can see a kind of a black smudge color to the trees that are impacted and dead and dying. So we document that as part of the flammable fuel within the defensible space. Next slide. Okay, and I'm just going to go through these. We break it down to individual parcel maps that are provided to homeowners by the Homeowners Association. This will eventually be through a web portal. And what we're showing here is the defensible space perimeters that are relevant for each structure or home. This allows a homeowner to eyeball it for themselves. They don't need a sophisticated technological solution to be able to tell whether or not they're in compliance. And we can run through the next series of slides fairly quickly if you want. Next one, please. What it looks like in color infrared, notably a number of dark trees showing indications of stress. We're also looking at a lot of chaparral in and around. That's part of the influence. Next slide. And we look at the NDVI, generalized green vegetation cover. Next slide. And we've developed some of our own indices that are especially tuned to looking at dead trees. So we are able to cross-reference between the images to differentiate subtle color information into distinct dying versus stress categories for follow-up. Next slide. And our biometric is basically using change detection to determine by parcel where vegetation has been removed to create defensible space. We can also look at additions of vegetation, maybe converted less flammable vegetation that's used, because we still have to keep in mind that these homes all through these areas are also part of a watershed. So the notion that we're just going to clear cut all parcels and make a bare Tucson city, look to it is not viable. We have to be a lot more clever than that. So hydrological modeling would be applicable to the data once we have it in the GIS. Right now, we see very little activity, but that's probably partly due with the coronavirus. We have now a website developed to inform homeowners of the opportunity to reduce flammability. Who cares? Well, people that are at least conscientious about saving their homes care. The insurance cares. They're getting sick and tired of paying for liability insurance for people that don't comply with the law. And of course, firefighters have to consider safety first and where they can go in and safely confront a wildfire. And finally, the final slide, I'll just say, next slide, questions can come at a later time, but one thing I've observed over the Witch Creek fire and other fires throughout Southern California is this total devastation from firestorms. And yet, when I look down at all these destroyed structures, there's hundreds and hundreds of swimming pools. They're out there full of water. And this idea of thinking, how do we, equate a wildfire with all this water that we would think you would use to fight the fire, but we're not using it at all. There's probably 1 million gallons out there untapped that if we used automated sprinkler systems with smartphone integration, we couldn't create some defensible sense in terms of the environment, including the ambient environment around structures, around vegetative fuels to reduce flammability, reduce the destructive impacts. And I conclude with that, and thank you so much for the opportunity to share this information with you.
And thank you, Richard. It's always good to see the work that you're doing there. And yeah, there's a big puzzle there on a number of fronts in terms of how do we do a better job here. So thank you.
You're welcome. Thank you.
And we're going to move along to the next presentation, the first of Block 6. We're going with Chris Rowley, and he's going to be presenting on Sky C2 System Overview, which was a USDA Phase 2 SBIR project. And Chris is the director of the UAS and Geospatial Solutions Division at Skyward Limited. Mr. Rowley has worked in and around the Department of Defense and Intelligence, Surveillance, and Reconnaissance, also known as ISR, communities for more than 30 years. So go ahead, Chris. Let's do a sound and video check.
Hi, can you hear me, Everett?
Yes.
Okay, great. Thanks so much for inviting me to speak today. It's a real honor to speak to this audience and give you an update on the Sky C2 system. Slide, please. So this was part of a phase 1 and phase 2 USDA SBIR efforts. We've been working on it over the last 4 years, actually. I spoke in 2017 at my first TFRSAC, and here we are at the end of our phase 2, getting ready to demonstrate the system at the end of the summer. Originally, when we started looking at this, real-time surveillance with drones over fires wasn't like something that was happening a lot, nor were we talking much about firefighter tracking. That's become much more complex, we're happy to see. But that's kind of what we based our initial idea on, traditional DoD sort of surveillance and reconnaissance in real time, providing command and control and situational awareness. Next slide, please. And the methodology behind our technical objectives was to try to use as much commercial off-the-shelf and government off-the-shelf solutions to keep things low cost and flexible. We wanted to make sure that we were using layering standardized geospatial data with common image formats and data formats so that we could integrate with other systems, other databases, other pieces of software and tools that might be used by a community that we were beginning to interact with. As much as possible, we wanted to remain open in our architecture. The idea was to provide a real-time COP that would help with turn information and data into actionable intelligence. And we didn't want to rely on the internet, so we built the system as an intranet, able to communicate with itself, but able to connect to the internet if possible. The whole idea in the end was to have the ability to track and visualize firefighters in real time, see the area in which they're operating, and maybe have a secondary means to visualize and confirm fire status and position. I want to point out that this is not a silver bullet or end-all be-all solution. It's simply, more than anything, a force multiplier. Next slide, please. So in designing the system, we also wanted to make sure that we were keeping it as small as possible and mobile as possible. So while it's similar to Defense Department of Defense systems, we really are striving to keep a small footprint, keep costs low. You can really get the system for under $100,000, and that includes aircraft, sensors, ground station, and everything. We, again, tried to make sure that we're open standards, open architecture to make everything as plug and play as possible so that we can swap out sensors, which we think we have achieved. Swap out sensors, data types, things of that nature, and connect with other sorts of tools outside of our own system. This is a baseline system. It's a prototype right now, and we will be showing it here at the end of the summer. So we still need more inputs from the communities that we're working with, the fire community. But we're still looking at new ways to grow the system. So right now we're looking at integration with CivTAC. We're talking with Brad Schmidt out at the Colorado Center of Excellence for Advanced Technology and Aerial Firefighting. We're working with NOAA right now. We just concluded a phase 1. We're looking at winning a phase 2 here shortly. We're doing integration with electrical power infrastructure inspection tool that helps identify micro-arcing in power poles, which is one of the leading causes we know of wildfires. And we're always looking for partners and more funding as we continue to move forward. Next slide, please. So this is just a quick overview, very simple cartoon that kind of shows the system concept. Basically, there's a device worn by firefighters that broadcasts a radio signal to the aircraft where we also have a sensor ball with electro-optical and IR capability. All that data is sent back via radio to our ground station where we have aircraft control, sensor control, and analysis workstation with specialized software. Next slide, please. These are kind of the main tools that make up the overall system, and I'll talk about each of these in more detail in the slides to follow. Next slide, please. So kind of the backbone of our system is what we call SPADE Pursuer, SPADE Database and Pursuer Common Operating Picture. This is a GOTS tool that was initially developed in cooperation with the Air Force Research Laboratory. And it's got over a decade of operational use on the defense side. But we've been doing a lot of work to try to make it relevant to this specific mission. It's built on the NASA Whirlwind engine, and we're able to pull in multiple layers of sensor data, multiple feeds. And we're integrating, we're beginning integration with TAC to any feeds that we pull in from our own systems that we can feed into TAC. And we have the ability to connect to other web services as well to pull in data if you want to visualize it within our common operating picture. Next slide, please. These are just some of the other things that the system is capable of. I don't want to, I'm trying to move through these quickly to respect time, but we can basically do a lot of the same kinds of things that other COP tools can do with 3D data and shape files and tracking and that sort of thing. Next slide, please. So this might be one of the more unique components of our system, what we call F-Star. It's a firefighter tracking system. This is a conceptual drawing of the unit that we have that's very similar, but it is a body-worn beacon that communicates in the 900 to 950 megahertz range. Tested so far, we're looking at about 5 miles of transmission distance. One of the unique things about it is that it has the ability to turn on a distress mode so that if you're under duress, you can turn that on, and on the pursuer COP, it will show a change in color and a flag to show that the person when that particular beacon is under distress for some reason. We're looking at upgrades to add an IR or optical light emitter on this device during the scope of this project, but it would have introduced too much project risk. So we're continuing to look at that as part of a follow-on solution. And out of our demonstrations, we're hoping to get some feedback on things that we can do better with the system. Next slide, please. So the other component of this system is the transceiver that's on board the aircraft. It's an antenna that will receive that data and push it through some persistent systems radios that we have on board the aircraft, along with the rest of the data from the aircraft itself and the sensors down to our ground station. One upgrade that we're looking at right now is the possibility of connecting the beacons to something that provides biometric data, so like local temperature, CO2 content, atmospheric pressure, and vital statistics of the firefighter wearing the beacon. Next slide. So this is just showing that our dots will show up on the moving map in Pursuer and display a track behind them. One of the things that we felt it was important to do was break these beacons up into groups and individuals so that you could organize your beacons by group and individual, and if you wanted to turn some of them on or off, you could, so as not to clutter the display. Next slide, please. This is our aircraft, the Supervolo. It's interesting in that it's still a small UAS, so 26 pounds, but it has like a 7.5 hour duration because it's vertical takeoff and landing and fixed wing, also gas and electric hybrid aircraft, which gives it that extra ability to fly longer. The gas motor charges the batteries during flight so that you're able to keep the batteries maintained during flight. And then if for some reason you were to lose battery power, all electrical systems kind of transfer over to the gas engine. And if you lost that, everything transfers back to battery. You can take off and land with the batteries and fly with the fuel primarily. It all fits in one transit case. And right now we're carrying the Trillium HD40 sensor on board, but we're able to swap that out for a variety of other kinds of sensors. A future version of the aircraft, as a matter of fact, will include this Lucent 12, or actually the Lucent 31 Vision large area mapping camera. Next slide, please. Something else that's great about this aircraft is that it only consists of about 6 pieces that you can put together in about 5 minutes. and you can launch it very quickly. And launch and recovery takes about 5 minutes, about the amount of time it takes to refuel the aircraft. Because it's vertical takeoff and landing, you can take off from virtually anywhere. And there's some statistics on the slide that I'm not going to go over right now, but you're welcome to check those out. It's pretty unique for a small UAS. Next slide. So we are using persistent systems radios on board the aircraft. We have a wave embedded relay module, which works in the 2.4 gigahertz transmission range. We have the same thing on the ground, basically in an MP5 chassis, but we will be swapping that out here shortly in the next couple of weeks for a new 120-degree integrated sector antenna, which will provide us a better sector swath and increased gain for further distance. I'm not going to necessarily speak to what that distance is because we still have to undergo actual testing, but it's advertised to be in the area of about 30 miles. Next slide, please. So we had looked at putting ADS-B systems on board aircraft, but determined not to do that because the FAA had decided that ADS-B on drones wasn't something that they wanted to do. So we did not include that. Also, the company we were working with only just got their TSO certification for ADS-B systems, and it boosted their price up quite high. So due to project risk, we also determined not to do that. We can, however, integrate that if need be. Next slide, please. This is the ground station. It basically is like an intelligence analyst system. It breaks down into about 5 transit cases, so total system's about 6 transit cases. Next slide. Okay, it looks like I'm out of time. So I'll just invite you all to take a look at these slides whenever you have a chance. And if you have any questions, please feel free to reach out to me.
Thanks, Chris, and thanks for keeping in touch with me over the years on this. It's been it's been fun watching this capability go through the various SBIR development phases. So thanks for that.
Yeah, absolutely. Thank you, Everett.
Okay, let's keep on target here. Let's next we're going to let me bring up the bio here. I guess Brian Wee is presenting on the knowledge management for mitigation and response, and Brian is based in Washington, D.C. as the founder and managing director of Massive Connections, LLC. He works on data-driven decision management for climate resilience, traceable decision-making using data and models, and legislative and regulatory barriers to the effective use of decision science for complex environmental challenges. So Brian, you want to give a sound check and turn on your video?
Yes, can you hear me and see me?
Hear you fine, and we need to turn on the incoming video. There you are. Yep, you're fine.
All right. So thank you, Everett and Vince, actually, for inviting Bill Ting and myself. So this talk is presented Data Information Services Center. Next slide. And the punchline here is summarized in this diagram. So this diagram, what you see here are the various phases of fire management, starting from prediction all the way up to thinking about long-term recovery and monitoring needs. And how do you enable data-driven decisions depicted by the second half of the diagram below, where you look at how data is fed into models, ultimately used for fact-finding and scientific assessments, and then relied upon in management decisions. So as you look at this slide, this is where we will end this talk, but think of what you just heard from people like Dave Jones earlier today, when Dave talked about, people spending most of the time, 80% of the time looking for data and 20% of the time trying to extract intelligence out of the data. And so if you had a picture like this, if you had a schema like this where data is connected to decisions and you could identify an appropriate decision made in the past that resembles what you are trying to solve, then half of your problem of locating data is solved. So that's what we are aiming for. Part of this talk also resonates, I guess, with John Melton's earlier talk about NASA Ames data and reasoning fabric, where the fabric connects data to the other downstream processes. And so that's what you might want to think of as you look at this diagram. And lastly, Sean Triplett yesterday talked about incident awareness and assessment, the IAA, and how do you use the data captured in an early phase of the fire management process and use that for subsequent analysis after the process again. So if those points have resonated with you across those earlier talks, this is where I am trying to lead you towards the end of this talk. Next slide. So yeah, the whole motivation for this is data-driven, science-based decisions. And when I mention this, you should, some of you might think of things like the Foundations for Evidence-Based Policy Making Act, recently passed about a year and a half ago by the US Congress. And so what we want to achieve and what we want to drive to is decisions that are technically defensible and actually legally defensible in court even, that can be traced back to decisions. And we want to get to a phase where you can look at data and information visualization in a very intuitive manner that fits your purpose and fits your needs. Next slide. And this is presentation. We will not have an actual software demo. It is a long-term vision, and what Bill and I wanted to do was to assess the level of resonance of what we're doing here with the audience and see if you want to take part in the requirements definition, because again, we have not actually built any software except we have experimented with prototypes. But before we think about actually building anything, we want to make sure that the requirements are right and that it meets your user needs. Next slide. So this work is conducted under the auspices of the Earth Science Information Partners, ESIP, which Everett has mentioned it a couple of times in the past. And I won't spend too much time here except to say that ESIP is a rather unique organization. It's run under a 501c3, sponsored by NASA, NOAA, and USGS. And Bill Ting and I, we run this thing called the Agriculture and Climate Cluster, the ACC. It's a group within ESIP, and other groups include things like the Disaster Lifecycle Cluster. And for example, Dave Jones, whom we have heard from earlier in this talk, Dave co-chairs the Disaster and Lifecycle Cluster. And there are other clusters or other interest groups, for example, the Semantics Harmonization Cluster and the Discovery Cluster. We won't go too much into that, except to let you know that there is a group, the ACC, the one that Bill and I co-lead, focused on agriculture and climate, but the term agriculture automatically implies that we cover issues relevant to USDA, which includes wildfire, which is why we're here. Next slide. The topics and the themes that our cluster covers include science and technology. So under science, we're going to talk a little bit more about wildfire mitigation and response, but the cluster has organized activities along the lines of climate adaptation strategy. So for example, we also examine issues about coastal flooding and how data can be used to inform your options for adaptation in coastal areas. And also for technology-wise, our cluster focuses quite a bit also on natural language processing. And so there has been quite a bit of AI and ML discussions in this today and the day before. So that's also within the scope of our cluster, AI ML. We also look at AI ML, not just for analyzing geospatial data, but also AI ML for natural language processing. And quite a bit of this talk actually will be focused on natural language processing, as in how do you feed a machine documents, human readable documents, and get the machine to help you find the data and information relevant for your problem. And where I'm going with this for the talk is I'm going to talk about the BAERs, the Burn Area Emergency Response reports, and how those you might see those as being consumed or analyzed by a machine using natural language processing, and a machine actually can do some limited reasoning about what's in a BAER report, so that the machine can suggest to you, based on your current circumstances of the fire, what are there similar BAER reports that you could pull up to inform your decision. And so part of that goes to the concept of linking data to decisions. So again, you want your decisions to be data-driven and science-informed and technically defensible and even legally defensible. And for the legal side, which is why our cluster examines, occasionally we examine policy issues. So for example, we just recently had a 1.5 hour introduction to US policy, and basically it's an introduction to some of the basics of the legal foundations of US law. All right, so next slide. Now, so what you see here is an informal representation of the fire management life cycle, and part of it mirrors NASA ARMD's workshop tomorrow. Right, next slide. And again, just to emphasize, we're interested in connecting. How do you let the machine connect data to model code to information? Next slide. And the way that we want to do this is to make it such that a data that is used for example, in prediction, you want to see the same data used, for example, in mitigation planning, or in the case of what you just heard from other speakers, data that is acquired during the early attack phases of firefighting, used, for example, to inform the options for a BAER team on the ground. So how do you connect these pieces of information so that you use the same data consistently throughout the life cycle of the wildfire? Next slide. And this is a wonderful way of connecting across disciplines, across organizations, and across time. And this partially goes to some of the points made by Natasha Stavros about how do you connect economics and also the societal needs and also ecology in a consistent picture. And I'll show this in the next slide. Next slide. Where after completing the picture of connecting data information across the entire life cycle, next slide, what you can do is to, could I have the next slide? What you can do is actually to convert that connected picture into something called a knowledge graph. So I'm going to give you a very quick example of a knowledge graph that we have created for this presentation. Next slide. So this knowledge graph is based on actually on a BAER, the Hyde Park fire in Colorado. Next slide. And so we start off with, this is a fictional example, but we start off with a fire. This is an example of an information node, a node in a graph database. So what I'm showing you here is actually can be done in something called a graph database. Most of you are familiar with relational databases. This is another kind of database where details of the fire are captured in the graph. Next slide. And what you can do in the graph database is to tell the database that for this fire, it has a certain geography, and for this geography, there is an overlap. And in fact, this overlap can be automatically detected by the machine, that for a fire that is happening in Canyon Lakes, the Forest Service District Canyon Lakes, it has a geography overlap with a vulnerable infrastructure, State Highway 14, which is pointed into an actual geospatial database. And so this is a little bit of how you connect a graph database representing that knowledge. So this is knowledge represented in a graph database to an actual data repository, an existing data repository. Next slide. Furthermore, and then one more slide, that fire has a corresponding BAER report that contains information about soil erosion potential, and also it has scenarios it contains scenarios for the way that the soil erosion potential is calculated and estimated. And as we see again, the scenarios for soil erosion scenarios are actually retrieved. The data for those scenarios are retrieved from actual data sets that are curated in government repositories. Next slide. And then the BAER also has stabilization treatment options, right, for the given soil erosion potential. So this is the case where if you look on the right-hand side, your data, right, is traceable back to a decision, the decision being the stabilization treatment. And so again, going back to what I mentioned earlier, what you can do is you can imagine a scenario where the machine is given the current circumstances of an ongoing fire before fire containment, and the machine is able to retrieve this entire data to decisions traceback to let the current BAER team know, based on what it knows about the current fire, this is how another team had handled this fire in the past for another geography. Next slide. And just to remind you, there is an equivalence between what you saw in the graph database and what I showed earlier in terms of connecting data and information across time and across space and across organizations, across disciplines. So that's how you can use a graph database actually to represent these kinds of connectivity. Next slide. And so what we want to do is we want to translate such a program into, next slide, into graphs and to transfer the information across different graphs. So you have one graph that represents the information entities and data entities during the fire. You want to transfer that information across to after fire, the processes that represent after the fire. And so information transfer across could include things like topography, weather, and values at risk. Next slide. And so as to facilitate, what you want to do is facilitate reusable and repurposable evidence-based decisions. And what you can do, next slide, is to use the graph database, for example, to visualize the connections between data and decisions. In this case, what you see here is actually a query from the graph database showing on the right-hand side, the pink nodes are data. On the right-hand side, on the left-hand side, it's actually a transition memo that the Biden transition team gave to the USDA. So the graph database is able to pull out what are the relevant data sets that will inform some of the initiatives proposed to the Biden government by the transition team. Next slide. And the next steps, and I'll finish off this, my last slide here, is that the climate cluster is agriculture and climate cluster is potentially putting on a workshop for the fall. And if any of these ideas resonate with you, we would encourage, Bill and I would encourage you to get in touch with us. And that's it. Thank you.
Thank you very much, Brian. That was great. And we just were online talking, Bill, Brian, and I a couple days ago, and I'm fascinated with this concept of looking one data set, one phase of fire, the data for that phase informing the next phase, and how data moves from one phase of fire to another and how it's used in the decision-making process. So thanks for that. To keep moving here, we're going to go to the next presentation by Daniel Dalton, Lighter Than Air, and the company's name is Sky. And let me just read a quick bio here. Daniel leads Sky's commercial rollout, working with strategic partners to design and deploy solutions for a diverse range of clients. And he has 30 years of experience in the technology sector. So go ahead, Daniel, if you want to do a sound check and a video check.
Yes, good afternoon. It's Daniel here. Can you hear and see me?
Yes, Daniel.
Excellent. Thank you so much, Everett. Firstly, Vincent and Everett, thank you for inviting me to introduce Sky to this community, to TFRSAC. Really helpful and strategic for us in where we are. Brief introduction, just before I go rolling into our themes. We've been encouraged and very well supported by our friends at NASA, at USGS, Goddard, and instrument teams. So what I'm going to tell you about today is really a story of two parts. The first is really a capability that we bring, and it's a story about a permanent capability that we can put in the sky. And the second one is where I'll embarrass myself with my lack of knowledge, and I'm promised that John Stock and Jason Stoker in the audience to save me on instruments. And I acknowledge there have been some superb instruments and data processing capabilities presented, and I hope today this helps shape our story about how we can also serve this community. All right, let's get going. First slide, please. Okay, what is Sky? Very simply, we are a platform that you park up in the stratosphere, so about 65,000 feet approximately, or 20 kilometers up. And it allows us to carry a range of instruments up there. The range of instruments is what the second part of the discussion is about today, and is where we're looking to refine that. But the really important part about this story is that we can sit up there in a single spot as a station, or we can move, and we can provide a range of capabilities back to the ground. So you can see some of the concepts there. We can do very, ultra high spatial, temporal, and spectral resolution missions. We can sit and stare for a long time. We can move. We can follow an event. We can change the mission. And of course, we can fly many of them, mesh them. And the real message for today is really about what happens when you bring what you could normally do capability and bring it down close, so that you can see more and do more. And likewise, what you can lift up from the ground, terrestrial equipment you can lift up and place at this altitude. And that's where our story, I believe, is unique in helping this community. There are many good applications, as you can see down there, for sourcing data sets with different classes of instruments together. Next, please. So we're real. This is a photograph from last year from one of our missions we flew. That is the Sky One airship. It's the first commercial scale airship. That is in our hangar in Roswell. Some of you might notice that, in fact, she is floating. She is lighter than air, uses helium for lift. And you can see at the rear there is propulsion, control surfaces. And in the next slides, you'll see a little bit more about what the physical makeup is of her. So next slide, please. This is her emerging from the hangar. You can see and get a much better sense of the scale of her there. She is 262 foot long, or about 72 meters. There is a great video on our website. If you just go to sky.com, it's on the homepage, worth 3 minutes over a cup of coffee. But briefly, what you can see here is that on the top, there is solar caping. We capture solar energy, we store it in batteries for persistent energy provision. And at the rear, we have obviously propulsion control services. We have avionics boxes at the front. And then the rest of it is left to payload, which is where I come into play. So we have a closed loop energy system that allows us to stay up there and persist for very, very long periods of times. The shininess of the material briefly isn't only because it's cool. It's because we've a lot of innovation in material science that has allowed us to create materials that endure and are ultra light, ultra strong, and ultra gas resistant, as in we retain helium for years without losing our buoyancy. So it's an incredibly efficient platform. And last comment for those who are keen, there is no mechanical structure to the airframe. The whole fabrics are strong enough that it remains super pressurized and provides the structure not only for the flight envelope, but for attaching equipment anywhere on that hull. And that's another innovation that we've been able to bring. Next slide, please. So I mentioned earlier, this is a story about a new capability. We like to think this as actually really a layer of infrastructure that we can now put in the sky to serve you. And really, it's a simple story of saying, if we sit in that sweet spot between where satellites typically are and terrestrial is, what happens? Well, you can bring, the best of SAC grade or space grade instruments down and improve what they can do in terms of resolution, in terms of stay, etc. And likewise with terrestrial, we can lift up stuff that normally is limited by line of sight and put them together in a unique combination. So we get to see things in very high definition. We get to persist, which allows us to create very rich data sets. And specifically, when we sit still as a station, we can characterize very large areas over long periods of time so that you get unique reference points. And ultimately, we can lift any combination of packages really that you're looking for on a mission. I'll explain later, but roughly speaking, the range typically is about 27,000 square miles of coverage. And lastly, one area which won't surprise you, where we've had a lot of traction, is in being able to provide communication services. So basically, standard LTE, as in 4G services, we can fly that 2G, 3G, 4G, 5G, you name it, it doesn't matter. We can fly it from up there and provide very wide areas of high-speed broadband capability to standard devices, which opens up a whole new arena of capability as well for teams on the ground. Next slide, please. Briefly on this, really it's just to say that the materials have allowed us to create a unique capability as a piece of infrastructure. And that's really what I want you to take away from this picture. Once one of our stations is up there, she can sit there persistently. At the moment, we're planning for year-long missions. Materials and other things would take us longer, but for practical operating reasons, you want to do annual certificates of airworthiness and other reasons. But if you've got several, you've got a fleet of them up there, you can swap them in and out. And the beauty of the format is that, big is beautiful. It allows us to capture more energy, lift more equipment, provide better, longer endurance services. Next, please. So let's unpack that and find out what happens when we load things onto her. So next slide, please. So the focus for us and our understanding, this is where I embarrass myself, is trying to help with forest fires, and particularly in their prevention. So I've been guided wisely by our friends at NASA and USGS so far. And really, my understanding is that we can provide a persistent eyes-on capability initially. So if you imagine that we're up there year-round, we'd be able to provide you with a 24/7 capability to see over very wide areas in real time and through different instruments. And obviously, if we can detect things earlier in the cycle, it puts everyone more on their front foot. We can help, provide data from several of these back to a centralized command and control, which presumably, and I've certainly heard today and yesterday, we can improve the whole data processing, data flow, decisioning, etc., to make better use of scarce resources. Obviously, the persistence capability allows us to provide long-term analysis and trends, shapes, changes, etc., and hopefully do a better job of detecting the preconditions for fires, or alternatively things like landslides, floods, etc. So very wide spec capabilities. Next, please. So here's a sort of concept, if you like, of our capabilities. And if you just draw your eye really to the image, it kind of breaks down into three main areas of capability. This is based off instruments off the shelf. It isn't specialized. But what you can see there is typically we have a capability in the inner ring of about a 50-kilometer radius to see sub 1 meter with stuff we know of off the shelf. And I'm sure there's even better kit there. And as you widen that out to about the 150-kilometer range, it goes up to above a meter resolution. But we also get, that's typically the limit of 4G LTE. It may go further depending on our bands, but that's the service range for broadband capability. Voice will go further. And then finally, at the furthest rings out of the 300-kilometer range, we can certainly do wide area sensor detection, whether it's IoT or specific devices. We can capture that and relay that data. So essentially, you can provide permanent cover of a very wide area. And of course, because we can sit closer, we can carry equipment, etc., you get much better, signal to noise ratio ultimately through this, just by sitting there for a longer period of time, being closer and adapting instruments. Next, please. So just to put it briefly in perspective, there's two images that Jason kindly supplied me from USGS of the fires that were in California and Colorado. So if you imagine that airship up there, with a different set of instruments, this is kind of the operating region one airship would cover for you. And of course, if you stamp that out with several more, you could cover very large extensive areas and have a persistent capability. Next, please. Okay, so I'm going to break this into three phases that we understand and the concept of operations. And just what I'm showing here is some candidate instruments that we are dialoguing about as a possible mission configuration for this. So the first stage would be, pre-event mapping, providing you with a very wide domain of awareness, both in area, but also across different sensor types. As an example, with hyperspectral, you'd be able to measure and monitor things like water stress, species composition, fuel stock, the way land usage is varying over time and changing, and ultimately the temporal profile of all of these. Similarly with the LiDAR, the Casals LiDAR that's been considered for this, fantastic capability to map and detect vegetation coverage and structures, ladder fuels. We can see exactly where buildings, utilities are, and how those are varying over time, and even down to power line and plant monitoring. There's a version of what happened or was developed with NERC. And I'll show you at the end briefly, we've had some forays with utilities into understanding and monitoring their equipment in real time to pre-detect when things are getting old and dangerous. So that not only is economic for them, but it's much better for safety. So those are two possible candidate instruments there that would provide data for pre-event mapping. Next slide, please. The second one is actually when there is an event, what we consider to be response support. So you'll get effectively a big eye in the sky. And of course, if you add cameras in, we can obviously provide live streaming, not only of a wide area, but we can provide very zoomed in, very high resolution real-time video imagery as required. thermal imagers, and instruments for monitoring weather, right through to microbolometers. All of those could assist in your real-time awareness and your ability to focus in on a particular area. The instruments on the right, you can see some of the candidates again that we've been sort of winnowing down as good candidates, possibly for this mission, this stage of the mission. But the other one I just want to highlight is in communications as well. So if you imagine, we'd be carrying, let's just say it's a 4G capability over that area, then you'd be able to make sure that every person who's operating in there is connected constantly on a standard device, not necessarily a specialized device. You can get video grade comms to them, and likewise you can monitor where people are. And in the extreme case, you could open that private network up to also temporarily to become a public network, so that civilians who are stuck in places who may have lost comms, typically in an event like that, you could connect to them as well, and be able to communicate and guide them through what you need them to do. And again, it allows you to detect where things are in real time on the ground, because most people these days carry a device, so it's a very good indicator for where humans are on the ground. And again, all of this can help and be fed back into centralized command and control. So in addition to that, if you had sensors out in the field as well, obviously we'd be able to, with our big antennas, capture that and relay that data back to you, and give you multi-layer capability off this layer of infrastructure. Next, please. And lastly, post-stage, the stock update effectively of all of this. Obviously, we'd continue being up there, and you'd be able to understand what's happened, not only immediately after the fire, but a week, a month, 6 months, etc. You'd be able to do cool things like look at the impact to soil and below ground carbon. And ultimately, all of this helps feed all these great models that have been spoken about today and obviously in existence, so that you can keep updating and providing much rich data sets, more real-time data sets, which obviously is a sweet spot for me, having an AI background. Long-term, high-resolution data is what you want. That's what gets these AI models doing their magic. Next slide, please. And finally, I know I'm short of time, but just to give you a sense, we were looking, it's funny enough, the other way around for, as I was saying, utilities, detecting hotspots, prevention, trying to prevent failure in power lines, in endpoint generation equipment, etc. And not surprisingly, they've been one of the anthropogenic sources of some of these fires. So it's a nice confluence of instrument payloads and both sides of the coin coming together, we felt. And last slide, and that's me. So thank you, guys. This was hopefully a good introduction to a layer of infrastructure we hope to be able to give you. And we're here today to listen and learn, and please help us shape our roadmap. Thank you very much.
Thank you, Daniel. And yeah, there's a couple of questions in the IO chat window there. If you want to take a look there, we'll be getting back to that when we get to the open discussion session. And we'll go ahead and switch to our next presenter now. Andrew Antonio is the co-founder and CEO of Urban Sky, a venture-backed stratospheric technology company developing broad area, low-cost, high-resolution remote sensing systems. So, Andrew, if we can get a sound check and a video check.
Yeah, can you hear me and see me okay?
Yes.
Great, thank you. Well, yeah, it's an honor to be here. Thank you so much for having me, and I'm really excited to talk to you all a little bit about our technology, and we'll continue the theme of the stratosphere here with Urban Sky, following Sky. So yeah, so just very briefly, we're developing a high resolution, broad area, very low cost stratospheric remote sensing system that can downlink real-time infrared and optical data above active wildfires. Next slide, please. So before I get into all that, just a little bit about us and our company. So again, we're a company that develops multiple different types of stratospheric flight technology and remote sensing capabilities. But our key theme is that we make very, very small, rapidly deployable, extremely low-cost systems. So you can think of us like the analogy would be a small UAS or drone. These very small, almost like weather balloons, can be launched rapidly within minutes and image very, very broad areas from the stratosphere over target areas. So today we have a couple systems operational. We'll talk about a few of those, but our main two operational sensor systems today are a 10 centimeter GSD optical system, so very high resolution optical imagery, as well as a dual high resolution infrared and optical RGB system that we're developing and that we'll talk about here today. So next slide, please. So what is this system? So we call it a micro balloon. So I touched on this a slide ago, but basically I spent most of my career, about the last 10 years or so, working on stratospheric flight systems, and I've flown the largest stratospheric balloons that have ever been flown with massive payloads. And so with Urban Sky, we've built a company that has gone in the complete opposite direction, which is all about building very, very small systems that can be rapidly deployed from anywhere. So instead of having to steer a stratospheric asset, our value is in, if you can launch from anywhere with just one person, then you can image an area of interest and take all the advantages of the stratosphere, that being broad area, very high resolution, a lot of things that were touched on in the last presentation. But that's what a micro balloon is. So we invented this thing called a micro balloon. So you can think of it like the micro satellite of the stratosphere. So very, very small, but can carry very powerful sensors. And again, if you can launch from anywhere, from the back of a truck or off the side of a road or in your backyard even, then you can build really, really good flight models using software to determine exactly where your small flight system will go, so you can image the area of interest that you're interested in. So very easy and rapid to deploy these systems. Again, just one or two people. Currently it's two, but very soon it'll be down to just one person to launch one of these systems. And can cover very large swaths of area over your particular area of interest. Next slide, please. So again, just to talk about the stratosphere, this was touched on before, but I think it's important to mention again is, why use the stratosphere? I tell people all the time, it's funny. You can count the number of companies operating in the stratosphere on maybe two hands. And so there aren't many. It's a very untapped layer of Earth's atmosphere, but it offers incredible advantages, especially for remote sensing. So like aircraft and drones, particularly like aircraft, from the stratosphere, you can capture very high resolution data, much higher resolution than an orbital satellite platform. But like a satellite, you get a very broad area perspective. So you can get very large ground swaths of imagery from the stratosphere projected onto the ground. And of course, it's very low cost. So aircraft, as I'm sure many people on this call know, when you deploy those, you're talking about potentially personnel costs, there's maintenance, there's fuel. So it can be very, very expensive to deploy an actual airborne asset. And of course, it's very expensive to launch a constellation to space. But with the stratosphere, in particular with our small micro balloons, they're very, very inexpensive. We're talking, single digit thousands of dollars per system, the balloon plus the sensor system. So, you can launch one of these a day and still be nowhere near the operational costs that you may encounter if you're operating a drone aircraft or leveraging a satellite-based asset. Another thing that's really important here, I think, especially for this audience, is that operating a vehicle in the stratosphere poses no conflicts to airspace for be it monitoring assets or firefighting assets. We fly very high, 60,000 feet and up, generally around 65,000 feet is our operating altitude. So we're far above commercial airspace and thus pose no conflicts to any aircraft or assets that would be in the airspace over a wildfire. Next slide, please. So that was a little bit about our company, but let's talk a little bit about the solution in particular for this application. So we're really excited about this, and we've been working on it really hard for quite a while. But basically, we have this existing platform that is the micro balloon. And just recently, we completed a phase 1 SBIR with NASA JPL to design a sensor system that would be valuable for wildfire monitoring. So we've done that and we've flown it, and I'll talk about it shortly. But in essence, what we're building is a high resolution long wave infrared and RGB sensor system. So it's imaging in both long wave IR and RGB at the exact same time over a very broad swath on the ground. And we have some edge processing on board this micro balloon that will pull out hotspots. So we're literally doing edge-based computing to determine certain temperature levels projected on the ground from the IR data to downlink where hotspots are in real time to bring that intelligence back down to the ground. So this is not a platform that can just launch, capture the data, and be analyzed after the fact. This is a platform that can scan very broad areas in real time and downlink areas of interest, in particular high resolution hotspots for first responders. Next slide, please. So a little bit about our status. I mentioned this on before, but yeah, so we're kind of taking two approaches to this and developing this hotspot system that we call it, the stratospheric hotspot system. So just recently we finished this NASA Phase 1 SBIR, which funded the vehicle, the development of the microballoon itself, and the sensor suite, that long wave infrared and RGB system. So from 60,000 feet, we're able to get 3.5 meter GSD resolution in long wave infrared and 1 meter RGB resolution. And we do that in a payload package that is less than 6 pounds. So very difficult, but quite impressive to be able to get that type of resolution in a very small payload package. So we didn't just build it in the Phase 1 with NASA, we flew it and we demonstrated it. So you can see on the right-hand side of the slide here, on the bottom, we're showing an overlay of our RGB data and our processed long wave infrared data. So you can see sort of the resolution. If you see some of those buildings on the ground, you can see the type of resolution that we get from that altitude with this sensor system. And then on the top picture there, you can see a full collect. So this shows you that you know, as this sensor collects, that's an actual full collection that we did. That was about 600 square kilometers of landmass covered in just under 1 hour. So pretty powerful capability for the cost. We have submitted a Phase 2 proposal to be able to demonstrate this system now over active wildfires. We actually are supposed to find out tomorrow if those come, if the announcement of those awards. So fingers crossed, and hopefully we'll be able to continue to develop the sensor and demonstrate it over actual wildfires. But in tandem, we've also recently won an Air Force Phase 1 STTR in partnership with the University of Colorado Boulder to add the real-time downlink and edge processing capability. So we completed that contract and basically determined that it is quite feasible that we can do enough edge processing and downlink critical information in a small enough package, data package, that we can give useful hotspot information to anyone that would want it on the ground in real time. Next slide, please. Just to continue on that thread a little bit here is, we touched on some of these things, but I mentioned broad area. It's important to mention too, when we talk about broad area from the system, anywhere from a 20 to 50 kilometer projected ground swath is our capability. And that changes based on the spatial resolution. So the way we do that is angle the camera further to get a larger swath, but some resolution degradation. But again, the thing I'll mention, I think that's most important, is this is a very, very low cost system. Again, single digit thousands of dollars to build each prototype vehicle, the balloon plus the sensor, and each system is fully reusable, meaning you can fly it, 5, 10, 15 times. That's an innovation that's unique to what we're building at Urban Sky. We're the first company to really build these reusable stratospheric zero pressure balloons. So that really hasn't been done before, and we're using all new materials to do that. And with what we're building our balloons. So yeah, that's really important for us, is that we keep the cost to downlink critical intelligence as low cost as we possibly can and make the operation very easy and rapidly deployable if it's needed. Next slide, please. Could touch briefly on this, but get a lot of questions about regulation. And yeah, so we're fully compliant. We fall under an existing precedent for NOAA and the National Weather Service and the FAA, which is the 6-pound payload class for unmanned free balloons, which is essentially what standard weather balloons are today. So we do file NOTAMs every time we fly. We do get clearances to do that. And we are proactively engaged with the FAA and go above and beyond in terms of what we need to do for regulatory compliance. Next slide, please. It's just a little bit about our team. Myself and my co-founder, like I said, we've been working on stratospheric technology for pretty much our entire careers. He actually led the design and the build of the spacesuit that broke the world record for the highest space dive ever. So our first investor in the top right there, Alan Eustace, was the person that did that space dive from 136,000 feet under a stratospheric balloon. And he's my co-founder built and designed his spacesuit, and we've been working together with Alan on this business ever since. Next slide, please. Yeah, and so that pretty much wraps it up. So we'd love to work with anyone that's on this call. Really, what we're looking for now is feedback. We're looking for ways to build a system that meets your requirements, and just to give us some intel and information on how to better this product. So please, by all means, feel free to reach out at any time. We'd love to collaborate with anyone on this call, and thank you so much for your time.
Yeah, thank you, Andrew. That was a great presentation, and I was just checking the to see if we had any comments in the IO. Yeah, there's several comments in the IO there for you. If you want to check those out, or we'll read them off during the question and answers. We're going to go ahead and go to our next presenter, which is William Cromartie, and let me bring up the IO here. There it is. So William is from Spire. He's a former federal officer and national security subject matter expert in aerospace and satellite systems, space counterspace weapon systems, counterproliferation, and aerospace sector geopolitics. So go ahead, William, and take it away.
All right, great. Thanks for having me. Is the sound coming through clear?
Yes, it is. Thank you.
Okay, perfect. So to start off here, I'll also introduce Chris Manzek, who's on the call. Also, he's one of our meteorologists at Spire.
Yeah, thanks, Will. Happy to be on. You guys hear me okay?
Yep.
Perfect.
Yes, we can.
Okay, great. So just to start off, so we're Spire. We have 114 satellites currently on orbit. And if we go to the first slide here, forward one, start talking about what some of these satellites are doing. So basically, one of the many things that we're doing from space right now is we're collecting weather. And we're collecting weather partially with a focus on items that are relevant to wildfire topics. So we're currently the largest producer of radio occultation and space weather data. As I mentioned, 114 satellites on orbit. We're launching these like crazy. When I joined Spire a year ago, we had 88. So we're literally launching dozens of these. We have 32 ground stations currently. And really, in terms of the role that we're playing here in the weather sector, it's filling in gaps, especially in a lot of regions that are underserved or might not have physical infrastructure for weather sensors. All right, next slide. So in terms of what we're doing here for radio occultation, I'll talk about this momentarily on the next slide. But essentially, we're collecting weather and atmospheric data from space using this technique. So a whole lot of our satellites up there currently have this payload. This is one of a few different types of data that we collect. You know, we're also collecting ADS-B data for aviation. We do AIS for maritime, a whole handful of space weather data. But in terms of what really provides the most value from an atmospheric science perspective and trying to understand things like winds and storm patterns and the kind of data that feeds into fire weather topics, radio occultation is a key factor here. Next slide. So if you're not familiar with it, basically radio occultation is looking at how signals bend through the atmosphere. And so you can see the red dotted lines there. That's a representation of a GPS signal or a GNSS signal going from that initial GNSS satellite there, hitting the atmosphere and bending. And you can think of that kind of like if you shine a flashlight through a prism, right, and it breaks out into different colors on the wall. Signals likewise will bend as they go through the atmosphere, and that gives you a whole lot of interesting information about temperature and pressure and humidity and atmospheric conditions that you need to come up with a weather forecast. So you can also see those turquoise lines there that are bouncing off the Earth. So that's when those signals from the GNSS satellites go down, they hit the Earth and they scatter. And so in addition to looking at how these signals bend, you can also look at how they scatter. And so one of the key elements there that's useful from a fire perspective is soil moisture, because that can serve as a pretty good proxy for vegetative ground cover when you're trying to do fuels analysis. And so essentially, you know, we're launching more and more of these. We just launched 2 more that do have that payload for soil moisture. And so, you know, in terms of coming up with a true soil moisture estimate that blankets the entire globe and covers a whole lot of locations, like, you know, forested regions where there might not actually be physical sensors currently, that's the role that we end up playing right there. Next slide. Next. Okay. So one way to think about it, if you can go back there to the slide with the dots on it, I think there's a little bit of lag there. Okay, great. So one way to think about it is, if you think about weather balloons or radiosondes as they're going up, essentially each of these RO measurements looks like taking one weather reading as if a balloon was in that location, but doing it from space. So you can see here, especially in an oceanic context, right, you get a whole lot of applicability there. But then, especially also in rural areas where you might have large forested regions, that's another reason that you might end up pulling in RO data so that you can hit those rural areas and have a good estimate of wind and atmospheric conditions above what could become a fire zone. Next. So essentially what we do here, we pull this in, we pull all that data in from space, we assimilate that, we have our own NWP model that we're running that does forecasts on an 8th degree resolution grid or 12 by 12 kilometer grid. And we're running our own AI and machine learning algorithms on that, and then ultimately that comes out in an API. So for example, if you have an incident commander that's using Esri systems, for example, it basically plugs right into that. Next slide. So one other thing that we do here, it's called an ensemble model. Essentially, it's looking at all of these different models that are used for weather modeling, weighing them based on their historical pros and cons and performance in the past, and turning that into one unified model that then can be fed into things like fire weather modeling, both in kind of a real-time tactical sense, but also in a historical sense of looking at historical fires. Next slide. So as I was mentioning, there are a few different elements that we touch on here with these different data that we're collecting from space. The maritime sector being AIS, aviation for ADSB, but also for weather here. So I know there's been a lot of focus on UAS topics, and this is something that we've been very actively involved in, specifically the question of UAS weather and looking at kind of the micro forecasting that you really need to make sure that you don't lose UAS assets, whether that's in a tactical firefighting sense, or if we look at it for like a border security sense, right? I mean, there are a whole handful of areas that UAS technology is being rolled out in, but especially with kind of the complications of fire weather and interactions between large wildfires and cloud cells forming above, we're definitely seeing more and more interest on that UAS topic in the wildfire sector as well. Next slide. Okay, and we can skip this one. Next slide. So one other thing that we do here, we also will do point optimized forecasts for specific locations. So in this case, if you have an airport with a runway, essentially that's taking that large 12 by 12 kilometer NWP model and then downscaling that and localizing that for a specific point on the Earth. And so, this is essentially pulling in local weather sensor data to come up with an even more localized forecast for a specific set of coordinates. Next slide. Okay, so in terms of a case study here, there are two that we're going to talk about, and I'll turn it over to Chris here, and he's going to speak here for a few minutes about Chiron, and then I'll speak for a couple of minutes about a hosted payload that we're doing with Aurora Tech that focuses on wildfire. So Chris, over to you.
Yeah, thanks, Will. So Chiron is a partner of ours at Spire Weather who has seen some really high degrees of success utilizing Spire's weather forecasting system specifically inside their own proprietary fire prediction algorithm, essentially. So Chiron is based out of Brazil. They build a software platform that uses some proprietary data sets as well as available satellite data sets, and have a lot of expertise in this domain of sort of wildfire prevention and essentially forecasting risk of where wildfires are likely to occur based on a multitude of different data sets. And we have some examples of, and this case study was published with Chiron highlighting that, as compared to just using standard weather forecast data that's freely available and local, readings from airports, so localized sensors that may or may not be very near a wildfire location, they've seen an increase in 30% of the accuracy in their risk prediction when they layered in Spire's highly accurate weather forecast system which is powered by radio occultation, that entire technology stack sort of that Will was walking us through previously. So let's jump to the next slide. There are a few screenshots that I'll just quickly walk through, and disclaimer that I'm not an expert in their platform, and I also have to apologize for the Portuguese on the screen, but I'll do my best to explain what's being shown here. So Flareless is the software stack that Kiran provides for specific regions. So this is not something they're doing globally at all times, right? It's a specific project that's funded by a local government. In this case, this is in Portugal, in the Fundão region. Where they have an active POC going. So these 4 variables are just an example. There are 12 total layers, I believe, that they use in their algorithm to produce this wildfire risk forecast. And their forecast is highly accurate, or in terms of resolution, right? It gets down to a 10-meter resolution, which is much, much greater than I think what the tool currently in the US provides. So it is essentially, on the screen, we're looking at things like elevation in the upper left, land use in the lower left. On the upper right, they map out the sort of human presence is what they call it, but it's, existence of cities and roadways and streets and utilities versus more urban or rural areas. And then again, additional land use parameters in the lower right-hand corner. And then if you go to the next slide, please, there are 4 additional proprietary algorithms and dynamic parameters. So the ones in the previous slide are considered more or less to be static, right? It's things that don't change very often over time. Although if they do, they'll certainly capture that and update their algorithm. These are dynamic properties. So think of it as, things related to vegetation, things related to soil moisture content. Again, that's where some of Spire's data comes in as well, as Will was mentioning. And then if you go to the next slide, please. Ultimately, what they're producing is not all those individual images where you have to dissect the information. They're combining them and running out a 7-day prediction of the risk of wildfires occurring on a 10-meter resolution, taking into account those dynamic variables as well as the static variables. And then the last layer that they add in, of course, is Spire's weather forecast. So that includes soil moisture forecasts, soil temperature forecasts. It includes, of course, lower atmospheric data such as wind, humidity, precipitation, and other key factors that would come into play here. And again, these screenshots are all from the Fundão region in Portugal, where there's an active POC, and there's some additional labels on the map just indicating some of the other data sets they're using, which, knowing things about what industry is in a specific location and where companies are specifically operating certainly helps them as well. Go to the next slide, please. All right, so this is what the USGS fire danger forecast looks like today. And so they like to show this just because, of course, the resolution of this is just not something that can compete with what Kiran can provide with respect to some of their proprietary algorithms, their additional data sets that they're bringing in, and Spire's weather forecast. So it's very difficult to, and I think this one is looking at El Dorado County in California, I believe, is the focus. I think that's Lake Tahoe in the upper right corner. So it's 1 kilometer or greater resolution in terms of the data sets that are being fed into it. And then if you go to the next slide, they're comparing that to POC they're setting up for the same exact region, smaller region in this case, but looking at the fuel material specifically in that same location. You can just clearly see the degree of resolution is really incredible when it comes to, putting this data into their algorithm. You can jump to the next slide. There's just a few more screenshots to share. So ultimately, this is what the end result of if you were to, stand up a service for the wildfire forecast. You have a time enablement, of course. So this is one snapshot of the forecast from Kiran for the wildfire risk in that same exact region. So again, they clearly see areas where you can identify very, very localized risk areas, high risk areas for hotspots, and therefore, of course, deploy the proper resources or try to get preventative measures or even put instrumentation in place in order to monitor areas much more closely based on what the forecast is saying is a potential for wildfire. I'll say this El Dorado case study is something that's being essentially deployed right now in real time. So they're standing up this POC to make it available for really essentially anybody who wants to take a look at it within the USGS and other services, local fire prevention agencies, et cetera. So if that's of interest to you, reach out and let us know if you want to have access to that tool, because I believe Kiran is more than willing to make that available to anybody here, whether it's just for visibility's sake or if you actually want to use the tool to help in real time during this upcoming wildfire season. Next slide, please.
All right.
And with that, I'll hand it back to Will.
Thanks, Chris. So I'll use just the final minute here to speak a little bit about something that we just announced. So you might have seen this news story. So basically, we're going to be partnering with a company called Aurora Tech, and they're going to be putting up a constellation of satellites that focuses specifically on spotting wildfires when they start, with a certain payload that they're in the process of developing. And so we just announced we're going to be launching this first satellite. So if you jump to the next slide here, there's a little bit more detail on this one. Okay, great. So on this one, basically the payload itself that they're going to be putting up there is a thermal infrared camera. They'll have a data processing unit on there also. And so basically it's looking for fires after they do start, and then transmitting that data down through our ground station network to create kind of an alerting system for specific fires as they're spotted. So this is really kind of an early detection mechanism. This will be, the first of a whole handful of satellites going up there. In terms of sizing also, so you'll see there it mentions this is a 6U satellite. If you're not familiar with CubeSat sizing, a 3U satellite is about the size of a shoebox or a loaf of bread. So a 6U is like 2 loaves of bread next to each other. So it's a relatively small satellite, but yeah, it will be suitable for fire detection and early warning. And this will be the first of many. So hopefully at a future TFRSAC meeting here, we'll be able to give you all a good readout of how this goes. All right, and so with that, I think we're at the very end here. So definitely feel free to reach out, and thanks, Chris, for your help as well.
Yeah, thanks both to you, Will and Chris. That was a great presentation, and I'd like to keep the conversation going after the meeting between us and you, so bear that in mind. I just want to check the chat window here real quick. Let's see, I don't see any questions in the chat there, but I did want to squeeze in one more presentation today. Brian Ashbrenner and Matt von Bargen. Could we bring up 7.2? There it is. And I've given them, we squeezed this in, so I'm going to give them 10 minutes, and then we're going to go into our closeout and open discussion and closeout. So can we get a mic check for Ryan?
Fairly rapidly, but yes, we are working with Matt von Bargen of the U.S. Forest Service, currently under contract with the Forest Service and Air Force SMC, and also collaborating with the team from University of Wisconsin who developed and maintained the operational GOES ABI wildfire detection algorithm. So with that, let's proceed to the next slide. So here is a broad overview of the system we're developing, FADS, or the Fire Autonomous Detection and Dissemination System, as we call it. So this system that we're developing provides real-time detection and characterization of wildfires using data from GOES ABI with the ability to fuse in additional high refresh infrared observations that we'll talk about a little bit later. But I want to draw your attention, first of all, to the animation on the right side of the screen. That's where the eye is probably drawn to. That's a depiction of GOES ABI data from the previous wildfire season, 2020, Southern California, part of Mexico. We have a 12-hour loop of GOES ABI data updating every 5 minutes. And it's worth noting, first of all, that compared to prior generations of GOES data before 2017, we had much more limited capabilities. We had roughly 2 updates per hour. Now we see an image loop that's updating every 5 minutes. And the spatial resolution has also come a long way, about double the resolution that we had in prior generations of GOES data, and also more spectral channels, more information content coming down in the collection of measurements that we are receiving. So a lot of detail. The meteorologists on the line see a lot of weather detail, but also we see a large smoke plume developing in the middle part of the frame. That's the Apple wildfire that developed in Southern California in Riverside County over a period of just about 12 hours. We see here it went from just starting to spreading over a very wide area and producing that massive smoke plume that spread out over a large area. So here is just a color composite of visible images during daytime hours and infrared images during the nighttime image to produce an animation, just to highlight the technology. So to kind of dovetail on that, let's advance to slide 3, or the next slide. So I did contrast the current GOES ABI, on GOES 16 and 17 with what we had prior to, the current generation before 2017 with the launch of GOES 16. Also to compare a little bit with the current LEO systems, low Earth orbit, MODIS and VIIRS systems. The spatial resolution of ABI doesn't quite match what we have currently from VIIRS, but it does, the geostationary assets do provide us with much more frequent observations, continuous 5-minute update cycle. As I said, we don't have the large gaps that we have to contend with the LEO data. So with dynamically evolving wildfires, like we saw on a previous slide, we are getting much more continuous looks. And I have a figure that addresses that in a few minutes. And the third tier of this, the lower blue row, data fusion, which I alluded to a minute ago, fusing data from GOES ABI with additional infrared assets that are currently on orbit without specifically mentioning that class of data sets. We can make use of even higher refresh observations to come up with a value added product that combines all the advantages of GOES ABI that I just alluded to with the quicker update cycle of these other assets. And with new capabilities coming online in the years ahead, it's there's a lot of opportunity here. So that's what this FADS program is all about. We're trying to kind of push the envelope with what we can do with the current state-of-the-art technology on orbit geostationary assets. So as an example, let's go to the next slide. Here is a look at the same wildfire that we showed a couple slides ago. I said 5-minute refresh. Here we are just looking we're decimating the time grid a little bit, looking every hour just to cut down the size of the animation. But we have 3 GOES ABI images here, the 2.2, 3.9, and 11 micron bands. And then on the lower right, we have a detection product from the FADS system we're developing. And so using this information, we see that the FADS algorithm locks onto that heat signature and produces a confidence score. So we look at certain things in detecting wildfire. We come up with a set of dynamic thresholds based on what would be based on the modeled characteristics of the non-burning cloud-free scene and look for big deviations. So going beyond exceeding a threshold by a lot yields higher confidence, and detecting a fire in a given location on Earth also increases confidence. So in the lower right frame of the animation, the green and red shades, the red dots, are higher areas of higher confidence. So we are able to lock onto that fire and confidently detect it as it evolves. And the line plot in the lower right just shows that as we get further and further into the life cycle of that wildfire, we are achieving a higher and higher confidence that we are detecting something that is a real fire and not some anomaly in the data. So that's in a nutshell how the FADS detection system works. So next slide, please. Just very quickly here, a look at another California wildfire. This was the Avila wildfire north of LA, I think San Luis Obispo area, just to show the capability of detecting wildfire from space from GOES ABI through moderately heavy cloud cover. The raw image is on the left from the midwave infrared band 3.9, and the FADS detection product is on the right. The blue and green triangles represent confidence. Green is higher confidence, just to show that we can lock onto it. Sometimes if we have very thick cloud cover overhead, it does cut into it, but then we can lock onto the heat signature very quickly once the cloud passes overhead. So next chart, please. A little bit about false alarm mitigation or anomaly mitigation, depending on what field you're in. There are a number of common features on the Earth that are not wildfires that we do need to screen out in order to just focus on the signatures of interest. So gas flares are one of them. Widespread in oil fields, primarily in North Dakota and parts of Texas, but there are others throughout the Western U.S., and we need to be mindful of them. That is an open R&D topic for us, but we do rely on a database of known gas flare locations that's generated using VIIRS data, and also exploring whether we can exploit the spectral signature of gas flares, given that they are significantly hotter than most wildfires, and the fact that the thermal emission peaks at shorter wavelengths. So that's an open area. And also solar farms, the lower part, they reflect very strongly when the view and solar geometry is just right. And some of that reflected solar energy, is significant at 3.9 microns. That's our primary wildfire detection channel, and they do look a lot like fires. But again, we can exploit the multispectral nature of the GOES observations to look for, peak emission at much shorter wavelengths in the visible, where wildfires have no signature. So with that, we can dynamically screen out that type of a spurious signature and avoid having that anomalous type of fire detection in our output product. All right, a little bit more. Here's an animation. Next slide, sorry. Animation of gas flares just over parts of the Canadian Prairie provinces, Manitoba and North Dakota a little bit, just showing how these images look in the GOES ABI 3.9 micron channel. Actually, a difference between a 3.9 and 11 micron band. They do show up very strongly as these flashes that you see as we loop through several hours worth of data. So we have to, these look a lot like wildfires, but we do have the ability to screen the information out using other information and databases of their locations. Okay, so I think we can advance to the next slide. To highlight the power of having geostationary observations, which complement very well the current family of low Earth orbit sensors, the VIIRS and MODIS. So what we have here again, that wildfire that we've shown a couple of times in previous charts, the Apple wildfire in Southern California. And I want to draw your attention to the plot on the lower part of the page. So the blue dots indicate the wildfire radiative power that we are retrieving from our FADS wildfire characterization algorithm. Every blue dot represents a 5-minute cadence GOES ABI image, and the red dashed lines that you see periodically through the plot are times when we have an observation from a polar orbiting sensor from VIIRS or MODIS, and we see in a very dynamic wildfire such as this, things are happening fast. The wildfire started; it grew very quickly around 2Z local time, and then it faded during the nighttime hours, and then the next day it really blew up. Moving upslope from where it started, there was a lot of dry vegetation, moved quickly and expanded to thousands of acres. And we can see with the continuous look from an ABI solution, and better yet from the ABI plus the additional rapid refresh IR assets that we're talking about that we are exploring, we can rapidly capture these changes on a minute-by-minute basis. And so that's what we're striving for on this current application. All right, next. So that's data fusion, trying to combine or fuse data from ABI and the other assets, which I won't specifically call out by name, but I think just in the interest of wrapping this up and getting on to the Q&A session, I'll talk about where we're going. So if you would advance to the next slide, please. We're developing, it's been an R&D effort up to this point, and we are working to integrate our current capability with the U.S. Forest Service EGP system, or Enterprise Geospatial Portal. So right now we are working on deploying our current version of FADS onto the Amazon cloud. And once fully up and running on the cloud, it will have access to that GOES ABI data, which is made available on the cloud by the NOAA Big Data Project, and also have access to the other ancillary data products that it relies on. And we are in the process of collaborating with the EGP technical team from the Forest Service to establish a pull interface by which they can access these products, and then we'll continue to sort out the details of the handshaking between our system and their system as we work through our current contract period. So looking a little bit further ahead, next slide, please. In my final slide. Right now, we are nearing the end of phase 1 of our 3-phase development plan, developing the core science capability and implementing the initial version on the cloud and interfacing with EGP. Moving forward later into the upcoming fire season and a little bit beyond, continue to maintain the system, monitor the automated processing and delivery on EGP, come up with better visualization tools, and then continue to improve the product based on user feedback. And then phase 3, transition to operations, continue to establish operational quality processing, system reliability, and continue to optimize, and then fully implement that data fusion capability, leveraging that additional high refresh asset to come up with a value added product. So that's where we are, and that's where we are going to support the 2021 fire season and beyond. So thank you for your time. At this point, I will hand it back to Everett and company.
Yes, thanks, Ryan. And since you're right on stage there, I'm going to ask you the one question that I saw on the chat window there, and that is FADS with GOES. Is there a publicly available data product, and where can we get more information on this?
So, as I said, we're getting there. We're getting there. Not yet, but once we get into phase 2 and phase 3, right now we are just working the handshaking with the EGP system, and with Matt Von Bargen from the Forest Service, we're looking at other opportunities to do just exactly that, get this product out there into publicly consumable format. So yes, we are trending in that direction.
Okay, publicly consumable. Okay, got it. Okay, thanks for that. That was the one question for your presentation. I'm going to go back to the morning block to start with. We covered most of the questions for Dave Jones. Is John Melton online?
I am, Everett.
Hi, John.
I am here. I am here, Everett. Yeah, sorry about that.
I do have two questions for you.
Ready.
Is the data and reasoning fabric using model-based systems engineering methods that might be compatible with the AAM reference framework?
So I saw that question earlier, and I sent it out to my local expert, and I'm going to read the response I got back just to make sure that it's correct. So it says the response is the data reasoning and reasoning fabric is part of a TAC-P-CAS, that's NASA speak for Transformative Aeronautics Concept Program, Convergent Aeronautics Solutions Project. So it's a NASA activity that's following the guidelines for those NASA projects, but they do not include model-based system engineering at this time. So sorry, a little bit long-winded there, but that's the correct answer.
John, yeah, that question went right over my head. So the second question is is the data and reasoning fabric related in any way to the digital information platform?
And the answer to that is no, but they are in discussions about partnering in the future. So hold on for that one. I imagine that one will end up being a yes if they're having the discussions.
Okay. Thank you, John. I would be very surprised if Sherry and Matthew is online since he's over in Germany. It's probably the middle of the night over there. Okay. That sounds like a confirmation. So I have Dave Jones. Okay, there was a suggestion for Dave, which I'll share with him. There's a connection. Couple questions. Dave Jones, are you still on?
Yeah, I am, Everett. I'm here. Can you hear me?
I can perfectly.
Okay.
How would you share different levels of security via an application like this, and how would you abstract data to allow sharing to a lower level?
So in GeoCollaborate, if you have credentials that are required to access data, all the followers will be challenged for those credentials. Those that have the credentials will be able to see the data, and those that do not will continue with the collaboration session, but they will not receive the data. And so it allows you to collaborate and share sensitive information. We can also do very temporary sharing of data sets that require credentials, and we can pass those credentials through GeoCollaborate. And then as soon as the leader turns the data set off, it disappears from everybody's system.
Okay, and I actually remember that credentialing and the separation of data sets appropriate to the credentials from one of your earlier presentations, so thanks for that.
Sure.
Next question is, how does a host set up layers in their map? Is there a set menu, or is it customizable, plug and play, etc.?
It's pretty much plug and play. If you can set up your data as a OGC compliant service, like a REST service, then you can share that link to the REST service, and GeoCollaborate can consume it and share it across all the collaborators' platforms.
Okay. REST service, got it. And the third question, would land cover and or fuels layers be useful? We're built on AWS, Amazon Web Service, and serve vegetation data via REST API.
Yeah, sure. So that would be perfect. So land cover data, as a matter of fact, I belong to a GIS committee within the Sensitive Information Sharing Environment within the All Hazards Consortium. And we're taking on a use case that was proposed to us by utilities to do a canopy tree assessment in service territories for utilities. And so land cover, land use data is very much of interest. And so if that were available and updated rather quickly, whether it was from drones or high altitude or satellites or whatever, could provide some very useful information for utility responders for power outages.
Right, absolutely. Okay, thanks, Dave. That was the extent of yours. There was a suggestion which I'll share with you later, and a connection with Amber Soja. John Green, are you still online? John Green.
Yes, I am. I had to find my mute button. my unmute button.
So I have three questions for you, John. What altitudes and airspeeds were used for the Jefferson County and fire examples?
And I'm going to go from memory. I'm actually in the process of looking it up, but I think I remember pretty well. The fire mapping we did out in Boise was at 17,000 feet above ground, and speed, I believe, was 140 knots. And in Kentucky, we flew right around 7,000 feet above, and the speed was 140 knots again. Now, I have to mention the image examples that are in the briefing that we did are from the Wide Area Imager. The T-Bird runs quite a bit faster. So, that's the answer to the question, but I'm not sure that that's the question that they're really interested in. But
okay, yeah, thanks for that, John. Okay, question number 2, T-Bird. What is the pixel count for the sensor, frame rate, and downlink bandwidth required to transmit the data? What swath at a given unmanned aircraft altitude and VSD are you targeting?
So that's an interesting question, which I would love to just give you the simple answer to. Unfortunately, it's a little more complicated. So for example, the sensor count, we use a step stair optical configuration. So each individual sensor in T-Bird is 640 pixels by 480, more or less. But we stitch them all together. So like if you were thinking about how many pixels do I have across track, we're taking 18 frames across track. But you can't just multiply 18 times the 640 because we have overlap. So that's the short description of the sensor count, pixel count. What was the rest of it?
Frame rate, downlink bandwidth required to transmit data.
Okay, let me stop there. I think there's a couple more points, but frame rate in T-Bird is relatively low, and I don't have it in front of me, but it's either 1 frame a second or 3 frames a second or something like that. And again, you got to keep in mind that it's a step stair system, so we're collecting data continuously and putting them all together into megaframes. And sorry, I forgot, swath width, was that the other question?
Yeah, there was a swath, there was a, let's see, a downlink bandwidth.
Downlink bandwidth, okay. And in between, I did see that question, and in between the presentation and this question and answer, I did a little bit of, pulled up some of my notes. Again, it's not a simple answer. The data rate, the raw data rate in the sensor is relatively simple to figure out. The data rate that's going to go down to the ground is going to depend on, and this gets driven by what kind of a comm system do I have available to me. But the system is capable of, we collect the data, then we geocode it. So the way I do the calculation is I take the geocoded pixel, what's the GSD basically at nadir, and then we geocode every pixel as if it were the same size as the pixel at nadir, but they're not, they're quite a bit bigger. So you can vary that. You could pick a different number for what's your output pixel size. And like I say, in my models, I've simply used, basically the best case or worst case, depending on how you look at it, pixel size at nadir. Then you take the entire swath and multiply it up. Anyway, we end up with T-Bird, it's just below 200 megabytes a second. Well, that's a lot of data. We won't be able to get that down in real time. So what do? There's an algorithm that creates a fire layer. So if you have if you don't have a lot of bandwidth, you can just send down the fire layer. That I didn't calculate it, but it comes out to something close to 0. Much less than 1 megabyte a second. Then you can send down compressed imagery, and we've done tests that show we can compress by about a factor of 25 to 1. And again, this is all automated in the system. You select how much compression you want. You select which layers you want. Do you just want the fire layer? Do you want the fire layer and the terrain layer? So like I said, it's a little tough. Just doing that calculation in my head, though, I get down to T-Bird needing somewhere around 8 megabytes a second. And then the other piece that I toss in is you're probably not going to send down all of the data. You're going to pick specific areas of interest, mapping box, and that sort of thing. The other thing I mentioned is we do collect all the data and store all the data, and so we can send down the full raw data set.
Great. Okay. Yeah, and I know that also that swath width is a little bit complicated too. Depending on your altitude and a number of other factors.
Yeah, and with there are a couple of charts in the brief. I'll just click on them and give you a couple of examples. In the CubeSat, the swath width is about 2,000 kilometers. You're flying at I did a model in the Icona at about 23,000 feet above ground. The swath width is about 14 kilometers. a simple calculation is if you want to fly at some altitude, a 90-degree field of view is twice the swath width is twice the altitude. So like in the Icana at 23,000 feet, the swath is roughly 46,000 feet.
Yeah, last question for you. It should be a pretty straightforward one. Are you using quips for the T-bird as you did in the wide area imager?
We are not. The quips are great, but they're kind of large. And in T-bird, we're doing something much smaller. So we're using a microbolometer in the long wave, and we're looking at both microbolometers and cooled INSB detectors in the 2 midwave bands.
Okay. All right. Well, thanks, John. I appreciate that.
Thank you.
Yeah, you bet. Yeah, Mary Ellen Miller, I believe I see you're still online. I have 2 questions for you. Can you provide an update on the MTRI data ferry work?
Oh, I know they're working on it. That's about it.
Okay, they are working on it. Okay. The second question is how is ESI different from EDDI?
I have no idea. I don't know what those abbreviations are. I'm not very good at these questions.
Nor do I. Okay. And I do have a kudo for you, which I will
Oh, ESI, evaporative stress index, maybe? From ecostress?
Yeah, that's not
EDI.
That sounds.
EDI, I don't know.
Okay. Well, we'll see if we can dig that one out, and we'll get back to you on that.
Thanks.
Let's see. Is Stan Kubota online? Okay, we've lost a few people. David Yole or Ali Anabari?
I believe David.
Yes,
Yeah.
Ali's here.
Oh, Ali. Okay, good.
Yeah, I hung around. Yeah, so the 2 questions. On the first one regarding 5G, does providing airborne 5G prevent any specific challenges compared to 4G? The answer is yes, definitely. 5G, obviously, range is going to be the big impact. We'll try to get more throughput, but sacrificing some range. But for most of our operations, we've operated in 3G and 4G LTE, and we typically operate in the rural areas where 5G will probably be the last place where 5G will show up. So it doesn't really affect our plans, since pretty much everything we'll be looking at is using 3G 4G with 3G as backup, and then is going to be 5G capable. But again, I don't see it, the way places we operate, I don't see that being a major factor.
Okay. Next question is on BVLOS.
Yep.
How confident are you in the path to BVLOS ops for your type certification and achieving wide access for flight without a chase aircraft?
Yeah, so we're very confident. We're along the path. We're hoping to get it done sometime in the middle of 2022. We're well along that path, but obviously we don't set the schedule. The FAA does, and they have a lot of questions internally on this size of an aircraft, where we're not again a little guy. We're a fairly large vehicle, but we're operating in rural, pretty low density, Class G and Class E airspaces. So we don't see any roadblocks. It's just going to be, it's just a bit of a grind going back and forth with them. But our configuration wise, we've thought through a lot of it. We've actually done, and I think the follow-on question on is there confidence and concern with the existing sensing technology maturity. We've done simulations with MIT Lincoln Labs using their DGAS simulator, with our dual radar, with ADS-B in solution running through an ACAS XU processor. And what we found is that our solution as it is for sense and avoid is sufficient, given the current, it meets the current RTCA MOPS with not a lot of margin, but once we build in some autonomy, we should have sufficient margin with the existing technology until they're able to build better detect and avoid type of technologies.
Great. There's sort of a follow-on.
Good. Yeah, go ahead.
Go ahead. I was going
No,
to
do you have a follow-on question for him? Go ahead.
Is there confidence concern with the existing sensing technology and its maturity, or with this necessary regulatory change for 91.113?
Yeah, and so again, I right now my answer is I believe we have confidence. Could that change, and could there be some necessity for regulatory changes? I think it's quite possible. There's I think a lot of unknowns, and so hopefully we're going to get more answers. And I welcome folks that are eager to find out kind of what we find out from the FAA as we're going through it, to reach out to us. I think we're going to learn a lot more in the next 6 to 9 months as we get our G1 established with them and get towards our experimental license. So great question. And like I said, my inclination is that what we have will be sufficient, but I don't want to, I wouldn't bet my life on it. Exactly. And then the FAA is, it's a complex organization, and they have a lot of things to think through and a lot of stakeholders. So things could easily change, and I think there'll be some negotiation, and hopefully we'll pave through that path. So we're happy to share that information once we get it with anyone as well.
Okay, well, thank you, Ali. I really appreciate that.
Thanks, Ali.
I just I got a note from Cherry and Matthew. So I'll go to Cherry, and then I'm going to go back to Mary Miller.
Yeah, she's got her hand up. I was just going to mention that to you. So
let's see, where did let's see, Cherian, I did have one question for you. Let me see. Can platform adjust to prevent false alarms in areas with recreation or ag fires on national forest and private land?
Yeah, thanks for that. Can you hear me, Everett?
Yes, I can, Cherian. Thank you.
Cool. Yeah, that's actually an interesting question because it goes down to the gas sensors that we're using for in the network, and the way the gas sensors actually detect smoke is in fact to try to determine what, let's say, the air quality is around the sensor, and the way it detects it is actually by a machine learning model, which we are in fact training right now in our smoke chambers, feeding it all different kinds of normal smoke, urban smoke, cigarette smoke, and wildfire smoke, different kinds of wildfire smokes. And we actually see that the sensitivity is quite high. So it can differentiate even between different kinds of smoke. So it'll be interesting for us to see the difference between campfire, campsite smoke, and maybe normal forest fuels smoke. And we're pretty sure that that would also show up as a difference. That's the primary strategy for being able to distinguish between different kinds of smoke with the smoke that we're interested in. But then the other strategies could also be, because we have location awareness on the sensors, we could put a higher resolution of sensors around these sites, which is what we intend to do, and then kind of dissipate them over a distance, and then check not only one sensor is giving an alert, but also some kind of even machine learning maybe possibilities to check if other sensors around, depending on wind direction also, is giving us an alert, and only then be sure that there's a fire, there's a smoke that's coming from a wildfire. There are other possibilities to get other data and to do it also, but I would say that this would be the two first approaches that we would take for that.
Well, thank you, Sherry. And I do have one other question. What time is it over there in Berlin?
It's almost 11.
Okay. All right. Thanks. Yeah, and thanks for coming back on. Let's go to Mary Ellen Miller next.
Okay.
Ed posted something about the evaporative demand drought index.
So I still Yeah, thanks, Ed. I have not considered anything other than evaporative stress index, so I still can't answer that question well, but I poked Nancy French, and the data ferries at MTRI just got funded to demonstrate operability this summer, and then the system will go to a commercial partner for final development and sales.
Okay, I have that. I got the data ferries that there just got funded. Okay.
Great, thanks for that update. That's wonderful. Wonderful news to hear.
Okay, and let's see, I'll go to the block 6. Yeah, thanks, Mary Ellen. Is Daniel Dalton online?
I'm here. Hello.
Good, good. I hear you. So I have, looks like maybe 6 questions for you. Any concerns about helium as a non-renewable resource?
The answer is, yeah, in development, it's not a problem. When we go into larger scale, we'll switch to hydrogen.
Okay. Scale to hydrogen. Okay, got it. How mobile will these ships be once they are launched? For example, to move large distances, would it have to come back to ground, or do you just put it up and move it where it needs to go?
Yeah, it can cruise. It has propulsion, so we can cruise. And in addition, if we want to go around the world, we'll just pick up a tailwind and, you know, help us get around faster. So we can move very large distances, and we can then keep station where needed.
Okay. What kind of point density and canopy penetration would you expect from the LiDAR systems? Would cloud cover and weather systems affect this?
I'm going to gracefully pass to the experts in LiDAR, because if I dare answer that, I'll get clobbered next time we speak. But I hear it's really, really good.
I can actually answer that, Daniel, to some degree, and Vince probably can too, that with LiDAR systems, a lot of it depends on how many points you're putting out per square meter. Some of those points are going to get through the canopy, some of them aren't. So the more points you throw out there, the more points are going to get bounced back to you. Would you concur with that, Vince?
Yeah, it's kind of a complicated question to answer. It's based upon the altitude of your data collection efforts and the point cloud that you're developing. You're right.
And I would say, sorry.
Go ahead.
I would say the complement to that is, from an adjacent space, is the use of radar up there. If you complement those two, you can get a good level of understanding what's at the canopy level and what's down below. So, I mean, that's one of the general benefits, is that with multi-instruments up there, you can aggregate data and come up with multi-layered data sets that help you see through things effectively.
Right. Yeah, and the cloud and the weather systems, yeah, it's optical. So if you have clouds and weather in the way, it's going to be more difficult for LiDAR pulses to get through. So next question, what kind of point density and canopy penetration? Oh, that's one I just read. Oh, that looks like a duplicate there. Would cloud cover and weather systems affect this? Okay, I think I just answered that.
Radar, though.
I'm going to skip that one there. Helium retention is truly a game changer for airships. And I guess that has to do with the fabric that you have there.
Correct.
Congratulations on this breakthrough. Does your ship have a buoyancy compensation system, or do you bring the ship down with propulsion?
No, we have buoyancy control in the ascent and descent. So yes is the answer. We can control our altitude and the ascent rates and descent rates.
Okay. What is the cost per pound per hour of service?
Damn,
Probably a little early in the game. A little early in the game for that, maybe.
A little bit early, but the answer is, I think, the endpoint we can see is we are very cost competitive compared to generally the other solutions. That's kind of why we're in business, because ultimately once we're up there at scale, then yeah, the unit economics are really good. So I can tell you, just as an sorry, carry on.
I'm sorry if I interrupted you there.
No, carry on. That's fine.
Okay.
Everett, looks like there's two questions for Andrew Antonio. I don't know if you got that latest question yet.
Is he online, Vince?
Andrew, are you there?
Hey, hi everyone, can you hear me?
Yeah,
Yes,
we have two questions for you. Can the micro balloons hold position once they're at 60,000 feet? How do you handle airspace conflicts during the rise and fall, the ascent and descent of the balloons?
Yeah, so our balloons are what are called zero pressure balloons. So we do hold altitude stability, so we can fly to a targeted predetermined altitude and stabilize. It's a very unique type of balloon that allows you to do that. It doesn't ascend or descend. It stabilizes at our target altitude. So that's really important for uniform imaging. And to answer the second part of that question, we generally launch outside of Class B airspace. So we're not within busy air traffic patterns or areas when we launch. But that being said, we also integrate different systems into the balloon to be safer for airspace. One of the things we do is we fly radar reflectors on our balloons, and we're also going to be adding ADS-B receivers and transponders onto our system within the coming months, so that will be visible to other aircraft. But in general, that's how the systems work. And they're so small that they pose very little risk to other aircraft, even if they're launched, and they rise fairly quickly. So.
Okay, one other question here. Well, it's a series of questions in one box here. Are you using a maneuvering system similar to the now defunct Google Loon process for holding position in the stratosphere?
Yeah, so we do not use an active propulsion or horizontal movement system. So we cannot steer the systems. Our innovation actually lies in that the balloons are so incredibly small that they can be launched from anywhere. So a big part of our innovation is in building predictive flight modeling software for stratospheric winds, so we can launch from a certain position to allow the system to fly to the area that we want. So we generally hit our target flight path within 1 to 2 kilometers of our exact prediction. And with a 20 to 50 kilometer swath of coverage, we get fairly precise flight control with that model.
So the second half of that is your airship doesn't seem to have a horizontally directed propulsor, and I think that is correct.
Right. So same answer there. Yeah, we pick our launch point, which allows us to target and fly over the areas we want because we can launch from anywhere.
Okay. All right. Well, thanks for that, Andrew. Those were the two questions for you. And then I guess did I hit Ryan up already with his? Oh yeah, I have the answer typed in there. So that covers all of our questions. Are there any other thoughts from Vince or anyone else before I sort of launch into some closing thoughts here?
I'll join you in closing costs with making, one or two statements towards the end, but I'll let you go forward with that. I don't have anything to add right now, Everett. Okay. One thing I do want to add, actually right now, as you go in the closing comments, is I really want to point out, we want to thank the NARI team for making this all possible. You and I have kind of, over the years, coordinated the TFRSAC meetings and done it kind of on a shoestring, and kind of a tremendous amount of lack of knowledge by us on how to manage these virtual workshops. And so I really want to point out the NARI team who helped set up the staging of all of this and providing us with the forum capabilities to really operate this problem-free. And so thank you to Anna and everybody on the team, and everybody who's out there, please give them a congratulatory handshake or a hand clap, and then we'll let Everett make his comments. Thank you.
Okay, and thanks for that, Vince. Yeah, and I too wanted to thank the NARI team for their support on this. It's different than the way we've done it in the past, but it's been very smooth throughout the 2 days here, which is greatly appreciated. You know, and as I was thinking about some closing comments, I'm sitting here thinking, you know, here we are with all of these great capabilities that are being developed. Can you go to, let's see, yeah, go to the next slide there. This is the same presentation I had up this morning. So here we are with all these capabilities which are being developed, and they're seemingly within reach, but just, you know, just kind of out of reach. And it's a little bit frustrating as a federal government employee working for the Forest Service and working closely to support remote sensing needs in the Forest Service and other land management agencies. We have this huge problem. It's a growing problem. There's actually lots of political and public attention on this right now because we've had a number of really bad fire years, and that's a good thing if we can harness that that concern so that it actually produces support money to help get some of these proposals across the finish line. You know, we've had a number of you know, this meeting here, we can talk all day long about all these different capabilities, but we don't have any funding to help support and push some of these proposals across the finish line. You know, today and yesterday, we've seen many brilliant ISR solutions to real problems. These solutions, thank you, honey. These solutions include data collection, data processing, and delivery of information through either maps or common operating platforms to those that can use it. And that's really what we're trying to do. We're trying to, we have a pipeline, we're collecting data, we're processing data, we're producing products that can be used as intel, turning that data around rapidly and producing products. That's really what we're trying to do. We're trying to give the folks on the ground the best information that we can. Bob Baird got on yesterday, and you know, he's the one that's on the tip of the spear when it comes to having to deal with these serious issues of managing large fires, multiple large fires at the same time sometimes. And so we're trying to help those folks out. Let's see, from the morning, let's see. So, you know, I noted some of the undermining currents that we're facing in terms of lack of funding and, you know, some of the other institutional inertia that we face. Let's go to the next slide. You know, and it's not just the institutional issues, but there's also technical issues that we're working to overcome. And it's just amazing to me that the progress that has been made over the past 20 years in terms of unmanned aircraft, sensors, computing power, you know, the onset of artificial intelligence and machine learning that we're going to hopefully be able to lean on and rely on more in the future to help us with our efficiency of handling data and analyzing data. We're going to continue to work to bridge the gap between research and operations through a number of different means, including this forum here, and making the connection between the end users and those with capabilities, those folks that are developing capabilities. We want to make sure that the folks that are developing capabilities understand what the needs are and what the gaps are. Let's go to the next slide there. I think that's the artificial intelligence one. I don't want to belabor that one, but let's go to the next slide. On you know, the as is, the current condition, we need to build more connective tissue between the folks that are distilling the needs and gaps, that information, and figuring out some way to get all these wonderful capabilities that are being developed, to get them operationalized so that we can, you know, we can make a real impact in the fire community in terms of remote sensing support. So I think, let me see if there's, and I think that's all I really wanted to use out of this particular presentation from this morning. But Vince, do you have any other closing thoughts?
Yeah, and then I'll make a couple of closing comments, and then we can probably turn it over to Anna so that she could kind of highlight what's going to happen tomorrow with the workshop, or if Laura Grindle or anybody's online, it could kind of highlight what's going to happen at the workshop. Some of the comments that I wanted to close with were, God, Everett and I've been doing this for 18 years, 2003. And we started out in 2003 with about 20 members of our TFRSAC, and they included people from the fire management community, so situation unit leaders on wildfire teams, IMT teams. We also had personnel from IMT team, team leaders, commanders, to give us direction and to focus where we needed to make improvements to technical fire imaging. That team, as I said, was at about 20 people, and it slowly grew over time. We now had at today's meeting, I guess the last couple of days meeting, registration that approached 350 people. So you could just show you the general interest in the community with the exchange of information that we provide. And that's what the TFRSAC really was intended to do in our initial breakout. It was to put, quote unquote, the eggheads from the various agencies, federal agencies, research centers, university labs, and the like, together with the fire management community that had these needs and data gaps that they needed filled, but didn't know where to really get the technology advanced to a mature enough level that they could make operational use of those capabilities. Whether it's in sensor systems, innovative platform designs, such as UAVs, data communications protocols, how do we exchange information in real time from acquiring platforms to incident commanders on the ground where it can be made most effectively utilized, as well as collaborative decision environments similar to the GeoCollaborate that we heard about today, and other generalized systems. So, our maturity over the years has really just kind of amazed me and where we've come from. But we tend to now even cycle back to some of the early kind of low-hanging fruit of our early TFRSAC meetings. And that was, we're cycling back towards this idea of data fusion and sensor web. Not every one system, whether it be aircraft, satellite platform, in situ measurement capabilities, has the ability to solve all the issues that we face in technical wildfire management. So we can see that we're starting to take advantage of, in the old days, we started taking advantage of using the directed capabilities of pinpointing MODIS fire observations, and using that to direct our payload acquisitions with our Icona missions back in the UAS days of 2006 through 2009 Western States mission. So, we're kind of form a sensor where we're utilizing detections from other platforms to drive our new data collection. We're kind of going to come back around to that again, where we're using the early detection capabilities of the geostationary platforms, Himawari, the European Meteosat sensor systems, and of course our GHOST systems, to pinpoint early fire detections where we can then designate collections from other platforms that might be able to get higher spatial resolution. And then as we move into those processing capabilities, we're starting to see the need then for pinpointing locations for closer examination and more tactical observation through strategic and continuous persistent observations from smaller platforms or platforms like we saw in today's presentations concerning lighter than air vehicles that have the ability to persistently lag over an event or multiple events and provide consistent information. So that's taking us from the viewpoint of taking maybe once every 14-day observations like we used to have with Landsat, taking it to a couple of times observations or multiple times observations per day with MODIS, taking it down to then persistent observations that we can see coming in the very near future. So I've just been amazed at the progress that we've made in all these technologies, but they all kind of circle around that central theme of data fusion and sensor web. How do we make use of all the resources out there in a collaborative manner to answer the pressing questions we have about wildfire management and wildfire progression and recovery and remediation operations? So I've been very pleased to see this expansion over the last 18 years. And it just amazes me and realize that I've learned so much, but forgotten so much of what we used to do because of all the explosion of new capabilities and technologies. And I want to particularly thank the participants that presented and made their presentations to our community. You guys are hot scientists in the strictest form of the word. The community just amazes me what can be done, and it starts to make me look forward to or point towards retirement because I just don't have the knowledge capability anymore that you all bring to the table. But one thing I will say is Everett and I will continue to be focus points for bringing the communities together. And we hope that this TFRSAC meeting has provided that forum for you to exchange the information. And if anything, Everett and I always say that we're marriage brokers. We may not be able to do the science anymore like you people are doing, but we know the people that are doing the science, and it's you. And we can marry you with those community members that we have relationships with within the fire management community of both federal and state organizations. So that's what the intent of the TFRSAC really is. It's to bring the communities together, of the science communities, the artificial intelligence communities, the sensor science communities, the remote sensing communities, geospatial technology communities, together with those in the fire community that need those tools but don't necessarily understand where they exist, what maturity level they exist at, or when they might be available. So we'll continue to form that community and be the marriage brokers, bringing those parties together. And so with that, I'll conclude my remarks and ask Everett if he wants to make any additional comments, and therefore ask Anna then to follow on with any additional information that heads up for tomorrow's workshop breakout. Thanks.
Yeah, and thanks, Vince. And I think you really hit the nail on the head there. That this, that this is a community, and I think the power of this community is in the people that come to this meeting. The more people that we have, the more we reach out to the community, the more intel that we have to work with, the better we understand the needs and the art of the possible and bringing those together. And so, looking ahead to the fall, I'm really hoping that we can have a face-to-face meeting. I think we've done a good job in the virtual environment here, but it's not the same as having these face-to-face meetings where you can interact with folks, between presentations and so forth. And so there's something that you lose in that. But I think all in all that we've done a pretty good job of keeping the meetings going through the virtual environment. So I guess with that, let's see. Okay. The other thing I wanted to mention was that, we have the third day tomorrow with the NARI folks, and we want to make sure that that folks can attend that meeting if they want to, if they have an interest. If you go back to the website, there should be information there about the NARI meeting tomorrow. So I'm going to be there. Vince is going to be there. And I know that from looking at the sign-up sheet that there's going to be quite a number of people that are at both meetings. So I encourage people to join. And with that, I guess I'll turn it over to Anna.
Thanks, everyone. And I'll keep this brief, but this was amazing. It was amazing to see the TFRSAC for the first time and be able to work with Vince and Everett to really bring this community together. But we're also excited to be adding a third day for the first time. So tomorrow is the NASA ARMD Wildfire Management Workshop. It'll be a little different than today. We will have what we're calling a general session that'll run throughout the day at different times. And that general session will run exactly like what you're seeing here today. There'll be a YouTube link, Conferences.io, and that's how we'll engage with all of you. But interspersed in that general session, we actually have 2 breakout sessions. And what's really great about that is we've actually already sent out to everyone who's registered calendar invites for those sessions. And we're setting up individual rooms so that we can have smaller, more in-depth and robust discussions. So what I encourage of all of you is many of you have already registered, so thank you. We're excited to have you. If you've already registered and know you're going to be there tomorrow, please double check your emails. We sent one out yesterday that you have all your calendar invites for the breakout rooms. Those invites went to the email that you registered with. Please double check that. And if you don't have it, please email NARI so that we can set you up prior to the day tomorrow. But any of you that didn't register, we have closed registration, but we want to honor anyone that was here with us these first 2 days for the TFRSAC. So feel free again to email NARI and we can work with you to see what rooms may have availability so you can dive into those breakouts with us as well. So with that, we're excited to see you tomorrow, and thank you so much.
Thanks, everybody.
Thanks, everybody, and hopefully we'll see a number of you tomorrow. And for those that don't, we'll see you in the fall when we send out further information on our next TFRSAC meeting. But stay in touch with the website because it'll provide information on the services and the presentations and the YouTube links of all the presentations and where to gather that data and then contact the individual presenters if you want to request further information and exchange. So thanks, everybody.
Thank you, Vince. Thank you, Everett.